So you already started streaming?
Yes, I'm on the way of doing this. You see the problem. I have to do all of this, and
yeah.
actually, I think we can slowly start.
Yeah.
Any objections?
No. We can start.
Good. Okay, then first of all, welcome everyone. We're really happy to have you all around here, for the time being virtually. This is, in fact, a third edition of analogous conferences. The first one happened in 2021, thanks to Sravan and Luca holding it from Japan. Last year, we tried to do it in hybrid format, but now we returned a little bit to online because we wanted to cover many more people than previous time. And we are now happy to welcome you all speakers and participants to have nice and I believe very inspiring week of talks. I want to say some technical things before we start. It is that, first of all, I remind you that on the website you can find the program and you can find timetable, and talks start a little bit different days. Little bit different times during different days. So pay attention to the times. It's in all possible time zones, which I could imagine. So speakers, I hope, will appear in time, so we'll be all set. Talks supposed to be 40 plus 5 minutes or something like this. And I think the best procedure, if you get a question during a talk, you simply raise your hand and then we try to accommodate all questions in these 5 minutes. Well, unless you have very, very urgent question, which you cannot wait, but I think we can wait half an hour anyway. Also, I want to say that all the speakers, at least those who listen me now, you will be co-host, so you will be able to share screen and you will be able to annotate on the screen if you need so. It's up to you. And also, after each session, we will have some time for discussion. I think it's a good opportunity for all speakers of this session, or maybe even all the day, or maybe even other speakers to participate and answer extra questions which participants and other speakers have. So I really encourage you to participate in this time as much as you can and have time to do so. And we will hope to keep answering as many questions as reasonable. Also, unless there is any explicit request from speakers, we will live stream and record talks. So in case you want to return to this or have no time to see now, you will be able to do it later. And I think that's it for the organization. Anna and Sravan, did I forget to say something?
I think you said everything.
I think it's all okay. So I think now we can slowly move to the first talk. We have to arrange this first. So Anna, can you stop sharing and then PC will start share the screen?
Yeah, please go ahead.
So people can raise hand if they have questions and we will get
Yes. One thing which I forgot to say, there is chat, of course, and you're also welcome to put your questions in chat. And then maybe it's easier. So not to wait 20 minutes, for example.
So, Alexei, should I begin?
Sorry?
Should I begin now?
Oh, well, first of all, can you share this your
Yeah.
slides? Because I believe you need to share this.
Can you see my screen now?
Not yet. At least me.
Let me do it one more time. 1% and share.
There should be normally just share screen button, the green one at the bottom, and then you have to choose, and you normally choose desktop to share.
Right. Sorry. Sorry about this. I have a computer recently, and apparently I need to open system. Let me try one more time. Sorry about that.
So anything we can advise to you?
Yes, I was asked to open access, and led to the page called security and privacy, location of services, and so on. Allow the app below to record the contents of your screen, even write using yes. So screen.us sure. Now. Sorry that I didn't say this. And cost you extra time. I'm sorry.
So normally it should be just a green button which says share screen. Once you press it,
That's right. Yeah, that is true.
once you press it, should be some choice like desktop, current window, whatever. Normally you choose a desktop.
Right, which I did, but it says that I need to allow Zoom to share your screen, which is strange because it usually I've been using Zoom. So open system preference, which is what I am doing now. So apps supposed to record the contents of your screen, even while using other apps. What does this mean?
Anna,
anybody in the audience who can help?
Anna, did you share screen without any issues?
Yes, I shared it.
Yeah, because normally if you could share, any co-host can share.
It could have a problem. Maybe he has several windows. So maybe this is a problem. What kind of a computer do you have?
I have a MacBook Pro.
MacBook. Stravan, you can advise on this.
Yes,
Okay,
this is because you are not on the same window. So you have to change your window. So your Zoom should be in the same window as this document that you want to show us.
And so currently this is through Windows. Usually I just go directly from my MacBook Pro to share my screens.
Yeah.
So
So
today
if-
is a little bit surprising to me.
Mhm.
Joyo, are you online?
Yeah. So did you click the share screen? What are the options you are getting? Can you?
Yeah. Once I click share screen,
Uh-huh.
there appears this page where, like what we usually have,
Yeah.
desktop,
Yes. You can
desktop
select
one,
the.
and whiteboard, and so on.
Yeah.
Microsoft PowerPoint, and
You can
so,
select the desktop.
so I clicked share, but the response was, a new window says allow Zoom to share your screen, and the suggested button to click is that says Open System Preferences, and which I did. I clicked that, but then now it appeared. Now a new window says the title of the page is Security and Privacy, and now this privacy, which has does show appears to have this zoom.us, but I clicked that, but there's no action allowed. Change privacy preferences on
Maybe
Mac.
let me try. I'm also using Mac, so maybe if something with Mac, I can try to.
But this is unprecedented.
Well, you
I
can
never
see my
had that
screen,
problem.
right? Yeah, it's working.
So is it possible that not to keep everybody waiting, let me is it okay to exchange the time with the next speaker? So
Maybe you can send us the slides and we can move.
Right, that was what I was also thinking.
Yeah.
So if I can do this, and maybe perhaps either of you or Katarina can help show the page. I just say next page.
We can do
All
that.
right. Okay.
Yeah, we can
So
do that.
let's
Please
do
send
that.
us.
Yes,
slides.
yes, maybe it's a solution because it looks like your computer is blocking you share, which is not standard. Yes, you can send by email to me, for example.
All right, and I am doing that right now.
Okay.
Alexi, you can forward that and then I will share screen.
Okay, good.
It's coming up.
So are you sending it right now?
Yes, I am. The file is not also big. It's around 18 megabytes, and it's still turning. Yeah, it's progressing. Please hold.
For what? So did you send it?
Yes, it's not done yet.
Okay. It's on the way.
Right now, it's done.
Okay.
So it's like a little bit big file, yeah?
Right.
Yeah,
Okay.
So is it okay?
Yeah. I'm opening it, so I'll share screen.
So Sravan, can you share screen?
Yeah, I'm opening it, so it's loading.
Okay.
In fact, I thought about the same about 5 minutes ago, but I didn't say it.
Yeah, but since it's happening, all these technologies, especially given that they change programs almost every month, it's really crazy. It's really fantastic. No, they really declared this officially that they will change Zoom every 3 months. Every 3 months, you're obliged to upgrade. If you don't, you cannot connect.
Well, I'm still trying to open this document.
But did you load at least already?
Yeah, well, Microsoft is taking time. Do you have PDF of this in very chance?
I can do it. Yeah, I can do that.
Yeah, usually PDF is a lot.
Well, Sraun, I think I managed to open it, so I
Okay.
can try.
Okay. Yeah, you
Oh,
can do
very
that.
nice. Thank you.
Okay, so then you can start
There's one
sharing.
thing that I don't know how to make a full screen in PowerPoint, but
I'm
Just
now-
share screen. We'll find out. Okay.
that's
I
fine.
also managed to open it finally. So anyway, yeah.
Yeah, it's here.
So is it
Wonderful.
somewhere at
it.
the top? It should be presentation.
Yeah, view. You can go to the view.
Slideshow. No, slideshow to the right.
I
Yeah,
see.
slideshow. It should be presentation.
Right.
Perfect.
Great. Thank you very much.
Okay, it is like this. So then let me go ahead with sharing this session, and we're happy to start. Despite all these technical problems which Zoom encouraged to us, we start with Professor Chen from Taiwan University and from Stanford, who will tell us about black hole information loss paradox and the Annabelle experiment. So please, something like
Thank
40
you.
plus 5 minutes.
Sure. Thank you very much to both chairs and chair of the session. So this is my tremendous honor to share with you some thoughts about the black hole information loss paradox and a report to you, a ongoing attempt to address this issue through experimental means. So yes, please, next page, and next page, please. Yeah. So I'd like to take this talk as a tribute to Stephen Hawking. From the beginning to the end of this talk, the entire content has to do with his thoughts. So next page, please.
Next.
Yes. Right. So the following couple of pages is kind of a common sense to essentially all of you experts. And so please forgive me for insulting your knowledge, but just for the for self-containment, let me just begin by saying, as we all know, that black hole Hawking evaporation with this famous Hawking temperature formula, which links several major branches of physics in one stroke. With Newton's constant, you connect to gravity, GR. With Planck's constant, there's the quantum mechanics involved, and with Boltzmann's constant, you have statistical mechanics, etc. So this is a remarkable discovery by Hawking. Next page, please. Now, soon after his seminal discovery in 1974-75, he pointed out that this black hole evaporation may result in the loss of information, which hits on to one major tenet of quantum mechanics, which is conservation of probability, or in a pure theoretical language, there's the unitarity seems to be violated. Now, this is kind of extremely strange in the sense that black holes, as we by now all know, has this thermal entropy, or let's say Bekenstein-Hawking entropy that is proportional to the surface area of the hole. So there are tons of information. In comparison, the Hawking radiation is in the form of black body radiation, which is well known to have very little information. Just one curve fits all. I mean, you really don't. It's just total randomness. And so eventually, if the black hole is evaporated entirely, and then it turns all into heat. So where did the information go? Now, it's been 48 years after Hawking stimulus discovery, but the nature of black hole evaporation is still under debate. Next page, please. Next page. Yes. So now, the big question: how can Hawking radiation carry information out? After all, that's actually not even half of the question. The problem. I think more importantly, if so, how? Next page, please. Now, there's no lack of attempts to resolve this issue. As I just said, the problem or the paradox was first pointed out by Hawking himself in 1976, and followed by endless debate ever since. Now, solutions. Let me quickly be clear. This page is not only partial; it's totally biased list of the solutions in the history. I think I'm very sure different speakers will have a different list, and maybe 3 pages long. So this is really a partial review of it, and please do take a grain of salt. Now, solution, the more known ones include, for example, in the early 90s, Susskind and Maldacena and so on, the black hole complementarity. Then in 2012, Koczynski and company suggest that solution is not self-consistent, and propose that the black hole should have a firewall. And I suppose many of you have heard and known about this. Then a somewhat different track was concentrating on entanglement between Hawking radiation and partner particles. To my knowledge, first person who pointed this out was Frank Wilczek in 1987. However, that was a talk given at I think Texas Relativity, the famous series of meetings, and was a proceedings paper until I think maybe 5 years later, he and his students and co-workers published the first refereed paper. Then Schutzhol and Unruh in 2010, Kota Schutzhol Unruh 2015. Now, there's also the suggestion or thinking whether if black holes upon at the end of its evaporation will not evaporate entirely, but leaves behind a Planck-sized remnant protected by what's called the generalized uncertainty principle. And having a remnant there, it opens other possibilities of preserving the information. And this was well reported in the Physics Reports 2015. Then there's also counter-argument against almost every proposal. And the one includes the argument against the firewall conjecture by myself, Don Page, Sasaki, etc. Now, I suppose you'll hear this BMS software proposal by Hawking, Perry, Strominger. Then there's also the champions of the other camp, mainly led by Bill Unruh and Bob Ward. And they published many papers over decades, but the most recent, 2017, they argued that not only there should be no firewalls, which is in agreement with me and my coworkers' arguments, but also even if the information is indeed lost, they argue that there's nothing wrong with it. Now, then more recent years, I think beginning 2019, there's a rather exciting development from the on the string theory side. It begins with island conjecture and as well as replica wormholes, and I'll come back to that point a little bit later. A more recent attempt has been by my co-workers and myself, collaborators. This is to base on pretty much the original path of Hawking and Hartle, and to invoke Euclidean path integral as a approximation to the true quantum gravity theory, and to try to address it. And I'll come back to it. Next page, please. Yes. Now, talking about quantum entanglement, this is, again, sorry, I hope it's not insult to your knowledge. We all attribute this to Schrödinger, and by actually this terminology was invented by him, but not sure if everybody knows. But I only knew this about maybe 10 years ago, that the whole idea was really coming from Einstein, and Einstein shared the idea with Schrödinger, who was in Dublin at the time. Einstein was in Princeton, and so the famous Schrödinger's cat was original a Keck-up, something Einstein, some Gedanken experiment. So, but anyways, that was not the main point that I'm trying to make, but just that these days even on newspaper, we see these buzzwords, quantum entanglement, and Schrödinger insists that this is not just a property of quantum mechanics, it is the property, character of quantum mechanics. It fundamentally breaks quantum mechanics from classical physics. Next page, please. And also, one salient feature about quantum entanglement is the monogamy character. That is one husband, one wife system here. Now imagine that our universe is separated, it's partitioned into system A, let's say this dark gray region, and system B, the white region. But quantum field doesn't care how you partition the space. So there's must be entanglement, between vacuum fluctuations that can cross the border, some inside, some outside, or of course there are also the cases of both inside and both outside. So this reminds us of the famous von Neumann, concept of entropy. Next page. Now, the first serious attempt to address the information loss paradox through quantum entanglement was by Tom Page in a series of 3 papers in 1993. Now, so the essence of his argument is the following: if if you have a system A where the entropy, let me say the Boltzmann entropy keeps going down, and then if the system has a radiation, the radiation just keeps going up. We call it system B here. Now, so he investigated the entanglement entropy of the entire system. Let's call it as A sub A of B. Now, then it's found that roughly past half, half time, when the black hole evaporates more or less down to half its mass, the time where the entanglement entropy reaches the maximum, and after that, the entanglement entropy is just gradually reduced. And there is a technical definition of the meaning of information, here represented by the symbol I, which is S of B minus S of B/A. And this information will be, according to the definition, will be essentially nothing until after the page time, and then it shoots up. And finally, at the end, recovers the entirety of the total entropy of the system. And so this is truly seminal, but I must warn you that John Page's treatment of the system has no gravity. This is a very important point to make. It's a quantum mechanical system. However, it's 30 years since there's numerous efforts to incorporate gravity into his notion, but not very successful so far. But there is a kind of a side story about this. In 10 years after, roughly 2004, I think, and you know that Don was a postdoc of Stephen Hawking. Now, they made a bet in the early 1980s about the information laws, and so the Hawking promised to pay Don Page $1 if he was wrong. He thinks that information will indeed be lost, and Page believes that information will be preserved. And if he lost, he will pay Stephen Hawking $1 British pound. Now, in 2004, Hawking conceded, and so he paid Don a US $1 bill. By the way, this photo was given to me by Don Page. Too bad that the resolution is not that good, but you see the tricky smiles on Hawking's face. That is because this $1 bill is fake. In the middle it is not George Washington, but Marilyn Monroe. So that's the way he made jokes. Now, next page, please. Yes. So now, so the following several pages is to allude to you, my collaborators and my current thinking. Of course, it's not claiming that this is the solution, but just to let you know that there are these ways of thinking. So, as I already said, we invoke the Euclidean path integral as a faithful approximation to the true quantum gravity. Now, here I'd like to add a few more comments. The fact that the attempt to generalize Page's curve in GR to include GR has failed. It is often regarded as the efficiency of the semi-perturbative calculation in GR. In particular, the decrease of the entanglement entropy after Page time would require non-perturbative effects in quantum gravity beyond our current understanding of GR. So one possible circumvention of a full-blown quantum gravity calculations, which does not yet exist as we know, would be via a new classical saddle point, for example, a soliton, deduced from a valid approximation of quantum gravity, where a semi-classical tunneling around such a new saddle point, for example, via instanton, might be able to capture the essence of non-perturbative quantum effects evaluated around the original saddle point. So under this light, the Page curve would result from nothing but a transition between those two saddles. Okay, so instantons. So this is the philosophy behind our attempt. Okay, so now the left side of the figure is what you saw in the previous page. This is the, let's say, canonical page curve. Now on the right side, I put down so on the lower right is the in state of the wave function of the universe. Then on the upper right, then we posit that there are possible different futures and in the outstate. The eventual outstate should be the superposition of all the classical boundaries. Next page, please. All right. So in our approach, we argue that in order to solve this information loss paradox, one needs to assume two conditions. One we call multi-history condition. That was what I just mentioned to you. The other is called the late time dominant condition. That is to say that the information preserving history is dominated at the late time. So here's two Paris diagrams to explain to you. The leftmost is the one we are very familiar with. The green curve was the trajectory of the collapsing matter. The red one is the apparent horizon, and the blue is the event horizon. And now in the middle, we posit this kind of a world where at some point during this matter collapse, some tunneling happens between the possible paths in the Euclidean sense. And after tunneling through, the history has changed, and the singularity disappears. And so this is the end of it. And the rightmost diagram is just a cartoon showing pretty much what we are saying. We start with the in state and end up with multiple possible out states. But of course, quantum mechanics dictates that we have to do the superposition. Now, of course, the allowing in the setting of Euclidean path integral, it is inevitable that quantum mechanical effect allows the tunneling. And so this A and B are just two examples of tunneling. Our assumption is that in the early part of the universe of the evaporation, the tunneling is dominated by classical means, and information was losing. And towards the final stage of black hole evaporation, the path, the tunnel is to the path where information is preserved. Next. So these two curves shows our results. On the left, one sees that for simplicity, we model this whole history of physics with only two paths, two histories, and the information loss history, losing history is in the black curve. The probability of the information losing history is the blue curve, and the information preserving history, the P2 is the black curve. Now, on the right side, when you carry out the algebra, you found that one very important result, which is that the essence of page curve is indeed honored. That is, the entanglement entropy does reach a maximum, and after that, decrease back to zero. However, there is also a very important difference. That is that instead of a like his original triangle, you found that the page time is rather largely shifted towards the late time of the black hole evaporation. And you see here three different curves, black and blue and red. Now, unlike in the case of Page's original curve, which is just one single curve for whatever beginning, initial mass, and so on. But let me emphasize again that Page's, let's call it the canonical consideration, does not include general relativity, does not include gravity. Now, in our calculations, the location of the Page time does depend on the initial mass, right? If you begin with a much larger mass, the Page time goes much towards the end life of evaporation. Next page, please. So please allow me to make a quick comparison with recent developments based on string theory. What does that mean? The replica wormholes and island conjectures. These approach share two essential features with our notions. First, there exists more than two contributions to the evolution of the entanglement entropy, where one is dominant at early time and the other at late time. Second, the final entanglement entropy is dominated by the late time condition. So these, I think, these two features are common between our approach and the string approach. What's different is the following. So let me add one more comment. This therefore is analogous, ours in spirit, to the what's called quantum extremal surface (QES) computation for black holes, which is what the replica wormholes and island conjecture are based upon. However, there is to us a rather notable difference, which is that in the entanglement entropy calculated in the quantum extremal surface is based on the density matrix. Here we're talking about quantum mechanics or quantum field theory. So based on density matrix instead of the quantum state, which is the standard quantum field theoretical approach, as we all know. And that is also what we have followed. So we follow quantum state instead of density matrix, which we think has a jump. All right, so next page. Okay, so let's switch a bit to depart from the theoretical discussion, but now into how we can address the issue experimentally. Now, the reason why our debate on the information law started in nearly 50 years, that was essentially theoretical, was because as you just recall my previous slides, whether the information is preserved and more importantly, how is it preserved, depends mostly on the late time of the black hole evaporation. However, astrophysical black holes of solar mass size, etc., has a Hawking lifetime of 10 to the 67 years, but the age of our universe is only 10 to the 10 years. So essentially, except some tiny primordial black holes at the beginning of Big Bang, otherwise, the astrophysical black hole after gravitational collapses are too young. This is like infant in the Hawking sense, and therefore there's just simply no way, not even if you can indeed detect Hawking radiation from these huge black holes, there's just no way to address the information paradox. Next page, please. Now, analog black holes, therefore, the idea of invoking laboratory settings to simulate black hole physics makes a lot of sense. Not that we just were tired, lazy, we don't want to go out to look for it. By the way, we don't even know when and where would there be a black hole happens to decide to end its life and finish its evaporation. But that's an aside. To go to the laboratory to study black holes, ironically or interestingly, maybe for the first time in history, is indispensable, shall we say? That is not like, let me make a model just for the fun or what, but that I think, to my knowledge, it is rare in the whole history of physics where you have to rely on an analog system to study black hole, to study a issue which is extremely fundamental. It's a potential conflict between general relativity and quantum field theory. Yet, we cannot find a direct answer from observation. But this analog black hole idea was already proposed by Bill Unruh as early as 1981, where he proposed using sound waves in moving fluids, where he called dumpholes. Then there's the idea of traveling index of refraction in media, violent acceleration of electrons by lasers, and electromagnetic waveguides, and Bose-Einstein condensate. The vortices serves as analog black holes, etc. These are all very exciting. Now, the one I wish to address you more is this last bullet, accelerating mirror. This was already studied as soon as Hawking made his seminal discovery, first by Davis, then pulling Davis, and then Davis pulling Unruh, Wilczek, Collins Wiley, etc., etc. Now, next page, please. Oh, just now I forgot to comment that in comparison, most other proposed analog black hole ideas, can we please switch back to the previous page? Yes, so other than the last one, most of the proposed ideas intends to test the thermal nature of Hawking radiation. Is it purely black body, gray body, whatever thing? Not so much as to test out the information loss paradox, except this last one, or let's say at least my own ambition. Next page. Yes. So this is the space-time diagram of a flying mirror. Already accelerating. So to begin with, it is already kind of curving towards 45 degrees, the blue ray, the light cone. And then imagine that you manage, well, in a laboratory, you can imagine having something goes on forever. So it will stop at some point. Now, at that point, then the mirror stops, and so the whirl line just keep going straight up. So that black curve is the whirl line of the mirror. Now, the vacuum, we believe that's this fluctuation, quantum fluctuation, anywhere, anytime. So it's bound to interact with this black mirror. Imagine that these blue and red dots in pairs are vacuum fluctuations. Let's say they're photons. As we know, vacuum has a zero quantum number. So the fluctuating pairs must preserve all the quantum numbers. In the case of electron-positron, one electron, the other must be positive. And they each also cancel all the spins, all helicities, and so on, for momentum and such. Anyways, now it can happen that one of the two particles in the vacuum fluctuation happens to hit this flying mirror, and which let's assume to be perfectly reflecting, and so it's being reflected. Whereas the other particle in the pair, not so lucky and to keep going, and without any chance of hitting along the no ray, and this actually therefore serves as an effective horizon in the black hole sense, where indeed even the bona fide Hawking effect has to do with the black hole interaction with the vacuum fluctuation in the vicinity. Now, in the end, when the mirror stops moving, the mirror now borderline goes straight up, so that red dot must at some point hit, and then being reflected. Now, being stationary, this reflected red particle does not suffer Doppler shift, versus this blue dot, which hits the mirror that is receding, and therefore it suffers a redshift. So therefore, in the end, if you manage to measure both particles in the pair and study their correlation, and you can their helicities, their energy momentum, then you can decide how they are entangled. And so, by the way, so this Doppler redshift plays the role of gravitational redshift in the true black case. Next page, please. Okay, it is already 8 minutes after 2. I think I should skip some pages. These are technical details telling you how you can calculate the outflux, and the next page, please. And you can calculate the entropy of the system, and depends on how you design your flying mirror, the sudden stop of the mirror, slowly stopping, or the coasting and so on, long propagating. You can simulate different scenarios of black hole ending or fate. Next page, please. Now, how do you realize it? It happens that there's something called plasma wave field acceleration, invented or discovered first in 1979 by Tajima and Dawson, invoking laser to propagate through plasma, and the wave, the wave so excited can in principle accelerate high energy particles following behind. And in 1985, a second scheme was proposed to replace the laser pulse with the particle beam, charged particle beam, and it was argued that or showed that the equally strong wave, plasma waves, can excite and can accelerate. The plasma wave field was born after the 1985 paper, for which I happen to have contributed. So these two schemes, the LWFA and PWFA, by now it has become a very active field in laser plasma science, and being actively pursued worldwide. Next page, please. In the nonlinear regime of these plasma waves, it is almost like a tsunami. So it's like a piece of wall moving in the ocean. So it's already skewed and not sinusoidal waves anymore. But it's even more effective in accelerating particles and so on. Next page, please. Now, it was pointed out in early 2000s that such a plasma wave can serve as a nice mirror. If one, collides this mirror with a, optical laser pulse, then upon reflection, it enjoys a Doppler pollution. And so an optical laser pulse can instantly turn into an X-ray pulse, coherent. So this is if this can be realized, this is wonderful. Next page, please. So in 2017, Jiramuru and I suggest that why not use this mirror if we can manage to accelerate it, then we can realize experimentally the accelerating mirror scenario for analog black holes. And I think I've already mentioned, effective horizon just now when I was explaining the world line. So these are the analogy between a true black hole Hawking evaporation on the left side and a analog black hole using a flying plasma mirror on the left side. Now, as you can see, the analog Hawking radiation is really flying backwards. Then the partner pair, these bubbles, as if they're sticking to the backside of the mirror, co-moving. And of course, as we remember, Einstein's equivalence principle, strictly speaking, is not quite true because gravity cannot be translationally invariant. But if you imagine a tiny patch, tiny pixel on the surface of a black hole, then you are allowed to imagine a constant gravity, let's say G, and then you mimic that with a tremendously large acceleration provided by this plasma wave. Okay, next page, please. And so, how do you make it speed up? The idea is that you just simply gradually decrease the density of the plasma with a profile, and you can design the profile, and so that this laser pulse, as we know, moves slower in the medium, right? And the denser the medium, the slower it moves. So if you manage to make your medium gradually more dilute, this laser pulse will speed up, and therefore the plasma wave, the mirror dragged by it, will also speed up, and then Hawking radiation will come up. Next page, please. Next page, yeah. So without going into details, one can even calculate the effective Hawking rate temperature of such a system, where the capital D in the denominator stands for the characteristic length of this. Assuming a constant plus a Gaussian density profile, and this is the sigma of Gaussian density distribution. Next page, please.
Piscina, just to say that
So,
it's almost 40
yeah,
minutes.
I will finish up in 1 minute. So
Sure.
this is so I launched a international collaboration called Analog Black Hole Evaporation via Lasers, (ANABL), and that involves Echo Polytechnique, CA, Institute in Japan, National Taiwan University here. Next page, please. Now, next page. Knowing that most of our audience is non-experts, not experts, mostly theorists. So let me not dwell into technical details of this experiment, but just to say that this experiment, if you like, you can consider it as a flying Einstein-Rosen-Podolsky experiment. Einstein-Podolsky-Rosen experiment. Next page, please. Status is going on fine, and when we have carried out our first experiment in Kansai, Japan, last August, but it's just the beginning, and we are, we're very busy doing all the R&Ds mainly at NTU, and the goal is to do the next experiment in at the Apollon laser facility in Saclay, south of Paris. Next page. I think that's the end. This is the end. Yeah. No, please move on to the last page. Yeah. So thank you very much. I've taken too much time. Thanks.
Okay, thank you very much, and thank you for a very interesting talk. So questions, other questions? Anyone wants to raise hand and ask something? I remember it was some questions in the chat. There is also raised hand. Yeah.
Okay, wait.
So there is a question from Sravan.
Hi, Pishan. Thanks for the very detailed talk and very interesting. So my question is related to, well, usually in the Hawking papers, one of the major point is about CPT invariance, whether it is hold or broken. So what can you comment about that, whether CPT should hold
right.
or it should be broken?
Yeah. So
Где руку поднимать?
Sorry?
No,
No,
continue. It's someone else.
Okay, all right. So let me continue. I think that statement is equivalent to say that unitarity is not conserved. I think it's synonymous. And since, as I claimed, the information loss paradox is not yet resolved. I don't believe that there is a universal agreement on what it really is, and so I can only say that the majority. So this, while science is not done by voting, but the majority is in the belief that in the end of the evaporation, unitarity is preserved, and therefore the CPT violation, etc., must be recovered at the end. I think that's synonymous. But exactly how was what I emphasized is the issue. Yeah, not so much as whether it's preserved. Of course, Bill Unruh may not agree, but yeah, I think majority has that tendency. There's also Avril Srivastava.
Yeah.
Yes, there is also a question from Avril Srivastava. Can you unmute to ask your question? Yeah.
Yeah, thank you for the opportunity, and thank you, Professor Shen, for such an enlightening talk. I have some questions. I would like to begin with this one. Like, we can approximate a black hole as a black body. Is it correct, right?
Could you repeat, please?
Can we approximate a black hole as a black body? So, like, this is actually a linked question.
Got it. No. It's black hole is a solution of general relativity, which is a classical theory. Put into it quantum mechanics or quantum theory, and that's what results in the evaporation. Now, whether this black hole evaporation is truly black body or not so, etc., I think that's the output instead of the input. So you don't start by saying black hole is a black body and then da.
So my question exactly was, like, we know that black holes are emitting in the form of Hawking radiation, right? So since every black hole is described by roughly 3 parameters: mass, charge, and momentum, the angular momentum. So do we expect that the spectrum of the Hawking radiation to be unique? Whether is it the characteristic of a black hole, or or like all of the black holes might have a similar pattern, but it might change with the values of the 3 parameters.
Yeah, good point. I think the famous conclusion of Hawking's original 1974, published in 75 paper was that amazingly, black holes evaporation is in the form of black body radiation, and it recognized that only the mass of the hole, well, assuming that, you know, of course, in his original, and most of us do not care about putting the charge in there, let alone the spinning. Okay, so let's just have a terrestrial black hole with a mass. So this Hawking radiation, as I've shown you in its famous temperature formula, the only attribute of the black hole is its mass. There's no other property. Is that okay?
Let us get maybe another question from Irina Refieva.
Okay, thank you very much for your very interesting talk, very informative talk. In fact, I would like to know what happens in your picture if you take into account the charge of black hole, and if there are some experimental possibility to mimic, for example, extremal black hole. Okay.
Yes. There are tons of papers, and as you can well imagine, extending the original notion to include charge and so on. Now, you can find it from the literature. But I think well, this is only to myself. If one wants to really fight it hard on the issue that on finding the origin of this information paradox, then I personally feel that putting charges on the black hole is unnecessary. It will complicate the issue. So it's kind of a how shall I say, dilute oneself away from the concentration to the attention. This issue is there already, even without charge. Having charge, of course, you will have additional Maxwell, radiations, etc. It may complicate the issue, but here the true problem is where you like to keep track all the, there's so many different concepts of entropy, what exactly that means, and how they evolve. Those things. To me personally, that's the essence. Having or not having charge on the black hole may not help to solve the issue, but perhaps even dilute the issue, divert the issue.
Okay, thank you.
Sure.
Okay, thank you. And I think we have to postpone other questions. There were some questions in the chat. I suggest to postpone this to discussion time. So thank you again, Professor Chen, for your very nice and illuminating talk.
Sure.
And now
I like that.
Yeah.
Please, I'm happy to reply to those questions in the chat box. So while our session is ongoing.
Yes, sure. You're welcome, of course, to chat with people. Sure. And now we move on to the next talk by Leonardo Modesto. Anna, can you stop share the screen, please? Yeah. So Leonardo, can you unmute yourself?
Can you hear me?
Yes, we can hear you. You're here.
And you can also, okay, fine. So let's see if I remember how to use this tool. I just have to share the screen, right?
I hope so.
Oh.
We'll see.
No, what's going on?
Do you also have some security warning?
Oh my God.
Very strange.
Actually, I can say you why do you have it? Because you didn't update Zoom for a long time. Zoom sent email some time ago that unless you update Zoom, you will have some complications about this.
Open system preferences, and then
Anna, but do you also use Mac?
Yes,
So you use Mac and you have no issues.
probably because I
I used
updated.
in the past. Yeah, I used in the past without any issue. I don't know.
Alexei, maybe the speaker can try to share screen during the break. Otherwise, maybe there are
Yes,
some general problems. Yes.
Yes, next time, yes.
Yes, exactly. So, for example, I also would like to try share screen during.
Yes, you can
break.
try, but you have time until Friday. So
Yes, I have, but
you have a bit more time. So Roberto, may I ask you in advance, you also use Mac?
You're talking to me, Alexei?
Yes,
Yes, I also use Mac.
Okay.
Do you want me to try to share it?
Can you try to share screen just in case? I want to be sure that.
Let me see if it works. Can share something. Can you see it?
Yeah, you see, for you it works, okay?
So that's fine. I'll stop sharing right away.
Yes. So I don't know, Leonardo, can we advise you somehow?
Okay.
My suggestion is that either you send file now to me or to Anna, and we do it like with Chen, or I exchange you with Roberta, and Roberta gives talk now, and you update your Zoom in the meantime.
Okay, let's do like that. Maybe it's easier. Okay. Sorry about
to do what?
I prefer to talk to be the next speaker, and now can Roberto.
Roberta, is it okay for you?
Okay, it's okay for me.
Sorry about this, and thank you.
Let
me try to
guess you
share.
have to update Zoom. I think this is, I guess this is the issue.
Okay, let me try to share my presentation then. Let's see.
But sorry, Alexei, maybe some people will come exactly to
that's
some
possible.
particular talk. So maybe change the timetable is not a good idea. Maybe we can wait a couple minutes. Otherwise, maybe somebody especially
this is also
will come to
true.
Roberta talk.
But I don't know how much time Leonardo needs to do this.
I don't know what to do.
Files, just few minutes.
Just try to update Zoom and see if it works. If it doesn't, I can take over. No problem.
Just update.
Let me stop sharing.
Do you suggest just to update Zoom? So
usually that's the problem.
Yes, yes, because it's official notification from Zoom. They dislike programs older than 3 months, let's say. So they really insist you on updating.
So I have to get out right now, because otherwise I leave the
content. Most likely you have to decouple, update, and then connect again with a newer version.
Okay, let's try. Thank you.
Okay, we will wait you for 3-5 minutes.
Okay, fingers crossed.
No, but I think even with time is okay, because soon we will come to already time of Roberta's talk. So it's okay. We're moving on. In the meantime, I suggest that speakers, after they give talks, will send us presentations. If you don't mind, of course, we will upload them to the website. So from Professor Chen, we already have, but others are very welcome to send us presentation files.
So I'm back. Let me see if now it works.
Wait a sec. I have to make you co-host. Without co-host, you will not be able to. It's for sure. So where are you? Are you co-host already?
The same, get the same error.
No, it is not closed yet.
You are not co-host yet. Now you should
Now
be
it
able
is.
to.
Yeah, but I get the same problem somehow. So if open system security and privacy to grant access.
Granted. Give it to Zoom. It should work.
But I don't know what I have to do. Here.
Okay.
You see?
Work.
We got it. Okay. So yeah, so now we see your screen. And we're happy now to start with a second talk by Leonardo Modesto. He will tell us about quantum gravity and quantum cosmology. Please,
Okay.
40 plus 5 minutes, something like this.
Okay. Thank you, Alexei, to invite me again, and to all the other organizers, of course. Okay, so the topic of this talk will be a review of local and non-local gravitational theories and their properties, mainly focused on will focus on unitarity and renormalizability. I will shortly review also how to extend these theories to finite theory, but the main new part is about application and the implications for cosmology. So just to fix the notation and what we mean by renormalizability, let me here present 3 slides about electrodynamics, Fermi theory, and the Einstein-Hilbert theory. So a theory is renormalizable if it looks like in the case of electrodynamics, if at any loop order you get corrections, well, there is no pointer somehow. Do you see any pointer, right? Anyway, so the left slide shows the one loop computation of the amplitude in electrodynamics. This is the vacuum polarization. So it's the correction to the kinetic operator for the photon. So it turns out the divergence is in cutoff scheme quadratic in lambda. And in dimensional regularization, it turns out to be proportional to the box operator. Therefore, actually, the contour term is f squared, which looks exactly equal to the Maxwell action in the classical theory. We can do the same for the self-energy of the electron or for the correction of the vertex. And we always get operators that look like operators present in the theory. If you do the same in Fermi theory, you see that at one loop, you already get an interaction term which involves 2 derivatives, and it is not inside, it is not in the classical theory. At 2 loops, you get 5 derivatives and so on. So this is the main difference between renormalizable theories, and the prototype is electromagnetism. And non-renormalizable theories, again, the prototype for that theories is the Fermi theory. Gravity looks like Fermi theory, and indeed, if you consider one loop corrections, you get divergences proportional in dimensional regularization to p to the 4th, which means in a different invariant scheme, R square operators, Riemann square, Ricci square, or the scalar curvature square. So this term is not present in the action, and at one loop you get this correction. At 2 loops you get other corrections which are cubic, and so on. At any loop order you get new operators, and the theory turns out to be defined for this reason non-renormalizable. So we will focus now the goal is to consider other theories that actually enjoy the renormalizability property like electromagnetism, and hopefully at the same time also will turn out or preserve unitarity. So here is a list of known theories. The first one is Einstein-Hilbert theory that we already discussed it shortly, and particularly discussed its non-renormalizability. We can go beyond to the derivatives and consider the Starobinsky theory, which is so successful in cosmology. It shows 3 degrees of freedom, the graviton, and 1 scalar, and it is ghost-free. However, this theory is not renormalizable, and from the renormalizability point of view, there are more divergences than not in Einstein theory. Indeed, if you consider 1 loop corrections, already at 1 loop, you can get Ricci cube terms, Riemann cube terms, that you don't have in Einstein theory. There is a good candidate to be a theory for quantum gravity, which is Stelle theory, which includes also not only the Starobinsky operator, but Ricci square too. This theory has 8 degrees of freedom, and in the past was known to be sick because of the presence of the ghost. However, in our days, we have new proposals, or a revival of some proposals that somehow solve this problem. And I would claim that this theory, to me, is a good candidate for quantum gravity in our days. The proposals are mainly by Donogh, which is inspired by the Leavitt approach, and or we can deal with the ghost using the Anselmi-Priva prescription at quantum level, but also we can consider PT invariant theories and show that actually the theory, the ghost is harmless, is not a problem in this theory. We can go beyond 2 derivatives and consider n derivative theories, actually 2n plus 4, and this theory turns out to be super normalizable. So if you take capital N large enough, the theory has divergences only at 1 loop. So of course you have in general more ghosts, if you wish, but in our days we think we can deal with these ghosts using the Anselmi-Priva prescription, or considering a subclass of theories that I will tell you something about later, with only complex conjugate ghost pairs. For completeness, here I also list for the last a theory without ghosts, which is at least on Minkowski spacetime, which has which is 4 derivative theory again, but is not normalizable, of course. Okay, so what about non-local theories? Well, the simplest non-local theory that we can consider is this one, in which you have the Einstein theory and the Ricci theory, with in between a form factor depending on the D'Alembertian operator. The reason to introduce this special operator is to, at the same time, achieve supernormalizability, like the Azorey-Lopez-Shapiro theory, and also preserving unitarity without to introduce any other ghost, real or complex. The exponential form factor is as a peculiar, I mean, the class of 4 factors that we have under control have an asymptotic polynomial behavior. So e to the capital H asymptotically, I mean, identically this is an identity, but actually for large zeta or k square, which is what really matters in loop integrals, is polynomial. Therefore, all the theorems about power counting renormalizability applies. Here, the red limit at the bottom of the page shows exactly that limit. You have a polynomial behavior plus exponentially suppressed corrections. So actually, for what about divergences, you can really forget the non-locality and focus on higher derivative theories. So again, now we have to focus. We have to say something about the main properties in order to be a good proposal for quantum gravity, and these properties are unitarity and supernormalizability or renormalizability. So about unitarity, you compute the propagator, and the propagator looks like exactly the one of Einstein-Hilbert up to a follow-up factor e to the minus capital H, which makes the theory much more convergent, like, as I said, higher derivative theories. On the other hand, there is only one pole in K square. The tensor structure is the same of Einstein-Hilbert, and so the unitarity at tree level is guaranteed in Minkowski space-time, which is the only place in which unitarity is defined, up to maybe anti-de Sitter. What about perturbative unitarity? This is a little bit more involved, but not that much, because what we have to do is to define the theory in Euclidean space. And by this, I mean internal energies and external energy. You can take Euclidean, imaginary, purely imaginary, and then you make an analytic continuation of the external energy from imaginary values to real values. Now, the crucial point is that all the singularities in the amplitudes are the same. I mean, all the Landau singularities in the loop amplitudes are the same of the local theory. Therefore, the Katkowski cuts are the same, and unitarity follows by analytic continuation, exactly like in the local theories. Of course, the integration along the imaginary axis and the real axis are not the same, because the form factor diverge in the arc in the first quadrant. But the discontinuity of the amplitude is exactly the same of local theories up to a factor which has no poles and no singularity, the factor B, which takes into account of the extra Eiger derivative or non-local terms. So again, the main point is that the poles are the same and the spectrum is the same of the local theory. So we derived in the past with Fabio, but also other colleagues did in the past, including for the first, probably Efimov, the Katkowski rules, and then unitarity, also including or excluding actually the anomalous threshold from the discontinuity. Let me come back now to local theories and see how the unitarity works there. So the theory that I proposed with Shapiro, with Elia several years ago is 6 derivative theories that can be easily generalized to more higher derivatives theories. And the idea here is to have only complex conjugate pairs. So in this way, the propagator can be written in this fractional rational decomposition, showing explicitly the two contributions of the complex conjugate pairs, complex conjugate ghosts. And since this particular structure, the tree-level unitarity is guaranteed because the two complex conjugate ghosts do not contribute to the imaginary part. Only the real pole, the graviton in this case, contribute. So the idea is in this class of theories to exclude by hand the ghosts from the asymptotic spectrum, complex or in general real ghosts. And then this requirement is preserved at quantum level if a proper prescription is introduced. In this class of theories, it turns out, as shown by my student Jin-Fan Yu, that the complex conjugate poles do not contribute to the imaginary part at any loop order. We did this check for one loop, two loops, etc., for many diagrams. And it's clear the reason why it happens. You need really the complex conjugate poles to be present at the classical level, and these properties guarantee at any loop order. So they do not contribute to the imaginary part at any in any amplitude, so they cannot go on shell ever. Okay, so as long as you remove these states from the spectrum, they cannot be created again in loop amplitudes. is very similar to the VRST ghosts, where in loop diagrams do not contribute because cancel with the longitudinal degree of freedom of the gluons of the Yang-Mills fields, but asymptotically you exclude by hand. Here is very similar, and of course the real part, however, is different from non-local or local theories, as it is evident from the plot of the real part, which shows the threshold at 2m, where m is the mass of a real particle, known ghost particle, while in square root capital M, which is, let's say, the higher derivative scale, there is another cusp which shows the presence of these off-shell ghosts. So they do not appear off-shell, but they can be observed if the amplitude is somehow obtained in any collision. The continuation that here we use is exactly the same introduced with Fabio for non-local theories, but as I said, this continuation is not analytic, and then the non-analyticity is due to the pinching. So the poles of the ghost can coincide according to the external energy, and therefore this is actually the reason of the second threshold in this particular theory. So in this class of theories, we achieve unitarity, and if you have enough higher derivatives, the theory is also super-normalizable. What about real ghosts? About real ghosts, we have to follow, in general, the Anselmi-Piva prescription. The idea is to introduce, even for ghosts, the usual Feynman prescription. You decompose the propagator in the principal value and the delta contribution, and afterwards, this is a recipe, if you wish. You trash away all the delta contribution that involves energies of ghosts. In this case, both the ghosts, omega k, and both the frequencies come from ghosts. Therefore, you have to remove both, and the amplitude to compute is the one involving only the two principal values. If you make this computation, you end up with the log of the absolute value of p squared. Therefore, there is no imaginary contribution. And this works at any loop order in perturbation theory. In short, you could say that if the amplitude, you can get actually the amplitude starting from the Feynman one, in which you have log of p squared, and replacing it with an arithmetic average of m plus m star, which correspond to the continuation from above and below the cut. And the outcome is, as I said, log of p, the absolute value of p squared. So again, the imaginary part does not give any contribution. This is the recipe that you can apply to get physical amplitudes. Okay, let's come back now to normalizability, and this slide can be applied to any theory, local or non-local. Indeed, here we focus on an eigen derivative operator. R can be even the kinetic operator of, the box phi for a scalar field theory, or the Riemann tensor or the Ricci tensor for gravity, etc. So in general, for R, you can think about the equation of motion of the theory, the local theory, that any local theory. So the propagator scales 1 over p to 2 gamma plus d, and the power counting tells us that in order to do not have divergences for L bigger than 1, you need the integer gamma to be bigger than 3 in dimension 4, for example, and that in general depends on the dimension of the space-time. So in general, is easy if you have a theory which is non-local with asymptotic polynomial behavior, or if you have a non-local theory so a local theory with higher derivatives, if you have enough derivatives in all for a gravitational theory main operators, and by this I mean Ricci square and R square, then you can achieve finiteness at any loop order for L bigger than 1. However, for L equal 1, you still have divergences, and therefore you have at most to introduce 4 or 5 counter terms in 5D, the usual one. You can focus on R square and Ricci square. So we can go beyond the renormalizability. The answer is yes, and it's quite easy if you go beyond 4 dimensions, because if you look at the prototype integral for one loop, the one loop prototype integral, since the theory provides only rational integrals, and by rational I mean ratios of polynomials, like in this IKN example, general example. So you see that the divergences usually come from the poles of the gamma functions, the first gamma function. But in odd dimension, since n and k are, as I said, exponents of polynomial and therefore are integer, so you get that the gamma function is never divergent. So is always finite contribution to the amplitude. Therefore, in odd dimension, let's say in 5 dimension, for example, the theory is exactly the same up to finite quantum corrections of the classical one. We can do the same in 4 dimensions, but in this case, we have to introduce other 2 operators at most, quartic in the Ricci scalar. These operators do not contribute to the propagator because they're quartic. And however, they contribute to divergences, exactly to Ricci square and R square divergences, but the beta function are here proportional, linearly proportional to the coefficients S1 and S2. So it's always easy to find a solution of the question beta R square equals 0, beta Ricci square equals 0, and the theory is finite, and this result is one loop exact because you don't get any other divergences in dimensional regularization in any in higher loops. So this theory turns out to be finite as long as you take S1, S2 to have the some specific values. So we can achieve finiteness, and therefore we can think about conformal invariance. Conformal invariance at classical level can be, this is a general class of gravitational theories. So at the classical level can be implemented just replacing the metric with the dilaton square times a new metric. Of course, this combination, this product is invariant under Weil rescalings. And if you make such a replacement in the theory, you end up with a theory which is naively conformal invariant. What is not naive in this in our proposal is that the conformal invariance is preserved at quantum level because there is no, or in other words, there is no Weil conformal anomaly. Indeed, if there are no divergences, when you make the replacement in the quantum effective action, phi square, gh square, you have to properly make such a replacement, and you have to take into account that you are, since you are in dimensional regularization, you have to replace d with d minus epsilon. And the problem, as you can see, for example, the square root of g comes if you have 1 over epsilon in front. But you can read the last line. But if there is no 1 over epsilon, you can take smoothly the limit epsilon to 0, and the operator log phi disappear. So the symmetry is preserved. So in other words, what is crucial for preserving conformal invariance is the finiteness of the theory at quantum level. Of course, you have to get out this regime, and the idea at the moment is to break the symmetry spontaneously. So the scalar field dilaton takes an expectation value, and since you have one more symmetry, which is Weil invariance, the fluctuation is not physical. You can fix even phi equals 0, and the conformal invariant theory, in this case, I just showed Einstein-Hilbert theory turns out to be the usual Einstein-Hilbert theory after the symmetry is spontaneously broken. So the claim is that even Einstein theory is the theory after spontaneous symmetry breaking, coming from a symmetric one, although nobody pay attention to this. And the main reason is because such symmetry is not preserved at quantum level. So even in non-local theories or local theories, we always will have in mind later to fix the symmetry, to break the symmetry spontaneously. So how we introduce matter? Well, here is a very general recipe. So the idea is you have to take your local theories, and you can see there from calligraphic L with index L, and you had an operator which consists on the equations of motion, EI here in short, and a form factor capital F. So EI are the equations of motion for the local theory, and delta is the argument of the form factor F. And by delta here, I mean exactly the Hessian of the local theory. So everything is completely fixed, beside, like usually, the function capital H. That, however, asymptotically must be polynomial in order to have power counting and normalizability. So the main properties of these theories are several, but in first place, if you compute the equations of motion, you see that you get in the black square, the equation of motion of the local theory plus order E squared. And the structure is such that the local equations of motion are contracted with the form factor e to the capital H. Therefore, first of all the solutions of the local theory are solutions also of the non-local theory. And moreover, since the corrections are order E squared, all the perturbative equations of motions are the same of the local theory too. In other words, the stability properties of this theory are the same of the local theory. If you take Einstein-Hilbert plus matter, you have a solution there, and it is a solution also in non-local gravity coupled to matter. Moreover, the stability properties at any perturbative order are the same of the local theory. Here is the proof, but it depends. How much time do I have yet?
I think you have some 10 minutes.
Okay, let's skip this slide. Here I just show that actually the perturbative equation for the non-local equations of motion coming from the non-local equation of motion, the last line, epsilon n, imply that actually this is equivalent to solve the equations of motion for the perturbations of the local theory. So in summarizing the properties of the theory, see in first place that there are all the solutions of Einstein gravity coupled to matter. But of course, this recipe you can also apply to the standard model without matter, for example, and you get an Eiger derivative non-local version of a standard model of particle physics beside gravity. The theory has the same three-level scattering amplitudes of the Einstein-Hilbert theory and the same stability property of the local theory. Moreover, since it is an Eiger derivative theory, we have also Silberg normalizability, and because of non-locality, here I'm focusing mainly on local theories, we have also unitarity because the spectrum is the same of the local theory. That the spectrum is the same of the local theory is easy to see because, as I said, the equations for perturbations are exactly the same, again, last line of the local theory. So there are no other degrees of freedom beside the ones in the local theory. So this theory has many good properties, and the idea now is to apply to cosmology to see what could be the implications for observations. So besides, I like the idea of inflation and especially the Starobinsky theory. Here, I do not have in mind to implement inflation in the model, but really to achieve the observed quantities from quantum gravity, from quantum properties of the theory. So again, here is the third time, maybe I show the action, is in the box, you can see again the theory with the properties. And first of all, we want to implement, since the theory is finite at quantum level, we implement conformal invariance. And that's easy. You have to replace properly any field from the metric to any scalar, fermion, etc., with the proper companion, which is the dilaton. So you have to replace phi with phi over phi, where little phi is the dilaton, and so on and so far. So in the end, the theory turns out to be conformal invariant. This symmetry is preserved also at the quantum level, so we can use this symmetry to eventually do some physics. The scales of the theory. As I said, here there is a form factor which is e to the capital H, and the exponent is and the argument is the Hessian, or if you forget for a moment matter, is a polynomial with the Lambertian operator. So in general, after spontaneous symmetry breaking, because the idea is to break the conformal symmetry spontaneously, you have three scales. One is the Planck mass, one is the non-locality scale, and the coefficient B, or actually the Eiger derivative scale. So what is the idea here? The idea is to have a regime which is the conformal phase, in which the theory is finite and conformal invariant. And this happens when the dilaton value is much higher than the Planck mass. Then, when then there is a phase which is sub-Planckian X phase, in which the value of the dilaton is much smaller than the Planck mass, or smaller order the Planck mass. There, if B is large enough, like 10 or 100, the regime in which you end up after the conformal phase is exactly Eiger derivative theory, four derivative theory, plus quantum corrections that are the usual quantum corrections. So R log box R and Ricci log box Ricci. So again, let me show this picture first. You have this trans-Planckian conformal phase in which the theory is finite, and after spontaneous symmetry breaking, when the dilaton has an expectation value smaller or equal to the Planck mass, you end up in the kind of stellar regime, which is quadratic in R, because E are the equations of motion, and the equations of motion for gravity are G mu nu. So this is actually Einstein tensor square. Is a particular stellar theory, is a stellar theory with particular coefficients, the theory in which you end up, plus quantum row corrections that are these log corrections, and they are crucial. So first of all, what we want to achieve is scale invariance, and that's the reason why we need the stellar theory after the conformal phase, because the propagator is 1 over p to the fourth, and therefore you have a power spectrum which is scale invariant. That's what you need for derivative theory. The second contribution is the quantum contribution that will provide the small deviation from scale invariance. Small because the theory is perturbative. So these corrections, al q, al quantum, should be small respect to the classical contribution. And now I will relate the beta functions to the correction to the scale invariance. What are the approximations? Well, like I said, there is we have to be in the regime after conformal phase in which the theory is Eiger derivative. So the energy scale should be the energy scale of the Eiger derivative theory. Moreover, we would like to make this, we want to be in a perturbative regime. Therefore, the quantum corrections 1 plus Q2 and 1 plus Q0, one is the classical contribution to the propagator, actually to the spin 2 and spin 0 parts of the propagator, and Q 2 and 0 are the quantum corrections, the log corrections. So in order to be trustable, the perturbative theory, you need the log to be smaller than 1. And this happens if the energy scale is above the non-locality scale. So it's about below, sorry, the non-locality scale, lambda star over 10. So all these values are, you cannot change, you cannot take 100. This is the result of the computation. What are epsilon 2 and epsilon 0? Are these two parameters which comes from the quantum corrections, and indeed they are proportional to beta Ricci and beta Ricci plus beta R. They also include this coefficient B and the Planck mass and the non-locality scale. So here we are using the propagator in flat space-time. We need therefore to show that the wavelength is smaller than the Hubble radius, and this is the case. This is the case because in this picture you can see the black line which goes to 0 is the usual solution for a radiation-dominated universe in Einstein theory. The black line that goes towards minus infinity instead is one of the possible solutions in the trans-Planckian conformal phase. We don't know what is the solution there, but for sure any solution there is gauge equivalent. And what is more important is that always the Hubble radius is bigger than the solution, because it is represented in this picture by the straight line, the red straight line, the curved red line. So again, we have these phases, and now we can also get the value of the non-locality scale using our approximations, and it turns out that lambda star, the non-locality scale, has to be smaller than 10 Planck mass. So all the parameters are strictly fixed. So there is not that much room for other values. What about the usual problems of cosmology? Well, all the problems are really solved in once, because the singularity problem is not there, because we have the conformal invariant phase in which any solution, singular solution, is equivalent to flat space-time or any other regular solution like the one showed in the picture. The horizon problem again is solved because A is always smaller than the Hubble radius, and the flatness problem is the one that is solved in the nicer way, because in a theory which is Weil diff invariant, any here is the theorem 2, if you wish, any FRW universe with k equals 0 or plus minus 1 is equivalent to an FRW universe with k equals 0. So actually, k equals 0 and the other values are gauge equivalent. Therefore, it's automatic to select k equals 0. Okay, observables. Well, we said we can use the propagator in flat space-time, and we have it is including the log corrections. So the log correction here in the exponent is this k to 2 epsilon 2. Epsilon 2, as showed before, is related, or is written even here in the corner on the right, to the beta function for the Ricci square term correction. So in the end, you see, you don't have any more scaling invariance, which is represented by 1 over k to the 4th, but you have this 2 epsilon 2 correction. And you can compute the tensor power spectrum and T values, which turns out to be equal to minus epsilon 2. What is important, this value, is to compare such value to the scalar perturbations that also can be computed in the all exactness at the linear level. And you see the second box shows ns minus 1, which is 2 epsilon 2. And the implication or the prediction of the theory is that nt is 1 minus ns, which has to be positive. Last observable, very important, and it is exactly the prediction of this model, is the tensor to scalar ratio. So let's put in the values, what we get. So the two predictions, well, ns minus 1 is not a prediction of the theory. It's something that we take from the observations. Therefore, you get nt1 minus ns as a prediction. Ns is not predicted by the model. So the value of nt is here in the red box, and it's 0.03. While the tensor to scalar ratio is 0.01, and this is not this is a lower bound, cannot be smaller. Okay, so this is 3 times the value of the Swarovski model, and probably can be observed or ruled out in several years, maybe 5 years, I don't know. So the theory is falsifiable. So once again, I want to stress that here there is no inflation, there is only a conformal phase. Afterwards, we have a phase which we could say still with particular coefficients phase. The correction, so the reason why the power spectrum is not really scaling invariant, the reason why we don't have a really scaling invariance is because of the quantum correction. So this is really a quantum gravity prediction, and the quantum gravity prediction is this model is 0.01. So it cannot be 0.001. That's not possible. If so, if the observed value, the theory is ruled out. So that's the main result, or the main prediction. Another one is about the possibility to observe stochastic gravitational wave background. And
Leonardo, it is roughly 40 minutes you spent already.
Okay, I finished. This is my last slide. So it's just to show that Deshigo can be the right observatory to see the stochastic gravitational background. So it's sensible to our prediction, which is the black line. I can stop here. That's my last slide. Okay, thank you.
Okay, thank you very much, Leonardo, for your very dense talk with a lot of problems and conclusions. Questions to Leonardo? So any questions from, I don't know, are there any questions in the chat right now? Okay, if you think whether to raise or not hand, maybe Leonardo, I will ask you a little bit.
Okay.
I got a lot of questions actually, but let me ask some, I don't know, simple maybe. I'm a bit confused when you speak about these complex masses, especially complex conjugate pairs. Maybe this will work around Minkowski space somehow, even though I'm not sure completely. But
I mean, unitarity is defined.
I believe if you go to somewhat curved space, they may not be even complex conjugate. What will you do then?
So first of all, unitarity is defined only around Minkowski spacetime. If you speak about unitarity, if you are instead interested in stability in general, then at classical level you can have other backgrounds that are not stable. It could be. It depends the theory you consider, but if you apply the same recipe I introduced for non-local theories also to the local theories, it should be possible always to end up with equations of motions in which you can factorize these extra poles in front of the equation, the local equations of motion. So the idea is eventually to exclude this instability also around other backgrounds. But unitarity here is guaranteed, and is the only place where we can define in Minkowski spacetime.
Yeah, actually, stability in another issue. This I don't understand, because in class around Minkowski, your complex conjugate pairs, they will have definitely unstable classic trajectories. So it means that you have quantum theory without good classic limit. Is it what you expect?
Okay, so instabilities at classical level here, you trash away by hand. So you take your theory, there is an homogeneous solutions for the equations of motion for the ghost, the complex ghost, and you say it's zero by hand. Why one could buy this proposal? Because at the quantum level, this ghost cannot be created in loop amplitudes. This is the idea.
And
it's
how
like,
does nature know that we have to put it to zero?
We don't know this from nature. We don't observe, if you wish. We don't observe a particle with complex mass, and so you can say, well, as long as we do not observe, well, because there are instability, so you cannot observe. Otherwise, the universe in which you make the measurement doesn't exist, and you cannot make the measure, so you have a paradox. But yes, again, the unitarity is guaranteed in Minkowski space-time.
Yeah, I see what you mean. Also, there is a question from Silvia De Bianchi.
Thank you. Very good.
Do you ask your question? You need to.
Yes, thank you. Could you please go back to the conclusion slide, the one that you couldn't present?
Well, but that actually not a new slide. Sorry.
It's basically the last one. There was one point that
because there are many other things to say and I didn't have time. With this one, you like?
Yeah, exactly. What's about this point that you highlight here, finite entanglement entropy? So what do you mean here?
Okay, so actually you can compute so how you compute the entanglement entropy here? You need to compute the quantum effective action, and you apply the Wilczek procedure. Okay, so so when you have the quantum effective action, you take the derivative of this quantity, and you get the entropy. And this entropy usually is divergent. However, since the theory now is finite at the quantum level, there are no divergent contributions. It turns out that such entanglement entropy is finite without any quantum divergence. And eventually, of course, there are the usual finite corrections. So that's the idea. But
so there are finite corrections, okay?
Yeah, sure. An infinite, yeah. Log.
Okay.
So.
Yeah.
The
okay.
paper about so the claim here is that actually the first contribution is the same proposed by Walt, okay, without any 1 over epsilon divergence, and the reason is because the theory is finite again.
Yeah. Okay. Thank you very much.
Well,
there is a question from Alberto Salvio. Alberto.
Okay. Can you hear me?
Yes.
Thank you. I have a question. So first of all, I agree that unitarity of the S matrix is defined only on flat space-time, but probabilities should be defined for any background. So my question is, are all the probabilities positive, and do they sum up to 1 in this framework? Can one show
I don't
this
know.
for any
I don't know. I don't know. Well, to me, again, the only thing I'm able to investigate here is, the usual S dagger S equal 1, which is defined in Minkowski, right? I don't know how to define the same quantity in a curved space-time. But again, as I said, we can investigate the stability. And in local theories, for sure, stability is guaranteed or not guaranteed according to the result in the local theory, in Einstein theory coupled to matter, for example. Any quantum correction, if it's there, is in perturbative theory perturbative, so cannot destabilize the solution. Theory with complex ghosts or real ghosts in this Anselmi-Piva prescription, you have to trash away by hand at classical and quantum level. I don't know how to define probability in curved space-time, honestly. I'm ignorant, honestly.
Okay.
Well, I see there are many questions. I really suggest to postpone all other questions to the discussion time, because otherwise we will be really... Leonard, are you available for discussion time?
Which time in China?
In China, it should be like 5:15.
Okay, I will be around because I have to teach at 7. So
Yes. So I hope to finish discussion
Thank you.
before around 6. So I suggest to move other questions to discussion time, because otherwise we will be well out of time. And I suggest to move to talk by Roberto now.
Okay, thank you very much. Thank you.
Yeah, thank you, Leonardo, again.
Thanks
for
Sorry
nice
for
talk.
the issue.
Yes, and hope you'll answer all the questions later.
Thank you.
Okay, can you hear me?
Roberto?
Yeah, can you hear me?
Yes.
Yes, it's fine.
No, I think Leonardo should stop
Yes,
sharing,
Leonardo,
otherwise I cannot do mine.
Stop sharing.
Yes. Okay, let's see if it works. Can you see my slide?
Yes.
Can you see the pointer too?
Yes, sure.
Okay.
And so now we are moving to next talk by Roberto Casadio. He will tell us about quantum integrable black holes.
Yes, and I apologize. I might have to cut short at 11 sharp because I had a previous engagement. But anyway, I'll try to be short as usual. I'll try to propose a picture of black holes as truly quantum objects based on some couple of different approaches that lead to similar results. Well, let me skip this part. I think it's not so relevant to give. Everybody thinks, I believe, that quantum gravity has something to do with the Planck scale. And let me just remind you, the Planck scale means Planck length, Planck mass. They can be cooked up by putting together fundamental constants in a certain way to obtain quantities of a certain dimension, mass and length specifically. But behind these two quantities, there are truly dynamical effects. In particular, if you consider that a black hole of the Planck mass has a size that is comparable to its Compton length, the Compton length becomes equal to the Planck length. Then, you know, the Compton length is a dynamical effect, is the dynamics behind which we can locate the particle, for example, by shining light onto it. On the other hand, the gravitational radius that becomes the event horizon has something to do with a very complicated dynamical process, which is called black hole formation or gravitational collapse. So when you put those two quantities equal, the gravitational radius and the Compton length, you are really going deep into the nonlinear quantum dynamics of gravity. And a question you might ask, is quantum gravity really confined at this very short Planck length or very small Planck mass? Now, if you trust the effective field theory approach to gravity, it's a very simple back on the envelope dimensional analysis argument to show that loop corrections, starting from the one loop corrections, always give a contribution to the total action of your system. That is going to be proportional to the Planck length over the typical size of your system to the second power. So unless something strange happens for a macroscopic object, loop corrections are totally irrelevant. But the devil is in the details. What if the background you have chosen has nothing to do with reality? Or if the background cannot be truly described by purely classical physics, which is the assumption we make when you go to the effective field theory of gravity. So I'll present a couple of arguments that do not completely rely on the effective field theory approach, that show that quantum gravity, in fact, could appear a much larger length scale than the Planck length. And I'll do that considering the same problem from two different perspectives. The problem is the gravitational collapse of an astrophysical object, okay? So imagine a star And the only analytical model we have to describe this process is almost 90-year-old, the Oppenheimer-Schneider model of gravitational collapse. When you can make it a little bit more involved with the Tolman generalization, essentially dust. Dust means there's no other interaction in the system but self-gravity. A ball of dust will necessarily collapse, cross its own gravitational radius, become a black hole. Then the theorems of general relativity take over and tells us that the system will end up in a singularity. This is the classical background that one can use, for example, to obtain the Hawking radiation we already have heard about. And the Hawking radiation is a typical effect that you obtain in the effective field theory approach, which for astrophysical object is completely relevant, by the way. It becomes only relevant if you assume that the object continues to evaporate and reaches somehow Planck scale. But we have already heard about the Hawking effect and the problem with information loss. I don't want to go back into that. But I want to just remind everybody the kind of complexity we are dealing with here. A star means a very large object. If you just consider the matter contribution to this system for a solar mass object made just of neutrons, for simplicity, we are talking about 10 to the 57 neutron, order of. This is a number of degrees of freedom in the standard model of particle physics that we have no way to control reliably. I think we can all agree about that. And from this counting, gravity is still missing. If we trust Bekenstein's conjecture, and if you don't want to trust it, I'll show you a couple of arguments that lead to the same counting. But according to Bekenstein, a self-gravitating system of a certain mass involves a number of gravitational excitation that goes like the square of the mass of the object in units of the Planck mass. And here we are talking 10 to the 76. The complete quantum description of this system, therefore, involves something of the order of 10 to the 70-something degrees of freedom for a macroscopic astrophysical black hole. It's clear that there's no hope to describe this in details. We need to go to some simplified model. And that's what I will try to do in the remaining of my presentation. Okay. If there are questions anytime, please don't hesitate to ask. But this is my perspective here. The main issue in describing this problem, the collapse of an astrophysical object, is the complexity due to the large number of degrees of freedom, or excitations, if you prefer, in a theory, which I will take to be general relativity at the classical level, that is nonlinear. And the role of nonlinearity in such a complex system is something that I'm not sure we know exactly how to face. So let's simplify things, try to figure out what the role of nonlinearity is in this problem by going back to the collapsing ball of dust. Now, this is a system that has been studied by many authors in many different fashions. The one I would like to present here is the following. I don't go to the Einstein-Hilbert action, reduce it canonic, and then perform the canonical analysis as usual by assuming that, outside the ball of dust, we have the Schwarzschild metric. Inside the ball of dust, we have a certain different Friedmann-Lemaitre, Robertson-Walker geometry. I'm gonna try to quantize this system by considering that it is in fact made of dust particles, and the surface of this ball, the trajectory of the surface of this ball, can be reconstructed by following dust particles that sit at the surface of the ball, or if you want, in a sort of outermost layer of this ball. And they will follow geodesic essentially in this Schwarzschild geometry if they sit at the surface. You can consider inner layers, and then you have something similar. So that's the geodesic equation. for each single speck of dust that falls along the surface of the ball. You can, in fact, rewrite that in terms of an effective Hamiltonian equation. It's just the Hamiltonian constraint, if you wish, from general relativity point of view, the mass shell condition, the same thing. And of course, each dust particle will carry a fraction of the total mass of the ball, and you can play a little trick and go to some sort of one-body effective Hamiltonian, which you forget about that coefficient, which can be very small, and just look at the ball as a single object and quantize it. And quite funnily, you obtain the same results that you get by instead considering the motion of each dust particle. But for today, I will follow this simpler path. So you can consider any dust particle at the surface. This is the equation of motion. You quantize it a la Schrödinger. And what you obtain is a spectrum of bound states. Of course, this is nothing but the equation, the Schrödinger equation for the hydrogen atom. You just translate the quantities for the hydrogen atom into those for this ball of dust or motion of dust particles in the effective spatial space-time. This spectrum will start from the principal quantum number equal 1. Of course, there's no angular momentum. The dust particles are not allowed to spin around the center because otherwise we would not have a perfectly spherically symmetric system. We don't want that. So there's only one quantum number, and the principal quantum number starts from 1. And you can compute the eigenvalues here, and they start from n, little n equal 1, corresponding to an average size of the ball. Remember, I'm looking at the dust particles at the surface, which can be essentially a tiny fraction of the Planck length. If you look at this equation like you would do in Newtonian physics, essentially you forget about this expression, you just take the eigenvalues to be whatever they are. Now, an object that is a tiny fraction of the Planck length, to me, is a singularity. So in the Newtonian description that you get from this Hamiltonian constraint or from this Schrödinger equation, you recover a slightly smeared version of the classical singularity. However, if you remember that this equation comes in fact from general relativity, and in general relativity, the conserved quantity is this block E here. Block E is the conjugate momentum to time for it, along the motion of each dust particle. Then you would like this quantity to be well defined. And in particular, this means that block E square should be positive. If you impose that condition, then your spectrum does not start from little n equal 1 anymore. There is a minimum principal quantum number, which is given by an expression like that. And only states with larger little n are allowed. Let me call the minimum value then the ground state for each dust particle. And if you simply now multiply this integer times the number of dust particles you have in your ball, what you get is the Bekenstein counting for the mass or area of the black hole. And if you trust the fact that the dust in the ground state must satisfy this condition, and from this minimum value of the now say principal quantum number, you compute the expectation value of the radius of the ball, you get something that is a fraction of the horizon radius. So a macroscopic quantity. And if you trust the model completely, there will be a factor of 3/2 here, but you know, it's dust. I'm not sure you can trust that so much. Now, the fact that the expectation value of the radius is smaller, shorter than the horizon means this ground state is effectively, you can describe it, you can think of it as a black hole. It is inside its own gravitational radius. You have recovered Bekenstein relation, and as a consequence of non-linearity, let me stress the fact that this condition is the only piece of non-linearity that is left of general relativity in this description. If you go back to the Newtonian case, the ground state sits here. It's essentially, again, a singularity. I think this is sort of inspiring. If you think that this result is weird, I can just remind you that in the semi-classical description of the gravitational collapse of a ball of dust, you typically find that the wave packet describing the motion of the surface of the ball undergoes a bounce. And the bounce is what recently Rovelli calls a black hole to white hole transition. And the reason you have a bounce in the semi-classical theory is because you can, according to quantum physics, you can connect the collapsing branch, classical collapsing trajectory, to the classically expanding trajectory. That classically are completely disconnected. One falls into the black hole, the other comes out of a white hole. Quantum mechanically, you can join them together in the picture. But this minimum radius for the ball, like fully, completely collapsed ball of dust, is essentially what you see in this static description of what would be the bounce in the semi-classical dynamical configuration. And again, this is all a consequence of quantum physics and nonlinearity. So this is the first time we recover the Bekenstein-Hawking, Bekenstein area law, or Bekenstein counting of number of gravitational degrees of freedom, gravitational excitations involved in this system. Now, a problem with this picture, if you have questions, please ask anytime. The problem with this description of the ball of dust is that we don't have anymore the geometry. We only quantize the motion of particles. We end up with this finite sized core, and we would like to understand what is the geometry produced by this core. And that's the next topic. As we describe the core as a quantum object, and we'll see more feature of this quantum core later on, we would like to describe the geometry outside this core, at least outside the horizon, where we can see things, can experience things, consistently with what we know works very well from the experimental point of view, which is general relativity. So imagine this core now sits in a sort of semi-realistic universe. We know our present-day universe is quasi de Sitter. So we could reasonably assume that whatever the quantum state of the geometry sourced by this core is, it should closely resemble, let's say, Schwarzschild de Sitter geometry, in which we have the above radius of the present universe and the horizon radius generated locally by our core. This metric is simple enough. We just have essentially one metric function, and I will focus in particular on the local contribution coming from the core that is described by this metric function Vm here, which is essentially almost Newtonian. How do we come up with a quantum state that should describe closely this geometry? Well, again, remember we are considering a core with 10 to the 76 gravitational excitations. It's something that we suspect already is pretty far from the vacuum. We describe this quantum state, or we try to introduce this quantum state, just building an effective quantum theory for that one metric function, sorry, Vm here, or Vm plus V lambda, but V lambda is not the topic of my presentation today. You can find something in that paper. We have one function. Let's keep it simple and use a sort of scalar field. If you want, in the linearized theory of general relativity, this would be the longitudinal mode of the graviton. But we suspect we are going to be very far from the linearized theory. So this is not necessarily the best way to look into it. We assume that this degree of freedom, that again, we need to reproduce that metric. The only one we need to reproduce that metric solves at the fundamental or semi-fundamental level a wave equation for a massless scalar field in a fake, empty, or sort of formal Minkowski space-time. Why am I saying fake, empty? Because the idea is that the vacuum in this theory should represent a geometry, a space-time, a system with nothing in it, pure nothingness. Nothing means no matter that moves, no corresponding gravity that propagates, whatever. So this vacuum here is really something that has no dimensionality, no causal structure. In fact, I would be more than happy to describe it as a Euclidean space. And the number of dimensions also is only fixed here, having in mind that the end result, the quantum state that we want to describe, is 3 + 1 dimensional, but static. So the time is not that relevant. We could start from 10,000 dimensional Minkowski or Euclidean space and just assume that excitation corresponding to the extra dimensions are never produced, never excited. Then we proceed as usual. We know very well how to deal with this simple wave equation, the Klein-Gordon equation for a massless scalar field. We introduce the normal modes, and we assume that the geometry that we see outside the core or in the rest of the universe is described by a coherent state of this metric function, or in other words, of the metric tensor that we are going to reproduce. Coherent states are defined as eigenstates of the annihilation operators, as usual, and we take the expectation value of this scalar function on the coherent state. You get an expression like that, where you have these g of k, which are the unknown quantities in the definition of this spherically symmetric. By the way, we want it to be spherically symmetric for simplicity, because everything is assumed to be so. These are the only unknown quantities that we need to fix. And we want to fix them so that the effective metric that emerges as the expectation value on this coherent state reproduces our chosen metric function via var. Is there a question in the chat? I can't see. Wait, oops, sorry. No, I don't mean to do that. So we will determine the coefficient g of k essentially by choosing a specific geometry or a form of specific geometry. We impose staticity. This is also a little bit of a trick. You know, in reality, nothing is completely static. A key requirement now is that the coherent state as a quantum state must be well defined. And in order to be well defined, it must be normalizable. And it's easy to see that for any coherent state, the normalization coefficient is essentially given by the so-called total occupation number. You can think of those g of k squared as the single mode occupation numbers. So you sum over all of them, that's a total occupation number. It gives you a measure of how far you are from the chosen vacuum. Again, are there questions in the chat, or I see?
No, there are no specific questions now.
Okay. So we need to have a well-defined quantum theory. We need this quantity to be finite. That's the only generic requirement we will impose. Now, let's plug in our chosen metric function. We compute essentially its Fourier transform in spherical symmetry. We plug in the corresponding single mode occupation number. That's what we get. An integral that diverges both in the infrared and in the ultraviolet. In the ultraviolet, we know how to fix things because we know there is a core at the center of our geometry that has a finite size. in fact, of the order of a fraction of the horizon radius. And we can simply use that scale, that length, as to introduce an ultraviolet cutoff and make the integral finite in the ultraviolet. We can also plug in an infrared cutoff because the integral diverges there too. And the motivation for the, this is what we get, but the motivation for the infrared cutoff is given by the fact that we are assuming we live in a quasi-de Sitter universe, and the quasi-de Sitter universe has a size L, which is finite. And in fact, it makes not much sense to assume that the geometry outside our core goes all the way to infinity in a universe that is not infinite. So this is the expression that you get. Fun enough, we recover the usual mass scaling, the Bekenstein mass scaling. M squared is proportional to a constant, as before. This is consistent with the fact that the number of excitations in the system from the matter part and the gravitational part should somehow coincide. One should determine the other. And then there is this function that corrects that counting a little bit, which is due to the these cutoffs. Let me be clear here, we are not matching the interior of the core with this geometry very accurately. By placing sharp cutoffs, we are just approximating things. And if we did things a little bit better, and technically we could, we would have a different function here. But for the purpose of showing the main concept, I think this is plenty enough. Now, plug in the two cutoffs and go back to the metric function at this point. Essentially, this cutoff means we are modifying the occupation numbers in the infrared and in the ultraviolet, because this is what consistency of the theory requires, consistency of the quantum theory requires, and because this is consistent also with the quantum core that we found before. So what you get if you invert your Fourier transform essentially is a different metric function. Metric function which will show slight departures from the expected form that you started from. Do you want to call it this quantum error? You can do that. This is the main source of quantum error, I believe, the fact that you have a core inside the black hole that is not of negligible size. You can do the calculation exactly with sharp cutoffs. I don't know how relevant it is, but this is the picture that you get. We have this, again, Bekenstein scaling for the mass as an integer. The area of the black hole is quantized. This correcting factor, if you consider the core not in its static final configuration, but during the collapse, this is the size of the present day universe, that's a constant, but the radius of your collapsing ball will decrease in time, so this logarithm would increase. This is qualitatively telling you that the collapse proceeds from the point of view of the outer geometry. It's like you are exciting more and more gravitational modes until you get to the maximum number given, which corresponds to the final configuration, static configuration of the core. And then you can also count the typical wavelength of those modes, and you get, of course, the horizon radius. And these are the two corpuscular scaling that Dvali and Gomez produced some years ago. Maybe Gia will talk about that this afternoon, I have no idea. This is a picture. You have the core inside. This is the metric function. The dashed line would be pure Schwarzschild case. This is the horizon. If you trust somehow the sharp cutoff picture, you get this oscillation outside. I wouldn't trust them as a phenomenological fact. If you replace the sharp cutoff with something smoother, you get corrections, but those corrections are not in the form of oscillations. The interesting part is that as long as the core has a finite size, in the center of the system, your metric function will never go to minus infinity, it will always be regular. So the reconstructed quantum metric, which is essentially Schwarzschild with V replaced by this VQM, the quantum corrected metric function, always has a property of representing an integrable singularity. Integrable means that, for example, the Ricci scalar diverges like 1 over r square in the center, but its integral, its volume integral is finite. The same for the square root of the Krashman scalar. And the same for the effective energy density that you can easily recover from the quantum corrected metric. This brings up a picture of quantum black holes in which the effective energy density generically near the center goes like 1 over r square. Now, this would be classically unacceptable, but in a quantum picture is perfectly fine if you recall that the effective energy density of your matter particle, in particular, we have seen dust. Dust particles, the effective energy density of this dust particle is just given by their number times the probability of finding them near the center. And the probability of finding them near the center is a wave function that needs to be normalizable. And again, the condition of normalizability is that this integral then remains finite. You don't have to have an effective energy density that is finite in the center. Just its integral must be. Now, this integral gives you the mass function. And if the energy density goes like 1 over r square, the mass function grows linearly, at least near the center of the system. With this property, and you can also compute the effective pressure, the radial one is essentially the same as you would have in de Sitter, is usually equal to minus the effective energy density. The tangential pressure in the dust model is could be 0, in fact. And in fact, it is 0. In any case, in the more general cases, this is sort of subleading with respect to the energy density, tangential pressure or tension on spheres of constant radius. This is not particularly relevant. Of course, the system is anisotropic. With this mass function, you can try to look and see if there is an inner horizon in the system, a second Cauchy horizon, and the answer is no, provided the coefficient of proportionality here is sufficiently large. Now, let me remind you that horizons are found by zeros of this quantity here, essentially is GRR equals 1 over GRR equals 0. And if the mass function grows linearly, this second term goes to 0 around the origin as fast as the first one. If the coefficient is larger than this quantity around the center is negative, and this prevents from generating a second horizon. What are usually called regular black holes? People assume the energy density, in fact, is a constant in the center, a finite number. Correspondingly, the mass function grows like the volume, like r cube. And now, necessarily, if there is an outer horizon where this function delta goes from positive to negative, the second term here vanishes faster than the first one near the origin. So there's necessarily a region in which this delta is positive again, which means delta from negative must go positive, and then you have the inner horizon. The inner horizon, I think, is a little bit of an issue for many reasons. It denotes, to the very least, some instability in the system. Remember, from an inner horizon, you can only move outward, like from the outer horizon, you can only move inward. So if there's stuff collapsing and falling toward the origin, it must accumulate around here. That sounds quite dangerous for the stability of the entire system. In this quantum integrable black holes, there is no inner horizon, and you can actually remove also the inner horizon from electrically charged black holes. What about rotating case? For the rotating case, a behavior like this is not enough to remove, for example, the inner Cauchy horizon of the Kerr geometry. And the reason is, again, because the zeros or the horizons are found as zeros of this delta here. So if the mass function goes again near the center, like the radial, the areal radius would be in the spherically symmetric case, the second term here near the center is doomed to vanish, like the third one, and you're left with a square. A square is typically in the Kerr geometry the specific angular momentum, the angular momentum per unit mass. This quantity is positive. So again, in zero, this delta is positive, which means if you have an outer horizon where delta goes from positive to negative, then you must have an inner horizon in which delta goes again from negative to positive. This behavior is not enough to remove the central, the interior horizon in a rotating system. However, we have no reason to assume that the specific angular momentum be constant. In fact, if we assume that it goes like r as well, or r as higher power than 1, what we get now is that all of these three terms go to 0 at r equals 0, and you can have a situation like this, in which this delta is positive outside the outer horizon, then it becomes negative, and they all go to 0 together in the origin, and we're basically, it's like saying that the inner horizon is pushed to r equals 0, which, by the way, is no more a singularity. That's enough to ensure that you have no singularity in the center. A behavior like this is sufficient to eliminate the inner horizon as well. So this introduces a quantum scenario for the interior of even rotating black holes, in which the differential rotation and this behavior of the mass function allow to remove this singularity, the inner horizon. They are perfectly compatible with the principle of quantum physics. So I think it is a direction somewhat worth investigating and considering more specific models for the future. If you think that differentially rotating system is strange, well, by differentially rotating here, it means in fact that the specific angular momentum depends on the position. Look at a rigidly rotating sphere in Newtonian physics. You'll see that the specific angular momentum inside the sphere, in fact, goes like r squared, if I'm not mistaken. So it's not strange at all to have a behavior like this. What is strange is that, well, not so strange, in the Kerr geometry, that quantity is constant because it's in the vacuum. But inside the core, made of matter, albeit described by quantum physics, it would not be strange at all to have a behavior like that. Again, with these two prescriptions, you can remove the singularity and the inner horizon. So that's something I would consider quite regular in a sense. And this really concludes my presentation. This is a short summary of what I told you, so I think I can skip it. If there are questions, please go ahead.
Okay, thank you, Roberta, for your very nice talk. And yes, you are perfectly in time. So, questions? Other questions? If you want to ask, yes, there is at least one from Huang Wu. So please. Huang, are you asking a question?
I raised his hand. I cannot hear him speak, so.
Unfortunately, we cannot hear you.
I think he's muted.
Yes, Huang, you are muted. So you have to unmute first.
Okay.
Okay.
Okay. I have question. What is the why quantum hair is correspondent the gravity entanglement always with matter.
I'm sorry, I couldn't hear the question.
The quantum the gravity the entanglement with
Yeah, I think maybe I understand. Typically, people talk about quantum air having in mind an entanglement between gravity and matter. So basically, we are here, right?
Yeah.
We have a large number of standard model particle excitations corresponding. I showed you two arguments to support the Bekenstein counting, okay? So we have a large number of matter particles and a large number of gravitational excitations. They should form together one quantum system, okay? And my point of view is, why would this quantum system separate precisely into something that describes the interior times something that describes the exterior when the black hole forms? This is, for me, probability that this happens is 0. So the two systems will always be connected, if you wish, entangled together. Whatever the quantum state of matter in the core will affect gravity everywhere, including outside. And that's what I would call quantum air. The outer geometry will always know what's inside. Now, can we recover this information? That's where I'm less optimistic, because in the weak field regime, we know the effective field theory works. We don't expect large corrections. We need to go to strong field, let's say, probably near the horizon. Possibility to see something is, I don't know, when the black hole forms, but supernovas are quite a mess, or when the two black holes merge. At that point, it is possible that this quantum picture leads to some different phenomenology, but that has to be investigated. In the weak field regime, I don't think we see anything ever. I'm not very optimistic.
Okay.
Okay. Any other questions? Any questions in the chat? I don't remember.
Somebody raised hands, but I cannot see them. You should be able to see them.
Hi.
So Stravan, yes, Stravan has a question.
Yeah, hello, Roberto. Thanks for the very nice talk. Well, my question is related to S matrix formulation. Can you comment about that? Is there a way to define S matrix so that you can really deal with the, I mean, when the collapse happens, usually you can expect that
for me, no, my opinion is that the S matrix formulation is totally irrelevant for physical purposes. I suppose you have something in mind like the superscattering matrix that Hawking himself introduced, something like that. So you look at the initial state before the black hole forms and the final state when the black hole presumably has evaporated. For me, the interesting things happen in between. And with the scattering matrix, you lose that. I mean, you are taking time to minus infinity and plus infinity, but the interesting stuff from the astrophysical point of view, at least, is in between. And we need a more detailed description of that. So for me, for example, the information loss paradox is a non-issue. If we don't understand what happens to matter when it collapses, all the rest is not interesting. I'm sorry.
Even when the matter is collapsing, you have to deal with how these matter particles are scattering in the gravitational, in a dynamical gravity background, because when the collapse is happening, it's dynamical.
No, actually, that's a problem. In a background, which background?
Well, during the collapse.
Which background? That's the question.
Yeah.
Do you have control on the background? I don't think we have control on the background. That's the main issue.
Yeah, I see. You're right. Yeah.
If you assume a certain background, then you already know the answer you're going to get. But can we trust it? I mean, I think this is one of the few cases in which trusting the effective field theory, having a background and so on and so forth, fully, not saying we have to dispose completely of, because I'm not sure how we can dispose completely of, but trusting it fully. Let me give you an example, very simple. Hydrogen atom. What's the classical background for the hydrogen atom? An electron that spirals into the nucleus. What good is that for the quantum picture? Irrelevant. It's completely wrong.
Mm-hmm.
So if here in the classical description of the collapse, you use some background which is wrong, you're going to get wrong results. How can you tell that?
Of course, you do not know the completely how the collapse is happening until the end of the collapse or until the full formation of the black hole. But maybe up to a certain extent, if you use spherical symmetry, at least during the initial stages of the collapse, perhaps it's possible to assume some background, reasonable one.
Yeah, I showed you what you can get with the dust ball.
Yeah, I see. Yeah.
That's a possibility. I'm not saying that's the final answer. It's a possibility. And I find it curious that you recover the Bekenstein counting so easily. I don't think anybody has noted that before.
Yeah, that's certainly interesting.
Okay, thank you.
Okay, any other questions around? Well, I don't see other questions for the moment, so let us thank Roberta again, and let us move to next talk by Yorgos Karananas.
Hi.
Yes.
You hear me?
Yes, we hear you.
Suppose.
And can you? Yes, now it's better. Okay, so the next talk which we have, it's by Yorgos Karananas. He will tell us about conformal symmetry in the standard model and its symbiosis with gravity. So please, 40 minutes, something like this.
Great. So thank you very much for the invitation and for taking care of everything, the organizers. It's very thoughtful to try to accommodate our requests for when to talk. So what I will discuss today is mostly based on work done with Mikhail Saposnikov, Andrei Skerin, and Sebastian Chell, and as well as various works with Sasha Monin, Javier Rubio, and Volodya Kazakov and Marco Michel. So in case you want to decouple, this is the rough outline of my talk. I'm going to give you a brief introduction and sort of phenomenological motivation on why we should actually care about scale and conformal symmetry when it comes to the standard model, and especially when it comes to combining standard model with gravity, the latter playing a very central role in all these considerations. And after that, I'm going to actually conclude, hopefully on time. Now, it goes without saying that the standard model of particle physics is the success story when it comes to describing the microcosm. The theory is complete now, particle spectrum-wise. The Higgs boson, its last missing piece, was observed more than 10 years ago. And what has not been observed so far, however, are convincing deviations from the theory, at least in particle physics experiments. And also, as is, the standard model may well be a consistent field theory, valid up to rather high energies, at least up to energies where quantum gravity effects kick in. Okay. So it's rather reasonable to wonder whether we have in our hands the final theory of nature. Of course, the answer to this question is well known. It is negative, and the reasons why are actually compelling. First comes experimental point of view. And when we take standard model and put it in whatever gravitational background, being astrophysical or cosmological, we fail to explain well-established observational facts. These are, for instance, associated with neutrino physics, dark matter, baryon asymmetry of the universe, and also the homogeneity and isotropy of the universe at large scales. Now, from the theoretical point of view also, standard model suffers from a number of issues. ranging from detrimental ones, such as the presence of Landau poles, which really pose a threat to self-consistency of the theory. But of course, these take place at very high energies and, are expected to be taken care of in any reasonable theory, combining standard model and gravity. And then there are issues which do not pose a threat to the self-consistency of the theory, but rather are clean-cut indications that we currently do not see the full picture. And these are the so-called fine-tuning issues associated with the incredible smallness of the Higgs mass as compared to the Planck scale, and the incredible smallness of the vacuum energy as compared to the Planck. The hierarchy, cosmological constant issues, respectively. Now, to address especially the hierarchy issue, there have been ingenious proposals over the years. The most popular ones are associated with low energy supersymmetry, compositeness, and large extra dimensions. And the logic of all these approaches is to shield the Higgs from whatever physics lie beyond the standard model by introducing new physics right above the electroweak scale. Now, the fact that the standard model is modified at these energies is what differentiates these proposals significantly from the standard model at energies where, in principle, these new physics are accessible to the current state of particle physics experiments. However, what we have not observed so far, as I've already said, are any convincing deviations from the theory. Now, since the high energy frontier does not, at least so far, give us a hint on where to look, maybe we should take at face value this tendency that nature shows in being scale invariant, okay, and see how far this will take us as far as phenomenology is concerned. Specifically, what I'm talking about is the fact that scale invariance seems to be a recurrent theme, either in gravity or in particle physics point of view. From gravity, or better say in cosmology, when we observe the CMB spectrum, we show that it's to a very good accuracy a scale invariant. And leaving gravity aside and focusing on particle physics sector, we see that the standard model classically, it's actually scale and conformally invariant when the Higgs mass vanishes. Now, the question I would like to answer here, or at least try to formulate in a clean manner and try to answer in the best way that I can, is whether conformal symmetry plays a fundamental role when it comes to standard model and gravity. Now, conformal theories have been and are being extensively studied when it comes to flat space, and we know very well what it means, what it implies for systems that possess it. First of all, it forbids the presence of any dimensional parameters, provided that such systems have a Lagrangian description. And also, the conformal symmetry does not allow for a particle interpretation. On the other hand, nature, and by nature I mean the standard model, has both dimensional parameters and particles in its spectrum. So it certainly appears, at least at first sight, that we may be heading down, a dead end. Okay. Of course, this is a very premature conclusion, and not only premature conclusion is that it's not even complete, because in any event, I need the symmetry to be broken, because the picture I'm trying to paint has to be phenomenologically acceptable, right? As I said, I need to somehow induce dimensional parameters and allow for particle interpretation. And also, I have to introduce gravity in one way or another in order for this picture to be complete. And it's the mere presence of gravity that breaks the symmetry. Now, how gravity enters the game can be done in two ways. Gravity enters the game in two ways. Either in a maximally brute force manner, which I mean that we take conformal standard model, that is standard model with the Higgs mass to 0, and couple it to gravity in a way that scale and conformal transformations are broken completely, or in a maximally consistent with the symmetry manner. And with that, I mean that we take conformal standard model and couple it to gravity either in a way that global or local dilatations are preserved. Okay, let me stress that there is nothing wrong, there is nothing inconsistent with the maximally brute force manner. I'm simply using, this consistent word for a lack of a better alternative. Now, also, what we have to be very careful when it comes to talking about conformal symmetry and gravity. Conformal symmetry in general does not make sense for dynamical backgrounds. And again, in abuse of language, we say conformal and don't differentiate it with Weil, which are actually gauge dilatation. I'm going to be careful here. Now, first, I'm going to discuss the situation where gravity enters in a way that conformal symmetry is completely broken and scale symmetry is completely broken in the gravity sector. And in order to construct the action, we need to establish certain criteria. First of all, I wish only for the masses graviton to be present in the gravitational spectrum. This automatically put constraints on which terms are admissible in the gravitational part of the theory. Specifically, I cannot allow for operators which are of mass dimension greater than 2. So for metric gravity, this would imply only the Ricci scalar and the possible cosmological constant. Now, as I already said, I want conformal standard model, which means that I simply take the standard model Lagrangian with the Higgs mass being equal to 0. And then I'm also going to allow for all possible couplings of matter to gravity, but through portal operators of mass dimension not greater than 4. This is a logical requirement, but can be, of course, relaxed. Now, what I simply presented here is rather straightforward. Okay, so if we take the Higgs field H in the unitary gauge and we follow the rules that I just presented, we get something which is naively simple. Okay, it contains the standard Einstein-Hilbert part, a non-minimal coupling of the Higgs field to gravity, plus the standard kinetic and potential terms. And the dots here stand for the rest of the standard model fields, which are irrelevant for the present discussion. Now, what I wrote down, I must insist, is although it seems very simple, it's a rather non-trivial modification to the dynamics. And this modification kicks in at energies which are relevant for the early universe. Okay? This non-minimal coupling is actually kinetic mixing between the Higgs field and the graviton. Okay? And this modifies, changes the behavior of the field, modifies the behavior of the field when it comes to very high energies, and actually makes inflating with the Higgs field inevitable. And not only makes it inevitable, it makes its success inevitable. And I'm going to explain. As usual, when it comes to this kind of considerations, we need to untangle this mess, this non-canonical kinetic term between gravity and scalar sector, by Weyler scaling. Once we do that, gravity has the standard Einstein-Hilbert form, okay? And the scalar field appears in the action with highly suggestive form. Okay, in order to canonicalize it, we need to employ an exponential map. And once we do that, we realize that what we have, at least at high energies, is something which is exponentially close to exact de Sitter. We get a scalar field which has an exponentially flat potential. And exponentially flat potential is guaranteed to give us the nice plateau that leads to nice inflationary predictions. Now, we can understand the success from symmetry considerations only. What I wrote down, what it's the initial starting point, exhibits some approximate scale symmetry, which of course is broken spontaneously due to the evolution, okay, making the Higgs field the pseudo Nambu-Goldstone mode of the symmetry. Now, being an Ambu-Goldstone mode has a pseudo-Ambu-Goldstone mode translates into the field having an approximate shift symmetry, and an approximate shift symmetry translates into an exponentially flat potential, and exponentially flat potential into excellent agreement with observation. So the only thing I need to care about, vaguely speaking, of course, is the height of the potential, which is controlled by this non-minimal parameter psi that needs to be fixed to a rather large value. And once this is done, I'm guaranteed to get good inflation because the slope is very small. Okay, and of course, the predictions for the amount of gravitational waves produced here is very well within the observational bounds. Now, this is fantastic, okay? And it's so fantastic that there should be a catch somehow, okay? And of course there is a catch, and the catch is associated with the uniqueness of this thing, because so far I have been very vague about gravity enter the game and what sort of particles propagate there and so on. But once we started thinking how gravity enters the game, things change. I have to be a bit more specific here. By gravity, I am not talking about modifying gravity, I'm talking about which variables I should use in order to capture the gravitational interaction, or better say, which formulation of gravity I should use. There is a number of them. There is, for instance, the metric affine gravity, where there is Palatini gravity, there is Einstein-Cartan gravity, teleparallel gravity. And of course, the reason why we usually do not speak and do not distinguish between these guys is because metric gravity, general relativity, is sort of an attractor in this landscape of formulations when matter is absent. So it doesn't matter if I'm going to be discussing spin to field in terms of Einstein-Cartan or Palatini or metric affine, everything is one and the same. Now, in the presence of matter, this changes, okay? Matter matters. And this equivalence between the different formulations is not there anymore. Okay, now in what follows, I'm going to focus on and show what I mean more explicitly in the context of Einstein-Cartan gravity, mostly because it's as close as it gets to the particle physics mindset, and interaction follows from Gates' principle. I don't really care about the details, or I'm not going to enter into into them in this talk. I only need you to understand that when it comes to deviating from general relativity, we simply have more ingredients of geometrical origin at our disposal that should be present in the action. So in the case at hand, apart from curvature tensor that is associated with a connection, we also have torsion, which is associated with a metric, vaguely speaking. Now, imagine I wish to construct a purely gravitational theory that propagates only the massless spin to field in Einstein gravity. So when I only have metric field in my disposal, I can only write. I need to write down two terms: possible cosmological constant plus the Ricci scalar. Now, in Einstein-Cartan gravity, according to the criteria I have established before, I should include 10 terms. Okay, which is rather non-trivial, modification. So I have cosmological constant. I have two scalar curvatures, one parity even, one parity odd. I have two full derivatives of torsion that I may drop, of course, in this consideration, and 5 torsion square terms. Of course, we know very well that appearances here are very deceiving. The connection and, of course, torsion is a non-dynamical field, and this becomes transparent by obtaining what is called the equivalent metric theory. So we practically integrate out the connection. Okay, we vary the action, solve the equation of motion for omega, and we find the well-known result that the connection is the Levi-Civita connection. Okay, related to the derivative of the metric. Once we plug the result back into the action, we of course end up with what we should: a cosmological constant plus the Ricci scalar that depends on the metric. Now, the logic when it comes to matter field, to the presence of matter field, is exactly the same. Of course, we're going to have more ingredients, and what will certainly change are the consequences. Okay, interactions between the matter field change significantly. Now, let's see that. if, again, I use the set of criteria that I established before, I'm going to allow for my fields to interact with gravity in non-minimal manners, specifically for the Higgs. I'm going to have all possible couplings between the field and the curvature, the two curvature scalars, the two derivatives of torsion, and the 5 torsion square terms. The kinetic and potential terms are, of course, unchanged. And also fermions will couple non-minimally to torsion, but okay, we don't care at this stage about that. We're talking about purely graviscalar dynamics. Now, what hasn't changed, of course, is the underlying principle that dictated this nice inflationary behavior. The approximate scale and shift symmetry. Again, for large field values, the theory exhibits approximate scale symmetry, but now this the slope of the potential is a function of all the non-minimal couplings that are present in the theory. Now, since the slope becomes practically a free parameter, so does the production of gravitational wave. And then the picture I showed before in such considerations is modified as follows. So here is metric Higgs inflation, whereas in the when the gravity paradigm is modified, we can have much more liberty when it comes to producing primordial gravitational waves. And we can, of course, use future experiments probably will give us some insight on that. Now, so far so good. Let's try to understand how a fully scale invariant universe will look like. And things will become even more interesting here. Let me note, it's important that what I've said so far, although conformality was broken in a brute force manner, the statements are more or less applicable to the symmetry consistent manner too. Okay, so now let's focus on the scalar Weyl symmetric considerations. Now, first of all, it's clear that I should liberate the action from any explicit mass scale. So I should put, apart from the Higgs mass to 0, also the Planck scale to 0. So in other words, in the context again of Einstein-Cartan gravity, again, generalizations are pretty much straightforward, even for metric affine gravity. Of course, I'm going to have more ingredients, but the logic is the same. So I'm going to have interaction of the Higgs field with the curvature scalars, interaction with the torsion derivatives, interaction with torsion square terms, and so on. Now, what I've managed to do here is I ruined standard model phenomenology and early universe dynamics in one try, okay? Because what I wrote here is literally the induced gravity, how induced gravity looks like in Einstein-Cartan context, okay? So, again, we untangle the mess by finding the equivalent metric theory. So, integrate out the connection. Of course, it's still non-dynamical. And also, apart from the fact, the part containing derivatives of the metric, it will also contain derivative of the field. Okay. So once we do that and move to the Einstein frame by reading of the non-minimal couplings, we end up with a minimally coupled scalar field, which is massless and interacts with matter only derivatively and gravitationally. And of course, this is expected because what I have here is exact scale symmetry broken spontaneously, meaning that the Higgs is now the exact Nambu-Goldstone mode of my broken dilatations, and thus cannot be the standard model Higgs. It does not interact with the matter sector in an explicit manner, or does not have a potential, right? It's completely constant. Now, what we learn from this exercise is that a viable embedding of the conformal standard model into a fully scale invariant framework requires the introduction of an extra scalar mode. And this is what we usually call the dilaton, that now assumes the role of the scale donor. The Planck mass is generated via spontaneous breaking of the symmetry and then communicated to the particle physics sector via interactions with the dilaton. Now, apart from that, apart from being the scale donor, the dilaton can also have an important role in the late universe by being responsible for the present-day accelerated expansion. Now, this is very, very important because in such considerations, in spontaneously broken conformal theories, one cannot have non-vanishing vacuum energy, okay? The potential when evolving along a flat direction where the symmetry is non-linearly realized, it's automatically zero, okay? Although it sort of appears as a non-trivial statement, it literally follows from dimensional analysis. Conformal symmetry fixes the potential to be homogeneous function of the field, meaning that it's related to the derivative of the field. Now, for spontaneous symmetry breaking, we need to have the derivative of the potential to be equal to zero for a non-vanishing expectation value for the field, meaning that the potential itself vanishes. Now, you're going to ask me, how general is that? And I'm going to answer quite frankly that the situation is rather complicated because in all the simple examples, flat directions only appear at specific choices of couplings, and this yet again requires some tuning of parameters, some fine tuning. Okay, so the cosmological constant issue, at least in the simplest considerations, is not addressed in this context. Of course, it's put in a different context, provided that we find flat directions, symmetry breaking solutions that exist naturally without tuning. I only know of one non-supersymmetric example where this is the case in 4 dimensions. It's not general. Anyway, having dealt with late universe, let's try to understand whether we ruined early universe because of introducing yet another field. You can imagine that inflationary epoch may be affected non-trivially and have multi-field effects kicking in. Fortunately, this is not the case, and the inflationary dynamics, at least in a rather wide class of models, is universal. The predictions are universal and rather independent of the details of the theory. And we really get Higgs inflation, practically single field dynamics. Okay, now the key point there is that conformal symmetry in the multi-field consideration, the 2-field considerations that I'm talking about here, fixes the curvature of the manifold associated with field space curvature, the mixing between the fields. You understand that once I start coupling scalar fields to curvature, I am also coupling them. I'm coupling the fields between themselves, and this, in general, can result into rather non-trivial modifications. Fortunately, here, by assuming conformal symmetry, completely fixes the curvature of this manifold and actually makes it to coincide with this control parameter kappa that we saw before, that also controls the slope. So also in this Higgs-Dilaton context, the predictions are indistinguishable, more or less, from Higgs inflation, from the single field considerations. And actually, they give a neat connection between field space geometry and inflationary observables. Now, it may well be the case that you feel somehow uneasy that I introduced yet another scalar field in the game. Okay, although, as I already said, this may play an interesting role for the late universe. You may also feel even more uneasy because I'm working with action that contains that many terms, even though there is this class of universality built in. And okay, you have to understand that such multi-parameter theories are very common when deviating from Einstein's theory of gravity. Okay, now turns out that I can also I can constrain things and reduce the number of admissible terms, and at the same time get rid of the dilaton by making it a spurious field. And the way to do that is to use to assume that the theory is while invariant. So use this while redundancy as a sort of a bookkeeping device. Okay. In this way, I'm gonna make sure that the gravitational and the scalar sector only propagate the massless graviton in one scalar field, as I started before. Now, this is a rather unique situation, right? Because when we are gauging, we usually bring in new degrees of freedom, okay? But not here. Here, what we have is a non-trivial aftermath of the fact that whenever the metric gets rescaled by conformal factor which depends on the space-time coordinates. The geometric data also transforms non-trivially, okay? And specifically, they pick up in homogeneous species. For instance, the scalar curvature in the metrical, the rich scalar shifts by the derivative of the conformal factor, okay? And this is what enables it to actually play the role of the corresponding gauge field. Look, I'm not saying something very deep here. We all know this, important example of conformally coupled scalar field, right? In the standard metric gravity. So this guy, the action I've written here, we know very well that it's Einstein gravity in disguise, okay? We have Weyl invariance without introducing any ad hoc propagating degrees of freedom. Now, in Einstein-Cartan gravity, the situation is a bit different and it's also rather interesting, okay? The curvature, being a function of the connection, is inert under Weyler scaling, but one of the torsion contractions, one of the torsion fields, say here V mu because it's called the torsion vector, it transforms homogeneously. And actually, it's the Weyl vector in disguise. This thing, so we can use it to construct invariant objects, covariant derivatives. Now, very, very similar considerations apply if instead of torsion I have non-metricity. Now, it's the non-metricity, one of the non-metricity components that play the role of the Weyl field, and this was understood by Gilense and collaborators some years ago. Oops. Now, in the inflationary dynamics in this specific situation is genuinely single field. Okay. Now, the graviscalar incarnation of this Weyl invariant Higgs-Dilaton model would look something like that. Would only involve H field, its potential, and the rather non-trivial function modifying the kinetic term of the field. This is again, I would say, quite common characteristic of these scalar tensor theories. It's much more constrained as compared to the standard Higgs-Dilaton theory, but there is still enough freedom to get satisfactory phenomenology. If, for instance, I take a specific limit where all non-minimal interactions vanish and only the ones with the scalar curvature are kept, then I get this function being inversely proportional to the field square, which again yields this nice exponentially flat plateau that we saw before. This is literally, indistinguishable completely from single field considerations, and is expected, of course. So, and actually this brings me to my conclusion. I believe on time as well. And sorry? Is someone asking something? I can't, someone seems to be. Yeah, so I'm in my conclusions. So what I talked about here today is how conformal symmetry may be important for a harmonic symbiosis of gravity and the standard model of particle physics. Now, if inflation is responsible for making the universe isotropic and homogeneous at large scales, then it's the Higgs field that is responsible for inflation in this context. Gravity, as I showed, is very, very important. It has a very central role because it's responsible for breaking the conformal symmetry. And this can be done either in a, again, maximally brute force manner or in a symmetry consistent manner with important implications in each case. I confined myself to considerations associated with Einstein-Cartan gravity, but this is generalized also to other frameworks. And I also argued that having scale or Weyl invariance when it comes to combining standard model gravity may offer us some insights on the cosmological constant problem, although we are not there yet. Thank you for your attention. Thank you.
Okay, thank you very much. So, questions to Yorgos? There is a question from Sergey Vernov.
Okay.
Sergey, please.
My question is about possibility to add R-square term in your model, how it is connected R-square Higgs gravity with model that you consider.
Sure, I will tell you. So it depends what you mean by R-square. Do you mean scalar curvature square or Riemann square? Scalar curvature square.
Maybe in
Sorry?
Maybe in Palatini formalism, maybe in metric form, it is not.
No, you see, this is important, and also this is very important because if I start introducing R-square terms in general, curvature square terms, I'm going to introduce new degrees of freedom, like for instance happens in Starobinsky theory, and this contradicts one of my starting points, that I want my gravity sector to only propagate a massless spin-to field. Now, in Palatini formulation or Einstein-Cartan formulation, there exists a unique modification with curvature square terms that doesn't bring in any new degrees of freedom, okay? But this is not the general case, okay? In general, higher curvature terms bring extra degrees of freedom, and I'd rather refrain from doing that. Again, very few exceptions. It may be very interesting, for instance, from phenomenology point of view, instead of having the Higgs field inflate the universe, to put R plus R square in a metric case, or the other curvature invariance in the context of Einstein-Cartan gravity, this pseudo-scalar curvature, R plus R square, to have pseudo-scalaron inflating the universe. These have all been studied extensively in the literature. But in my consideration, these terms are not admissible. Okay. R square in general are not there.
Thank you.
Okay, there is a question from Sravan.
Hi, Georgios. Thanks for the very nice talk. So first, I have a comment and a question. Comment is, well, it's especially with respect to scale invariance. If you take R plus R square gravity, R square term is nearly scale invariant and it is dominant during inflation. So it is a perfect example. Of course, Higgs, I agree with your conclusion that Higgs is a interesting inflationary model, but R plus R square also belong to the same category with respect to scale invariance. This is
couldn't agree more. I completely agree, because this is why Starobinsky inflation is so successful, because you have R plus R square for energies relevant for inflation. R square dominates over R, and you get this exponentially nice plateau for the scalar. It's exactly the same logic behind. The principle is there.
Yes. So it's great that you also agree with this. And my question is about, well, the generalization of the Higgs model, with including the torsion. It gives different predictions for tensor to scalar ratio, as you've shown. But surely there are several class of models like alpha attractors and all. So then it comes real big problem how to distinguish these models. So but at least in your case, you have torsion. I am curious if you can say something about cosmological imprints of torsion, at least in CMB, for example. Do you expect anything, or is there a way to compute something in this model?
Okay, in this specific situation that we have here, torsion is non-dynamical. Okay, torsion is responsible for sourcing interaction between the fields. So it provides sort of, again, some selection rules for how the scalar fields or the fermions should behave. It may not be enough to look at inflationary dynamics to say, distinguish between Einstein-Cartan modification or non-metricity or alpha attractors and whatever. But for sure, Einstein-Cartan gravity, especially in this context, also has important implication when it comes to fermions, okay? Because it makes them interact in non-trivial manners, especially neutrinos and so on. And this has been studied and provides yet another way to understand whether this is something realized in nature, okay? So that's where I would look, in fermionic interactions, to be 100% sure.
But do you expect some signatures in the CMB
no,
with
because this is
higher order correlations?
No, because this is, again, it's indistinguishable from metric theories. Torsion is not dynamical. Torsion is a smart way of writing down specific modifications to kinetic terms and potential, to the kinetic term of the fields, just like non-minimal coupling to Ricci scale and metric considerations, a smart way to writing a non-trivial modification to the kinetic term of the Higgs field. It's exactly the same logic, more ingredient.
I understand. Thank you.
Sure.
Okay, and a question from Anna Tokareva.
Hi, Yorgos. Thank you for a very nice talk. You mentioned some models relying on Weyl invariance,
Yes.
like for the Weyl gauge symmetry, like proposals from Dimitru Gilencia and so on. What is the role of Weyl anomaly? I mentioned this problem because it seems to be very difficult to get rid of this anomaly, especially from the A anomaly term. And it seems that this model you rely on the precise gauge invariance. Otherwise, it's some strange theory if you don't have this.
No, I understand. But first of all, I was talking about only classical physics, right? And let alone, I was only talking about Weyl invariance as means to constrain the theory, right? So about the Weyl anomaly, I don't think I have to say much, especially in view of the fact that we don't even know how to compute it when it comes to the presence of torsion. Okay, it's not clear. At least that's my understanding. And at this stage, it's simply a bookkeeping device.
Can you just go to metric formulation from Palatini or torsion formulation and do everything in metric formulation?
This one? You mean?
Maybe I'm wrong, but I had an impression that all these non-metric formulations of gravity can be written in open sum field redefinition can be written in metric formula.
Yeah, exactly, but that's the game I'm playing here always, right? But these are classical considerations. Okay, I'm sort of assuming that torsion doesn't make any non-trivial contribution when it comes to quantum physics, and especially for the Weyl anomaly, having the Weyl vector being associated with torsion, it's not clear to me how to proceed here. Okay, so I don't have much to say about the Weyl anomaly apart from that it's there, obviously, should be there, and yeah, apart from a bookkeeping device at this stage, I'm not sure what is the physical significance of the Weyl symmetry, the Weyl redundancy. Okay.
Yeah, I see. Okay, so it's a good open problem.
I wouldn't give it some physical significance, at least at this stage, without understanding more in details what happens here.
Okay, thank you.
Sure.
Okay, I don't see any other questions right now, so I suggest to thank you, Yorgos, once again for your very interesting talk. And now we're coming to discussion time, so that everyone is welcome to ask questions to speakers. As far as I see, Pisin-Chen, Leonardo, Modesto, and Yorgos are around, so your questions and comments are welcome, so please.
I have a question to Pisin-Chen, so maybe can I ask? Yeah.
Yes, just a second.
So, hi, Pisin. So basically, my question is related to, as you mentioned in your talk, especially related to the page curve. The page paper is completely based on the quantum mechanical, gravity is not involved there. And then you showed your paper where you did the calculation with gravitational path integral. So you kind of saying that gravity is special and black holes cannot be treated as ordinary quantum system, which is against the so-called central dogma. Am I correct?
Okay, I didn't know that there is a dogma. But okay. I do agree that black hole is a very special species. It is it is not a pure quantum object. Well, we already knew for almost a century. This is a solution of the classical general relativity. Now, of course, we also believe that quantum mechanics is everywhere, and so there must be, a future complete description of the black hole that can satisfy both quantum field theory and general relativity. But before that time, I'm not sure how to describe it in an exact way. All what we have been doing now are an approximation to the true. Now, of course, different people have different beliefs, but one thing for sure is there is indeed a classical limit of the black holes, including the Nobel Prize winning gravitational waves or galactic central black holes. Those were extremely classical, I mean, in the Hawking sense. So any successful theory must promise to recover the GR predictions. I think that's to say the least. Now, the other extreme, when you are in the quantum limit at the Planck scales, etc., how you describe it well is a separate issue, and different people have different views. Of course, I have my own, but so yeah, not sure if my response to you is relevant to your question at all.
Yeah, it's true. Yeah, I also have the same opinion, but just want to confirm my understanding. Well, the central dogma is exactly the word used in this paper by Almheri, Maldacena, Polshinsky, and Sully, the paper you also mentioned in your talk. So basically, black holes are not the standard ordinary quantum systems. Then my immediate question is, how can we, because in the analog black hole experimental setup, there is no gravity. Then how do we understand from the analog experiments about something that has no gravity? I mean, sorry, we want to understand gravitational systems. Okay, so how analog experiments help us? There is no gravity there.
Right. Now, I think you're really pointing to a very important challenge. Now, so being in the laboratory and which is flat space-time, any analog system cannot 100% reproduce the gravity effect. And so when we say analog, like in fact, not only the analog black hole systems, many other physical systems in the past centuries, have similar analog systems. But I think the argument for such analog systems is that knowingly that being analog is not identical to the real system, but then it depends on the smartness of the people who invent or come up with the analog system, whether that analog system is capable of capturing the essential features, the core feature of that of that issue under discussion. So in the case of the Hawking evaporation, what really is that part? That's debatable, but I think many probably would agree that the essential feature is the entanglement between the Hawking particle and its partner. At least I think that was what Frank Wilczek insisted and convinced many in his 1987 work, which to me, I think was what
truly truly inspirational. And so I think for those who are interested in searching for analog black hole to hopefully shed some light, I think that's the right word to say, just to shed some light. You're not, you shouldn't claim, and I think that's totally false, to argue that analog black hole is going to solve the problem. I think we should still, where our theorists at, to look into the intricacies of this problem, and then some other guys, or just the same people, who are able to see through it and say, this piece of the entire argument is the essence. And if we are able to find an analog system to investigate this part, to confirm, this must be true, and so on, then I think we have we're doing some service contributions to this entire debate. So that's, I think, how I see analog black holes in its position in this entire game.
Okay. Thank you. And also, it seems like we have another question from Abrazio.
Thank you. My question is for Professor Shen.
Okay.
So, in your talk, you mentioned that you were trying to address the information paradox through the Euclidean path integrals. And I looked through the paper and I saw the use of the canonical gravity. But like Hawking in its paper has explicitly mentioned that like when a is considered for a black hole, then it won't be under equilibrium conditions because of its negative heat capacity. And that forces us to use the microcanonical ensemble for the discussion. So like how do you go about this? Like
well, right, yeah. Actually, you know what? It is you're very right in that this whole thing about the Hawking effect indeed is not under equilibrium, and so it is a how should I say? One should keep this in mind when discuss things. And luckily, when you if you handle the evolution of entropy through the variation of the actions and so on, I think you can handle it properly, and that's what people have been doing, including myself. So in that particular regard, I'm not inventing anything new. This has been what's been doing all the time. Not sure if this address your question at all.
So that means that we're not under equilibrium conditions. So that means
right.
the system
Actually,
is not under equilibrium conditions. That what you're right.
Yeah, okay. So I guess what I was saying was, say, take for example our approach using this Euclidean path integral. There's no notion of equilibrium involved.
So this means that the black hole doesn't has to be associated with any matter surrounded, like no accretion days. It could be possibly isolated system, we can say.
Right. So as typical, the setting was the whole universe is nothing but this one black hole there. So, but you do need to have a mass, and whatever it was the origin. Just now in my talk, I mentioned gravitational collapse. Let's say that's the case. But since there's a collapse and there's there must be a singularity, that there is a location. I mean, but I think other than that, you don't assume there's any other material other than, of course, later on or as time goes, this black hole evaporates into radiations or whatever kind of particles. But indeed, we and like anybody, many others, well, vibration it has many different senses, but here I'm saying that you don't worry about the radiation, Hawking radiation re-emerged into the black hole and things like that, accretion, etc. In that regard, but the Euclidean path integral formulation being by nature non-perturbative, it can handle. In this sense, I'm sorry that I used this word, which is rather easily misleading. This word back reaction, but indeed, what happens when the black hole evaporates to the late stage is where your temperature keeps going higher, right? And the emitted quanta can easily take away a major fraction of the existing black hole mass. So the delta M over M is not going to be much less than 1 anymore. And so there, our standard semi-classical treatment to the black hole evaporation, including what Hawking did in his original paper, ceased to be valid. And so that's why I think that the Euclidean path integral approach can do something good to allow for these, this instant tunnelings and so on is already beyond perturbation. And so we thought there may lie some hope for addressing the final state. That said, however, I must also emphasize that, at first thought you say, well, your modified page time seems to be moving so much towards the end time. Well, sorry about this. Just a second, So sorry. So I'm just saying that when you check, you found that actually the page time, even with a very large black hole, is still many Planck scale away, and so it's the semi-classical, meaning not truly quantum gravity approach, such as Euclidean path integral, should still be valid.
Thank you, sir.
Sure.
Okay.
So,
Question from Huang.
In information paradox, after base time, the entropy of Hawking radiation is decreased. Why?
Well, not the entropy, the entanglement entropy decreases.
Yeah.
Right. Yeah. The Hawking, the radiation, the thermal entropy, the Boltzmann entropy of the Hawking radiation still increases. It's the entanglement entropy that decreases. And it's not hard to imagine intuitively. Let's go back to the canonical page curve. You imagine the following: when half of your black hole original mass is now turning into radiation. So therefore, half of the matter is now in your system B, and the other half, the remainder of the black hole, is still in system A. Now, the entanglement entropy, which deals with the entanglement between the Hawking particles and their partners. The partner particles are trapped from an observer at infinity. It's almost infinitely slowed down and trapped to the surface at the surface of the black hole, and so that's part of system A. So system A, system B, and reaches a maximum. You have half and half, but when you have less and less black hole mass, when you keep evaporating, even though your radiation gets more and more, but the entanglement goes down. Can you imagine that? Yeah.
Okay.
Okay. Mm-hmm. Come in.
We have some question in Zoom chat.
Zoom. Yes, indeed, there is a question which asks, but it's question to whom? This is a good question. I think to Professor Chen. Pisin, can you read the chat or should I read it for you?
Let's see. Chat. When you said before that due to mass we have this information, is there any particular analytical way of saying that only mass is responsible for this information? I think so. I think so.
And the same participant was asking the question after the talk, which is this information related to the space-time metric? If yes, then how would it behave in the Kerr space-time metric? It was asked during the presentation, so I think.
Sorry. So let me search because I did not hear the entirety of the question. Is this question from? Okay, I do have one question. Is this related to the space-time metric? If yes, come in. If yes, then how would it behave in the Kerr space-time metric? Related to that. Yeah. Yes, indeed. People also look into the to the information issue based on Kerr space-time. Yeah, you can go check, and there's this thing. And if yes, then how would it behave? I hear some voice. Anybody saying something? Okay. So if not, then let me just
some
say.
random noise over.
Oh, okay. Yeah. No. Yeah, it does depend on the space-time metric, but not in the fundamental way. It may give you some, slight change of things, but not in the fundamental way. This whole business has to do with the existence of the horizon, and either Schwarzschild or Kerr or whatever. As long as you have a horizon that partition this universe into two subsystems, then you will have this paradox, this issue. And so in that sense, this my analog black hole experiment is indeed just trying to create an artificial, or let's say analog horizon in the laboratory.
Well, I don't see any other direct question. Maybe I will ask something to Leonardo. Leonardo, do you hear me?
Yes, I can. I can.
I want to ask you something because it was already too many questions after your talk. But I'm still confused a little bit with what you are saying. You are saying me that in your approach, you want to say that all these extra degrees of freedom with complex masses, or simply extra degrees of freedom, you want to put some, technically speaking, you want to put initial conditions to be 0. You don't want to see the degrees of freedom. In Young-Mills, I understand how do I do it for Fadeev-Popov ghosts. I really do prove that these degrees of freedom don't appear in the spectrum, I mean, in external lines. And this was done. This is why these ghosts are so much powerful. But here I cannot do it. I only can say that I put initial conditions by hand. Do you think it's possible somehow to still improve what we are doing about this non-local Lagrangian so that it indeed doesn't appear in external lines?
Yeah, so I mean, your question is a good question because as far as we know, as far as we do right now, me or even especially Anselmi and Piva, they really exclude by hands these degrees of freedom, ghost degrees of freedom, all stabilities from the spectrum. I mean, this is when I said it's similar to what we have in Young-Mills theory, I use the right words. It's similar. It's not exactly the same because in Young-Mills theory you have gauge invariance which removes the extra degrees of freedom. Okay. However, in loops, ghosts really make the same job, so they cancel the longitudinal degrees of freedom in loops. Here in loops, we use a prescription which preserves the spectrum somehow. So this is the state of the art. At the moment, I would say this theory, like this stellar theory or higher derivative theories, but local, are mathematically, I would say, consistent. Okay, you can like, maybe you don't like. That's a matter of taste. But we can do better. I don't know. I'm tried. I think you also tried somehow with this idea of ghost confinement. And Hold also did several very nice papers about the idea. The idea is very exciting, very nice. There are many similarities with confinement, but honestly, I wrote in the paper about complex ghosts. I wrote a section about that, but I removed afterwards before to submit the paper because still I don't know. I don't know if it's possible, but it's very appealing. It's very appealing idea. Actually, very old because even in Mikio Kako book on M theory there is this idea about stateless theory. So yeah, I think maybe we can do better. Maybe we can do better. Maybe we can prove one day that these guys are really confined, but while real particles are not. But even when I spoke with this with Frasca and others, we don't know yet, right? We don't know how to deal with this.
Yeah, I know that we don't know. So I was asking, maybe you already got an idea about this. Because you see, there is some discrepancy. We know how it works in Young-Mills, but here there is something, not like cheating, but a little bit hand-waving, that we need to put it by hand. So this was my question, how nature does know that we have to put it by hand?
I don't know how nature knows. I don't know. In the sense that, I mean, we don't observe, and as long as we do not observe, we can say do not exist, and we exclude by hand. I mean, it's just an hypothesis, by hypothesis. I mean, I would say. But you're right. The research topic you started is very interesting, in my opinion. Although, as I said, I wrote a couple of pages with Gianluca and then we removed afterwards because it was too much speculative and there were some discrepancies between what we do and what is usually done Yang-Mills theory or toy models for Yang-Mills theory.
I see.
So, yeah, but anyways, I mean, it's better than in the last century, because now at least we have several proposals to make the theory consistent, even Stella's theory. I mean,
yeah,
opinion.
It looks like Shravan in the line. The
Hi,
question.
yeah, I have a question to Leonardo, but in a completely different direction, not about the ghosts. In the alternative picture of inflation you have presented, I'm curious how, I mean, in the context of inflation, if you take Stravinsky inflation or any single field inflation, NS is related to number of E-folds of expansion during inflation. I didn't get it. In your case, NS is related to what? It should somehow,
NS?
what background is what? What is the background expansion you have?
Actually, the computation is done in Minkowski in the ground. And in order to get this power spectrum, we use the 2-point function for the propagator. Mainly, the whole computation is the 2-point function of the propagator. But of course, we try to justify why we can use that approximation and where the correction comes. So you have as long as you accept that there is a phase which is quadratic gravity, you already have a nice result. Actually, let me mention Reuter and Bonanno and Mottola and Antoniadis. They did very similar things. They were very inspiring for me. So in this, if the theory is quadratic, the propagator is 1 over p to the 4th, not 1 over p squared. And this is enough to get scale invariant spectrum. Of course, you also have to prove that the Hubble radius is larger than the A of t, no? In order to make consistent the approximation of flat space-time. So this is the approximation. Then, how you get quasi-scale invariant, and then how NS comes out non equal to 1. Because of the quantum correction. So the propagator is not exactly 1 over p to the 4th, but is 1 over p to the power 4 plus a little number, which is related to the quantum corrections, to the log quantum correction, which is always there in higher derivative theories in quadratic gravity. So that's the story. So you have a theory which intrinsically, since it's quadratic, gives you scale invariance. Then the quantum correction gives you the little deviation to the scale invariance that you need. And it's very quantum. It's like I would say the lump shift in electrodynamics, although in the infrared in that case, or G-2. So it's very, to me, the picture is quite clear, but it's alternative, of course. And it's a very quantum gravity, deep quantum gravity prediction as far as we know. I mean, we check the computations need and
yeah, but I'm curious, since as you mentioned Hubble parameter. So what is the Hubble parameter you have in this during this phase? I don't know, because it is alternative expansion to inflation, right? It's not exponential expansion or quasi-distributed expansion. Then what do you have?
So you can add anything in general because you are in a conformal phase, no? So you can have the FRW solution, but you can get any other solution, exact solution, which is a rescaling of FRW. So you can have even an inflationary phase there. But all in this regime, it's not important which kind of metric you have. The meaning of conformal invariance is that there is no small, there is no large distance. Everything, there is no notion of space-time distance. And that's the reason why you solve these usual issues of standard cosmology. It's more symmetric solution than not related to a particular metric like in inflation. Of course, in the paper, you can find several examples.
But still you need some kind of expansion of universe, right? I mean, let me compare to some alternative to inflationary scenarios like slow contraction, like an ekpyrotic phase, which is kind of slow contraction, or there are scenarios like matter bounce. So I'm curious, what do you have here compared to those in
Again,
analogy with
I don't
alternative?
know about this other, but I'm sure these models are all related to a particular solution for the scale factor, right? Can be bounce, can be inflation, can be bomb or whatever. In my case, you can have all of these or no one of that, because what we want to solve? I mean, at least we address the main problem of cosmology. The main problem of cosmology are the singularity problem, are the flatness problem, and the isotropy problem. No, so the singularity problem is solved easily. You don't need to even investigate what is the metric. You can find many examples, but you don't need, because if you have a conformal invariant phase, so this any solution which is singularity free or singular, solutions that are singularity free or singular are gauge equivalent. So the singularity issue is
the prediction of NS is completely independent of the background.
Yeah,
so it's completely background independent result.
Yeah, it is actually is evaluated in Minkowski, and the computation is done in Minkowski, but you are already out of this phase. Okay, so the conformal phase is there because I want to solve the usual cosmological problem, and usually these problems are solved by inflation. I don't solve with inflation, I use conformal phase. I replace inflation with conformal phase. Then I get out this phase, and just after this phase, I compute, because I cannot compute in a conformal phase, I have to get out. And the hypothesis that when you get out, you have still, and you don't have 6 derivatives. You should evaluate this density perturbation in quadratic. 6 is already too much. That's the idea.
Okay. But curiously, the prediction you have NT equal to 1 minus NS is exactly same as string cosmology. So
yeah, exactly,
is it a coincidence, or is it how you model it inspired from string cosmology?
It's a coincidence. Probably in the beginning, I didn't know that thing. Brandenberger told me, or Gianluca told me probably, or about this similarity. Yeah, we got the same. We got the same. Probably because in string theory also they do not have any inflationary model. Probably,
well, there is a bounce of particular matter bounce, as Robert Brandenberger proposes. And so it's curious if it is really coincidence, and I'm curious to understand.
Yeah, it seems this kind of quantum gravity inspired or quantum gravity models give the same result, exactly the same for that relation. And then we have this nice lower bound actually, because it's very hard to have a smaller value for the tensor to scalar ratio.
Okay.
Well, it would be nice to falsify, at least, I mean, to be able to falsify a theory is a good property.
And will you get non-Gaussianities in this setup?
Strawan, I have a short suggestion.
Okay.
Even though it's a discussion time, maybe we will move on because I see 2 raised hands.
2-point functions are quite easy to compute, but still you need to work out. But in the papers, there are all the details in the appendix. 3-point functions are much more complicated because some tricks we cannot use there. And then, well, in principle, we can compute, of course, but it's very, very complicated.
Okay. Thank you.
You're welcome. Thank you for the question.
Anna, you also raised hand.
Yeah, I have a question to Leonardo Modesto. First of all, let me make a short comment on complex masses and these complex poles. The problem is not only with loop amplitudes and the fact that they don't appear in loops. The problem can be seen also in 3-level scattering amplitudes. If you have such states, and if you have a propagator which contains complex poles, your 3-level amplitude coming through the exchange with this propagator We'll also have complex poles, which contradicts to the desired behavior of from the point of view of analyticity. The known problem here is that we expect breaking of causality at the scales of masses of these imaginary parts of these masses. Let's say it like that. So it seems like even if you forbid these states to be existing somehow, then still you have a danger to come up with a theory which is not causal. I don't know if it can be resolved somehow.
No, I don't think the micro causality can be violated in either derivative theories as well as non-local theories. Micro causality. Macro, no, doesn't look like we have any examples of macro causality violations in the at perturbative level in these theories. But that's a feature. That's a feature, I would say. Micro causal. Well, you know, physically will be really violated. That could be a good question related to. So let me rephrase your question. Because yes, mathematically there is this violation in both the theory at the microscopic scale. We for non-local theories, we expect from Efimov paper. I also have some arguments that I never wrote clearly, but we expect in non-local theories. In local theories also there are papers by Anselmi, several papers. But then physically we can observe, well, it depends on what will be the behavior of the theory, according to me and the paper I wrote with Fabio, what will be the behavior of the theory at high energy. Because suppose that at the scale in which this, in which your collider is sensible, your detector is sensible to these particles, to reach such scale, do you see or not that particle? It depends on the behavior of the theory at that scale. Because if the theory somehow, if the amplitudes are extremely soft, or if the theory is free at that scale, then you can never test causality violation because particles are not interacting. Okay, no ghost can interact. No one ghost can interact with any real particle. Not even real particles can interact each other. Therefore, you cannot test any causality violation. No? Suppose that in your theory you had a ghost, but you do not couple the ghost to any real particles. That is not that theory physically doesn't violate causality. Okay, and of course at quantum level it could happen, but if the theory is soft or asymptotically free, it's not the case. You can never see that causality violation. You can never use somehow the theory protect itself from observing or using time machines or things like that. That's my interpretation that we wrote in a paper with Fabio. A short paper. Please tell me what you think about it.
Yeah, well, that's the point is that what is important, the theory cannot be behaving like asymptotically free along all directions in the complex plane of exchange momenta, of physics of momenta. And for causality and all these analyticity properties of quantum field theory, you need to know you need to be certain that there is analyticity at the whole complex plane of, say, Mandelstam variables or momenta in the propagator. If you have some extra poles or singularities, it can cause problems at the scales.
We can claim unitarity, so the S matrix are the usual unitary property, but the analyticity properties are different. That's the reason why we have causality violation. So, but nobody should impose I mean, we can be free to change the analyticity properties of this matrix. It's not a fundamental principle. It's something that you have in some theories, like two derivative theories usually, but this can change in higher derivative theories. And there is really this plot that I showed, that in which you have these extra peaks in the real part of the amplitude are the exact non-analyticity you're talking about, and can be observed in principle. But as long as you don't violate unitarity, I don't see any problem in principle. And of course, the state asymptotically be cut away, and that's an assumption that you mentioned in the beginning.
I mean that still may have some physical consequences, like you say. So it's there is
the
a
extra bit is, for example, a physical consequence. No, the particles are off shell. They are not on. They cannot go on shell by hypothesis, but they are there off shell. And one of the physical consequences, the one that I just mentioned, when you measure the scattering amplitude, you see an extra peak there. So, like for the zeta 0, the W, but they can be eventually also on shell. It will do. Nobody, I think, never measured. In this case, they cannot. See, please go ahead if you want to add something. Sorry to interrupt.
Okay, so I actually wanted also to ask a short question about the Weil invariant proposal for cosmology. I just wanted to understand better if you have any scalar degree of freedom left in the spectrum, or Weil invariance will kind of vanish dilaton, right?
Okay, yes. So the theory contains only, in principle, the minimal theory can contain just the standard model of particle physics and graviton. However, in order to get Weil invariance, most of these terms in the action, or to do not say all of them, will contain the dilaton. So you implement conformal invariance introducing the dilaton. But the dilaton is not a particle you can observe. There is no perturbative degree of freedom associated to it. It can be a background, can be non-trivial background also, but no new degrees of freedom. No new perturbative.
If you somehow manage to, if you somehow manage to get full Weil invariance unbroken without any conformal anomaly, which may be possible to arrange in non-local theory, but still it's just a tricky thing. But even if you do, like, if you have this symmetry, it's a gauge symmetry, so the dilaton background is apparently would be just a gauge. You can choose changing the dilaton background is equivalent to change of the gauge choice, and you are free to go with any value. So in this sense, I have a question: how you say that you have somewhat different regimes for different dilaton values. What do you mean by that? Because you can, in the unbroken conformal symmetry setup.
Here the broken and unbroken phases are a little bit tricky, but in the sense that this symmetry breaking is spontaneous symmetry breaking is an extremely simple case of symmetry breaking, because you don't have degrees of freedom left. Usually you always end up with at least one scalar, right? Here the theory is not so rich, and there is only one scalar and one symmetry. Therefore, the X phase is a phase without any degree of freedom. But I don't see any difference with the usual spontaneous symmetry breaking, because as long as you select one vacuum, you break the symmetry spontaneously, and this is what we do.
Well, normally you select your vacuum if you have 1 degree of freedom, dynamical. Then you can choose a value for its vacuum, and then go with that. This happens with dilaton of scale symmetry or broken scale symmetry. This is fine. It's possible to do, but you must have Gallstone boson left, because you had originally you had.
Yeah, there is. The procedure is exactly the same, but that Gallstone boson is not observable because you can always gauge away.
Yes, that's the gauge, and this means the fundamental difference between local symmetries and global symmetries. With global symmetries, you can break it spontaneously. With local symmetries, you cannot break it spontaneously. You can just because it's almost the same as just fixing a gauge. So your theory is defined. You cannot change this without changing the physical content. So this may be a really confusing thing, but it seems like, of course, if you break it somehow, if you have some explicit breaking, to reproduce at least the observable things in the late universe, then I think it's fine.
So think about Einstein's theory, right? So Einstein's theory, it is a conformal invariant theory in the broken phase of Weyl invariance. It's exactly the same. That's a matter of fact. You take the dilaton in your invariant, this conformal invariant theory, and you fix equal to the Planck mass because that's the observed value, and you get Einstein invariant theory. You can also introduce the Goldstone boson, of course, is there, and the non-linearly it contributes to repristinate the symmetry because the symmetry is only spontaneously broken. So the symmetry is still there. That's what I mean. It's just that you selected one particular value for phi, which is M Planck, that gives you the Einstein invert theory, and that's the theory in the broken phase, Einstein invert, where phi is constant. But in general, you have the dilaton and the Goldstone boson, which is pure gauge, true, but it is there in order, and you can show because of its presence that the theory is still invariant. If you make a replacement, a field redefinition in your action, the gauge symmetry doesn't change. So should be still invariant. It's just that you selected particular vacuum. And this is explicitly clear that after this replacement and the action, the theory is Einstein-Hilbert, which is not manifestly Weyl invariant, but secretly it is, like the standard model of particle physics is secretly gauge invariant. So,
well, I don't think that Einstein-Hilbert action, just written from out of nothing, knows something about Weyl invariance. Of course, you can promote it to Weyl invariance theory, introducing for a scalar, but then this scalar is non-dynamic. It's just another choice of variables in which you write your theory.
Yes, and so what? I mean, it's fine.
Yeah,
I mean, it's exactly the same. But when you say it's non-dynamic, well, non-dynamic, it satisfies the questions of motion somehow, no? But there is a gauge that can somehow take care of it. But it's true that you can make this replacement in your action and you end up with Einstein-Hilbert. It's trivial. I mean, it's so simple that it's confusing, but it's confusing just simply because it's too simple example. Okay.
Yeah, actually, it's nice to have this discussion because people often get confused with different symmetries like conformal Weyl or the other things.
Scaling by, yeah.
Yeah.
Here, I mean, omega, the scaling of the metric is local, of course. Yeah, it's omega of x. It's not just scaling by. Yeah. So.
Yeah. Okay. I think that there are some other people who wants to ask questions.
Thank you. I appreciate your comments. I can understand your point.
Thank you for your reply.
Yes, indeed, Marco Piva is waiting.
Okay. Hi. Can you hear me?
Yes, we hear you.
Yeah, so I have just a comment about the first question, Alex, I asked to Leonardo about the ghosts. Actually, removing states by hand from the possible external state is exactly what you do in Young-Mills. Is exactly the same thing. You restrict into a subspace of the Fock space. The fact that you have BRST symmetry is what guarantees you that they are not generated back by loop correction. So you imagine you have a Feynman diagram where the external lines are only the physical polarization of gauge bosons, and inside in the virtual lines you might have everything else, including the Fedorov ghost and transverse, longitudinal components. What you cannot do is to remove them by hand without modifying something else, because you remove them from the external state by hand, and then if you have a non-zero cut diagram which involve a cut propagator of ghosts or non-physical gauge boson contribution components, then they are generated back because you have a non-zero imaginary part. Imagine something that like a 2-point function with only physical external states, and inside you might have some ghosts. If this has a non-zero imaginary part, it means that there is a non-zero probability to produce what's inside on shell. But in case of gauge theories, you have BRST symmetry that guarantees you that actually the only non-zero cuts involves only the physical degrees of freedom. And then you can say, okay, so I can put the external lines by hand to be, impose the external lines by hand to be only the physical ones. So here you do the same. Now the procedure is different. There's not a symmetry. If this is what you wanted to understand, there's no symmetry that guarantees you this. This is something else that is put by hand. It's whatever, a prescription or whatever method is used. It doesn't matter, but putting the external states by hand, so restricting on a subspace of the Fock space, is exactly what you do in Yang-Mills as well. That's the only thing that is the same. Is the
I
reason
agree.
why this is consistent that is different in the two cases.
This I agree, but you correctly mentioned that there is no symmetry here, which really guarantee you that something is preserved, unless apart from some computations which were done perturbatively, loop by loop, showing here.
Okay, but I was just I just wanted to have this comment because you started your question by saying in Yang-Mills I know that they cannot be external state but here you're putting it by hand. It's the same. You put by hand. If you compute a scattering between a gluon and a Faddeev-Popov ghost, you get non-zero. So the amplitudes are not zero.
Okay, yes, here I agree. Yes, here I agree. I would say that in Yang-Mills, usually people think like, okay, let's put them inside of a loop and show that they are not generated outside as long as there is BRST symmetry.
Yes, yes.
Yeah. So this way so practically it becomes equivalent, but here it's like equivalent up to some loop order, which people, you including, have computed, but there is no like symmetry which guarantees it should be for any order, let's say.
Okay, it depends on what method you're choosing, since Leonardo mentioned that there are indeed several proposals. I know about what I do, but if you're choosing a different prescription for a propagator and you do it in every legs inside every diagram, then you have the same.
Yeah, no, the result by Anselmi and Piva is any loop order correct? I mean, proved. So never at any perturbative.
I mean, we can question about that, but this is not the time to do that. But just want to say that putting by hand external states is a standard thing in gauge theories. And now you can wonder, but I trust this to be consistent at every order only if there is a symmetry. Okay, at this I don't agree, because I know that this can be consistent also without using a symmetry. Of course, you have to modify something else. You cannot just say there's no symmetry, but it's consistent to remove something by hand from the external state. You have to do some other modification. Now, whether this modification is consistent or not, okay, you might.
No, it's not like I trust or don't trust, but I would look at it differently. I would say like, if it happens such magically that they really don't appear at any order, and but then I would say that I would be wondering where is my symmetry, which I'm missing, which I don't understand. Which maybe also
there's no symmetry, because the point of I guess that some of the things that I know I do are somehow overlaps also with the other. Well, they are not overlaps, but there are some things that are true in all the other approaches where you want to remove these ghosts somehow from the external states because you don't want them to see. You don't want to see them. But you want to keep something else. You want to keep the contribution inside loops. So it's not really like Faddeev-Popov ghost, because they are completely unphysical. So the fact that they do not appear as external state because you remove them by hand, this is consistent with the when they are in the virtual state, is consistent with the cutting equation. So they are not generated back again. And it's because of asymmetry. This makes them completely unphysical. They are not posed. They don't give observables signatures at all. There are mathematical tricks to deal with the redundancy of gauge symmetry. It doesn't have to be like this. This is if you would have find, let's say this, if you would have find a symmetry that allows you to remove the ghost in stellar theory or whatever other theory with ghosts in the same way they are removed with Fadeev-Popov, they would be unphysical. You would have general relativity, let's say. Of course, there's no such a symmetry as far as I know. So the thing is that they are physical. You just remove some part of their physical appearance, but something else is still there. So if you find a symmetry, I don't think there is any symmetry that removes them. If there is, then you get GR. A very complicated way to get GR, probably, or something like that. This is very speculative.
Yes, this we can also discuss one day. Indeed.
Okay.
But I agree with you that in both cases we somehow can remove them. We somehow remove them by hands. This is correct. Yes, this I agree.
Okay, thanks.
Yeah.
Sorry, I would ask, I would make a comment about what Marco was saying. As far as I remember, there is a paper by Witten, maybe in 3D quantum gravity, where he tried to introduce an extra kind of BRST symmetry in Weil gravity, and he ended up with a topological theory. So it seems that if you force the theory to be more symmetric, to remove the ghosts, then all the states disappear, even the real one. So you get a topological theory. But this is just a caveat. I don't know if it is true in general. But no. I don't think so. There is a symmetry to protect. Yeah.
Okay, any other questions around? Let me just remind that the next talks will start, roughly speaking, in 40 minutes. So it looks like, so Zoom will not be closed. You can stay and discuss further things. So the next session will start at, yes, indeed, in 40 minutes. In 40 minutes, we have to recombine, and we will start with Ivana, Basil, and other people. Also, let me remind that we would be happy to upload slides to the website so that people can consult them later if they want. And for the moment, let me declare that I stop following like a chair of this discussion, and I announce it like a break for 40 minutes. But you're welcome to continue talking, of course, if you want.
Thank you, but actually in 10 minutes I have to go because I have to teach.
Yeah, but maybe other people want to exchange some.
Just apologize. It's already evening, late evening, right? In China, yeah.
Well, it's not late, but how to say this better? It's already getting dark.
Okay. Okay, I will take a break and I come back then. See you, Leonardo. Nice to see you.
Bye-bye.
Hello, Ivano, do you hear me?
Yeah, hi.
Oh, hi, good. Yeah.
Hi, Ivana.
Sorry, I'm a bit kind of last 5 minutes, but with this break, to have something to eat is not very easy stuff. So, since you are a co-host, what do you think? Are you able to share slides?
Yeah, I believe so. Let's see.
First two speakers also believed so, but you know, things happen.
So this
No, I
would
mean,
be
you can
my...
share slides. I mean, you are advanced speaker, yeah.
Wait, what?
You can share slides. So you
Did
are
that...
advanced speaker, yeah.
So is this fine?
Yeah, it's
okay, great.
Looks very well, yeah.
Okay, and you see the pointer, the mouse pointer.
Yes, we can see.
So if I scroll and such, should be fine, right? Very good.
Yeah. So Anna, do you have a program?
Yes.
I mean, you have it. So Anish, Breno, and Gia. So where is Gia? Gia Dvali. No.
Well, I think some people are still decoupled.
What?
Some people are still decoupled. We had more participants in Zoom.
I think they will join.
Yeah.
I believe they also wanted to get some, I don't know, cup of coffee, short snack. But also new people will come.
I have my coffee with me. Is that a Starbucks coffee?
For me, some Lavazza coffee machine.
Hello, Philip. Looks like you woke up very early.
You took it to me, or... Sorry, I cannot see anybody by sharing screen. So if someone is
Yeah. Hi. Hello. Good morning or good afternoon.
Hi, Philip. Good morning.
Even good night. Yeah. At 7:15, I'm up and about. Ready for the session. Fortunately, I don't have to speak, so I can easily listen.
Yeah.
Not quite sure what I'm going to do tomorrow. Tomorrow I have to speak as well. But you were merciful. You didn't give me the first one.
We can change if you want.
It's too late. I've already written the talk.
Yeah, indeed.
Yeah.
Indeed.
No, that's fine. Anyway, hello everyone.
Yeah. Anyway, and it's getting late already, so you see, like, not easy to manage all of this. But next time, it should be here in Shanghai. So you should come and you will adapt to the proper time.
Oh, okay. Very good. Let me say hello to Ivano.
Hi, Philip. I sort of recognize you from your voice because I cannot see you, but hi.
No, I put the video on.
No, I cannot see you because I'm sharing the screen.
How
are you doing?
Me, I'm doing very well. I just put a paper on the web on Sunday, so yes.
Very good. Looking forward to take a look.
Yeah, I actually I retired from teaching, so I'm actually now more productive than before.
Oh, very good.
Yes, as you'll find out tomorrow. Okay.
Yeah, definitely.
I'm going to.
So just momentarily unshared. See what's going on, and
yes,
when you want to start, I can share again.
Yeah, I think. Anna, what do you think? Should we start? Should we wait more?
We have at least first two speakers are in Zoom now, so hopefully.
No, but third speaker should be also somewhere. Breno, it's Breno. Breno, where is Breno? Breno is student of Leonardo, so maybe he also will join kind of last minute. I don't know.
Okay, I think still we can start now.
All right, I'll share again. One second.
So we start from the talk by Ivano Bazil, Dark Energy from Dark Bubbles.
Yeah, here you go.
All
All
you
right.
have
Okay.
40 plus 5 minutes.
Yeah, thank you. Okay, so can you see the slides on the pointer again? Yeah?
Yes.
Okay, fantastic. All right, thanks a lot. And obviously, thanks to the organizers for this kind invitation. And I must say, I'm really impressed with the organization, overall, because, putting together so many people from different time zones, it's really, really impressive. Okay, so anything, including faces and chat messages and so on. So please, as far as I'm concerned, feel free to just ask any questions or make any comments without, interrupt me at any moment. Okay, so this is and I remember very fondly last year in Portugal. It was really a great experience. And so in the spirit of the conference, I decided to present this work, which is half already published, half work in progress. And it is indeed about how quantum gravity can help making up, constructing models of realistic cosmology, right? And hence the title. So the dark energy part is obviously connected to cosmology. That's the main ingredient. Cosmological model is dark energy. Whereas the dark bubbles, they refer to a particular type of scenario that arises in string theory. Okay, so it's a scenario that I will describe first roughly how it may arise, in a sort of a model-independent way, as it was originally proposed, and then the bulk of the talk is supposed to be about how this type of scenario, this dark bubble cosmology, which was named such by the original authors, I didn't make this up, can arise in string theory. Perhaps the audience, I cannot assume the full background in the types of things I'm going to talk about. And therefore, I tried to make the talk more accessible, but also in particular on the shorter side, which means that if all goes well, there is more time for questions. So again, I encourage people to interrupt and ask away. Okay. With a sort of a grocery list, right? What we need to do if we want to, build a sensible cosmological model from string theory or really any other sort of approach to quantum gravity that may have similar features, right? So we need to make the universe look like our universe, right? What does this mean? Well, let's start with the coarse features, right? The ones that are, more apparent. Namely, we need to see 4 large space-time dimensions, first of all, right? So if there are any extra dimensions or anything that looks like, that behaves like extra dimensions, it needs to be sort of suppressed at low energies, right? The kind of experiments that we have performed. And second, perhaps the most important distinguishing feature, at least for my purposes, of a cosmological model is to have dark energy, and it has to be a dark energy that is both positive and small in Planck units, right? This is now it doesn't mean that it has to be constant. Okay, I'm actually not going to end up with an actual cosmological constant, as it turns out. I'm going to have dark energy that varies. This is sort of the spoiler for the end, right? But what matters is that we have a dark energy that behaves sufficiently like what we see, right? And then everything else is the details, so to speak. So the more microscopic aspects of the model, such as, what matter we have, if we have chiral fermions of what types and so on, what representations. And of course, none of this is compatible with unbroken supersymmetry, which may or may not be a feature of the models we start with. And so all of these things that we need to do to make work for our model are sort of all tied together, right? Because especially in string theory, each ingredient talks to all other ingredients in such a way that it's very difficult to just fit what we want and build any sort of model that we want. There are various issues with making extra dimensions small or just making them disappear completely. There are issues with making, constructing de Sitter vacua and making them stable and so on. So what I'm advocating for this talk is sort of a different approach compared to the one that is all followed usually in what one could name the mainstream approach to the phenomenology of string theory, right? And this is the sort of the mainstream approach that perhaps most here are familiar with. And the usual paradigm of building models from string theory is to have, to start from the most well understood theories, which are the 10-dimensional superstrings, and compactify the extra dimensions, right? Putting them in small compact manifolds, which are usually chosen in such a way as to preserve supersymmetry all the way down to low energies. This is very nice for more formal purposes. It's nice to have a computational control, to have an understanding of what's going on, perhaps to the extent of being able to compute things exactly, like all possible quantum gravitational corrections to certain quantities may be computed in certain examples of this type. And so the usual paradigm sort of attempts to keep this computational control alive as much as possible, to keep these ingredients fitting together in a way that usually preserves supersymmetry or at least some semblance of control down to low energies, ending up with sort of this landscape of effective field theories that usually look pretty far from our universe, at least for the purposes of this talk, right? Perhaps the closest that one can end up with is the minimally supersymmetric standard model or things of that sort. But getting down the grocery list that I told you about turns out to be quite difficult, right? So what happens is that there are many problems that one encounters when dealing with the standard approach. So first thing is, again, the first item on the list, getting the extra dimensions to be small. This is very hard. This is the so-called problem of scale separation, right? We need the scales to be separated. The scales of the external space-time, the Hubble scale, if you will, has to be at least strongly separated from the scale of the extra dimensions, namely the Kaluza-Klein scale, as it's named. And this is sort of a really big obstruction, right? To date, there are no examples of this type of constructions which everybody agrees upon, right? There may always be loopholes in one way or another. And then, of course, the problem of getting out of this dark energy that is positive is even worse, right? There are numerous obstructions to that as well. And again, all of this paradigm is usually meant to preserve supersymmetry all the way to low energies, which means that whatever means we implement of breaking it at the end of the day, because it needs to be broken, obviously, will end up in other types of issues, because as it turns out, there are obstructions to breaking supersymmetry at low energies in string theory, right? There are issues with the control of the effective field theory.
Excuse me, since you have a question.
Yes. Ivano, can you ask the question the other way round? namely, suppose you had a low energy symmetry, a low energy theory where the scales were separated, you had de Sitter and you had Saussure breaking. Are you able to show that that would actually embed in a string theory in the first place?
Probably not. I mean, the answer is probably. Sorry?
Maybe it's hard to do because it's not possible to do.
Exactly. So it's not clear, it's not completely settled whether certain features are 100% outside of the landscape of string models, right? It's very hard to completely exclude something, right?
Okay.
Some models we can exclude with very high confidence, but this is probably not one of them at the moment. So if you told me, for instance, that we have a model that has all these features and that has, say, no particles with electromagnetic charge that are whose mass is lower than the charge in Planck units, then I would confidently tell you this model cannot be embedded in string theory. But it has to have certain features, unless that's the case, I would just answer that I don't know, right? Yeah, I'll take the silence as an okay. But I'm very happy to keep discussing about this later, if you want. Okay, so actually, this is a very good question at this point in the talk, precisely because it's not completely clear whether these features are impossible to realize in this paradigm that I showed you. It's not obvious that the paradigm is just doomed, right? I mean, it could, as I wrote here in the slides, it's hard to do this. It's, there are obstructions to do that. There are maybe no examples that are known, etc., but there's no proof, right? And I'm afraid there cannot be any proof at this stage in development because, there is no complete full definition of what the theory is in all its possible regimes, right? So we have to work with the evidence we have. And this is what I'm doing here. So the two extremes options are either to thread the needle, right? Which means to tiptoe around these obstructions and just find the loopholes at each stage, just to fine-tune things and find the precise way of realizing what you need, even though the vast majority of models don't work in this way. Or the alternative strategy that I'm going to pick for this talk is sort of to take the hint, right? To take this state of affairs as an indication that the theory doesn't want us to build realistic models in this way. Perhaps we don't have to compactify extra dimensions. Perhaps we don't have to break supersymmetry at low energies, right? Perhaps we can do something different. We can hide the extra dimensions in another way. And we can start with the string theories that don't have supersymmetry at all, of which there are examples, or perhaps we break it at the string scale, so very high energies, right? So the starting point of this talk is to take the hint that these sort of swampland principles are telling us, are giving us, and just go with the flow, right? Just see if there is an alternative approach that just doesn't have these problems to begin with, right? It will have other problems, of course, because there's no free lunch, especially in quantum gravity. But perhaps we can at least go forward and make progress in another direction. And so this is the approach that I'm going to take. And instead of working with compactifications, I'm going to work with dark bubbles, right? So this is the sort of alternative paradigm that I'm going to work with. And then I'm going to see if it can be realized in string theory, okay? So what's this dark bubble cosmology about? Well, it's a scenario that was sort of revived after many decades by these people in Uppsala. I mean, there were hints of scenarios of this type way back, perhaps in the 70s or 80s, but at some point it sort of died, and it was revived very recently by these authors. And the idea is somewhat similar in spirit to the Randall-Sundrum brain worlds, but it has a few key differences. So instead of having like a brain that is sort of, you know, our universe lives on this membrane embedded in a higher dimensional space-time, but instead of like sitting still, right, it expands. So there needs to be some sort of instability that drives this membrane to appear, to nucleate inside of space-time, and then to expand, right? So this is this membrane has been dubbed dark bubble for reasons that I'm not completely sure of. But at least the bubble part should be clear, right? It's sort of a bubble that appears because of an instability, and then it expands because of its own tension and gravity, essentially. So when can this sort of scenario be realized? It's particularly easy to concoct a space-time that is anti-de Sitter, right? And it is unstable toward nucleation of these membranes or bubbles, right? So we have examples, and I'm going to show you later of such constructions. And so all you have to do is make this parent higher dimensional anti-de Sitter universe. You make it unstable, and then you just wait. And at some point, these membranes are going to pop up out of nucleation, and then they're going to expand. And why is this useful? Well, because if you're a little observer living on the membrane, on the surface of the bubble, what you see is actually an expanding universe, a universe undergoing accelerated expansion even. So what you see is a universe with a positive dark energy. And moreover, if things are favorable, and I'll discuss this later, what this means, the extra dimensions, even though they are large, they will be hidden from you if you are confined on the brain, right? So this is sort of the mechanism that is an alternative way to build the sort of 4D gravity with the positive dark energy. And let's delve into it a little bit more. So how does gravity work on this membrane that expands in anti-de Sitter? Well, obviously, because the extra dimensions are large, the actual gravity is not confined on the brain at all. It propagates in the extra dimensions without any obstacles. So the compactification mechanism works because if the extra dimensions are small relative to the scales at which you do your measurements, gravity behaves effectively like it's in 4D. But in this case, that's not true, right? So how do we square things with what we see? Well, there is an alternative way, and it's that the philosophy is the following. Instead of confining everything to 4D, we extend everything to the extra dimension. Let's say for the sake of this discussion, let's say it's 5D, right? So one single extra dimension, which is the anti-de Sitter direction in which the brain expands. So what happens is that you can rewrite the 5-dimensional Einstein equations by using some nice identities of that relate curvatures with the intrinsic and extrinsic curvatures on the surface of the brain. And if you play with the 5D Einstein equations, including this, the stress tensor that is localized on the brain, which is sort of acts as a gluing condition between the inside and the outside of the brain. If you do some, heavy algebra, you end up with an effective Einstein equation on the surface of the brain. But you see, because gravity does not localize on the brain, this equation will not look like the usual one. usually one would expect something like Einstein tensor in 4D on the membrane equals the stress tensor of the stuff that lives on the brain, right? Well, but in this case, there will be an extra piece, precisely because gravity is not fully localized. And this piece is due to the fact that there can be sources of gravity that are extended in the 5 dimensions. And this picture, tells the story much better than I can with words. These sources can be strings that are attached to the membranes. And this is something that happens routinely in string theory when we have D-branes, right? D-branes are a particular type of these membranes that can host open strings that they can attach to the surface of the brains. And so if we can have these extended sources, right? And when everything is sort of projected on the directions parallel to the surface of the membrane, we see that the Einstein equations become, as if these sources were particles on the membrane with a particular mass that can be calculated. And all the details can be found in these papers that I showed you earlier. So this is a sort of alternative mechanism to have 4-dimensional gravity on this brain. And the dark energy that lives on this brain can be made positive because it has an expression that looks like this. So it's proportional to a factor of this type that involves the tension of the brain relative to a certain critical value that depends on the anti-de Sitter parent universe, right? So this factor involves the curvature of the parent anti-de Sitter and the tension of the brain itself. And if this ratio is bigger than 1, dark energy will be positive. And if this ratio is close to 1, this dark energy will be small, right? Because this is measured relative to the anti-de Sitter dark energy, which is the scale of the extra dimensions, if you will. And then, one can go further, and these people have investigated lots of stuff like black holes, like how radiation and matter sources appear in this brain cosmology, and how gravitational waves behave, and so on. So there's lots of stuff that has been done on the bottom-up side of things. So these people have just assumed that this model exists, and then they worked out the consequences of this. Right? What I'm going to do here, because it's a conference about quantum gravity and cosmology, not just cosmology, I want to present a potential explicit construction of this scenario in string theory, right? So are there any questions about this part? So this, how dark bubbles work?
Well, I'll go first, if I may.
Yeah, sure.
Isn't it the case that if the 5-dimensional geometry is exactly anti-de Sitter, that T critical over T squared is equal to 1? I mean, that's the Randall matching condition. So you need somehow the bulk geometry to be lowered below ADS5 by the new condition.
Very good. So the answer is, so when the bulk geometry is exactly anti-de Sitter, whether this ratio will be smaller than 1, greater than 1, or exactly 1, actually depends on the nature of the brain as well as the anti-de Sitter. So it's not enough for the anti-de Sitter for the bulk geometry to be exactly ADS to conclude that this ratio will be exactly 1.
No, but the geometry on the brain is it has to be fixed to be a section of ADS5.
Yes.
The bulk is ADS5.
Yes, exactly. And which section?
Yes.
Which section it is depends on the brain. So whether the brain is exactly critical, which is the case in the Randall-Sundar models, or it's subcritical, and then it gives you de Sitter induced geometry. Right? So what is true, and this is a very good point that will be extremely important at the end, if the bulk geometry is exactly anti-de Sitter, and so if the bulk geometry is exactly anti-de Sitter, the brain geometry will be maximally symmetric. Okay, so it's either ADS, Minkowski, or de Sitter. And in this case, if the brane is subcritical, it will be de Sitter, right? So dark energy will be positive and constant. That's what I want to say. And as it turns out, there are models that are more desirable for other reasons, where the bulk geometry is not exactly anti-de Sitter. It's anti-de Sitter plus some deformation. And this, in turn, implies that the geometry on the brane will not be exactly de Sitter. It will be a quasi-de Sitter of the sort. So I will get to that. But thanks for the question. Okay. So
okay, there's one more question.
Yeah.
Please go ahead.
Yeah.
Yes, thank you. My question is, in this model that you're considering, this lambda brane, it has the same, it plays the same role as the cosmological constant in the...
Yes,
okay,
that's exactly right. It's precisely the cosmological constant, yes.
Okay, thank you.
You're welcome. Okay, so let's go ahead. So in order to build these models, supersymmetry has to be broken, obviously, because otherwise everything will be stable, right? We need the instability to make these branes expand. So there are a few options here, but because of the reasons that I told you about earlier, it's much easier, at least for this purpose, to work with models where supersymmetry is either completely absent or it's immediately broken, right, in the UV, so to speak. So this is what I will do. The other approach, which is the star in the mainstream sort of techniques, is ridden with all sorts of obstacles to build these sorts of models. So this is what I'm going to do. I'm going to take 3 models where supersymmetry is immediately broken. Okay, so these may be sort of less familiar with respect to the usual models. So you may be familiar with this hexagon, right, where these corners are supersymmetric models, right? Now, of course, one can start from one of these and just break SUSY somehow, but it turns to be very hard to do without introducing deadly instabilities that just completely ruin everything immediately. There is another option, and it turns out that there are other models in this very simple landscape of 10-dimensional string theories, where one can avoid these tachyons and yet end up with a theory that doesn't have space-time supersymmetry. So these are the 3 guys, right? These are the 3 models that I'm talking about. And they fall into 2 classes. For our purposes, these are 2 orientifold models. That we don't need to know exactly what this means for this talk. And then there is a model of the heterotic type. Again, we don't need the details for this talk, but I can go, I can elaborate if need be. So we have these 3 models in these 2 classes, right? And these models don't have space-time supersymmetry, and we can, but they don't have tachyons either. And so we can start from them to try to build this scenario. We want to build the anti-de Sitter that hosts these branes that expand, right? This is what we want. So how does this work? Well, these models have a peculiar feature. So again, I'm dividing this into the 2 categories. And both the orientifold models and the heterotic models, for one reason or another, they generate vacuum energy in this 10-dimensional universe. And this vacuum energy is a sort of a potential for a scalar field, which is the dilaton that always appears in these theories. And it's a sort of this exponential potential that is either sourced by quantum corrections in the case of the heterotic model, or in the case of the orientifold models, the dominant contribution comes from the fact that there are objects in space that have an energy density that also couples to the dilaton, of course. And so this is in more technical terms. You have to add the tensions of these guys, and they couple to the dilaton in a certain way. Or you can just have do your one loop integral bubble diagram to compute the vacuum energy that results from quantum effects, and end up in both cases with this sort of exponential potential. You have to translate it into the Einstein frame to figure out what this exponent is. But the point is that you always end up with an exponential potential. So what's the effective field theory that describes these models at low energies in 10 dimensions? Well, usually in these sort of stringy effective field theories, one has at least a few universal ingredients, which are gravity, of course, then the dilaton, which is a scalar field that couples to other stuff with exponential interactions, and then there are some higher form fields, right? Antisymmetric tensors. And in this case, in these models, we have our beloved B field. So it's a 2-form whose curvature is a 3-form. And then in exactly one of the 3 models, this one, the one in the corner, the 0'B model that was discovered by Sagnotti in 1995, in this model and only this model, there is also a self-dual F5 field string that couples to D3 branes, so branes of dimension 3, spatial dimension 3. The other, all of the models also have this 3-form B field. Okay? So what this means is that these much like the electromagnetic field couples to electrons, these fields couple to branes of a specific dimension. In particular, the analog of the electron and the magnetic monopole is, in this case, it's a brane of dimension 1 and a brane of dimension 5. Okay, which means that the world lines, the world volumes swept by these branes are of dimension 2 and 6. Okay. And then in the 0'B model, there's also this a flux that couples to these D3 branes, which means that they have a world volume of dimension 4. And you may recall that 4 is the number of dimensions that we see in the universe, which makes this model particularly interesting. So I'll get there in the end. Okay. So just keep this in mind. But then there's this extra piece that appears from the breaking of supersymmetry, which is this exponential potential, right? And this is a problem because this V naught here is a number that is, like the string scale, which means that if you just let if you look for the simplest solutions, the simplest backgrounds of this effective field theory, you end up with stuff that is very strongly curved. There's going to be warpings of the geometry over the order of the string scale, and so you need infinitely many corrections to include, and everything is awful. So the solution here, which is exactly what we need to build our anti-de Sitter universe to put these branes inside of. Yeah.
Ivano, you can't see us, so you don't know that I've raised my hand.
Sorry, but yeah, go ahead.
I have another question, if I may.
Yeah.
I'm an outsider to string theory, but I had thought that in descending from 26 to 10, it required supersymmetry. And yet you're telling us that that's not the case, that you can have 10-dimensional strings that don't have supersymmetry. So why was the big excitement in coming down from 26 to 10 done in the first place?
Well, the coming down from 26 to 10 happens when one includes supersymmetry on the world sheet of the string. Yes. Now, the consistency conditions that are entailed, in the whole business of building these models are the so-called GSO projections, and it just so happens that the easiest GSO projections that one can find to build the space-time theory also implies supersymmetry in space-time. But this is not a one-to-one thing. So worldsheet supersymmetry seems to be necessary at least to have fermions in space-time, which is definitely something we want to have. And then one ends up with 10 dimensions if one requires that the space-time curvature is low. It's a whole story. But then supersymmetry in space-time is not actually implied. It's it only happens to arise in the simplest models that one can build, but not all of them, right? In particular, in 10 dimensions, there are exactly 3 models that have no space-time supersymmetry, and yet they have no tachyons.
Okay, so
this is perhaps sort of a less known fact, but it is true.
Very nice, thank you. So your model still has fermions. It's just that the fermions don't have superpartners.
Precisely. So these models have fermions in space-time. So this is the light bosonic field content of the theory, but there are also light fermions, which I didn't say anything about, but yes, that they are present.
Okay, thank you.
Very welcome. Okay, so yeah, this is a very important point, and we'll need this later. Okay, so what we need to do, again, remember, is to build an anti-de Sitter vacuum background that can be unstable toward the nucleation and expansion of these brains here. Okay. So how do we do that in a controlled manner? We have to balance this potential here, which is sort of a runaway potential. It has no minimum. So what we can do is we can exploit this the fact that the dilaton couples to everything, and we can turn on fluxes, right? We can turn on these generalized electromagnetic fields. And in so doing, we can sort of balance the 2 exponentials against each other, right? And end up with a stabilized vacuum. So it turns out that doing that produces anti-de Sitter backgrounds, right? So by turning on this flux, one can construct anti-de Sitter vacua of the Freund-Rubin type, right? So they are space-times of the form anti-de Sitter times a compact space. So something like anti-de Sitter 3 times. Yes.
You have about 5 minutes to finish.
Yeah, I know. I have a timer. Yeah, thanks. So one can build vacua that have this anti-de Sitter shape times a few extra dimensions that are compact, but they don't matter for us. We can never find de Sitter vacua in this way, which is what we proved in this paper. But the most important thing is that this, you see, this vacuum depends on the number of units of flux that you pump in space-time, right? And these guys will decay. They are not supersymmetric and they're not stable. They will decay slowly but surely to lower values of the flux. And the way this happens is that this flux is essentially, it makes these brains pop up, makes these brains nucleate inside of the vacuum, and these brains have charge. So as they expand, they carry away the missing flux. So charge conservation tells you how this works, right? So this is a bit more detail about these vacua. These are sort of anti-de Sitter times an internal space, and the curvature radii of these guys are proportional to powers of this number n, and also the string coupling that tells you how strongly the quantum corrections are weighed by the string coupling, how strong they are. It's also a negative power of this number of flux units, which means that for large fluxes, these vacua are very well behaved. The corrections are small. Now, there is a little exception, and I will tell you about this later, but this is the story. So we can build unstable anti-de Sitter vacua by pumping flux in space-time. And these vacua will be unstable and they will decay, right? So why do they decay? Well, the reason is that these vacua are essentially built by stacking lots of flux, right? But flux doesn't come from nowhere. It comes from charges. And the charges are the brains because they carry this charge that sources the field. So basically, these vacua are built by stacking a bunch of brains in space-time, and they curve space-time in such a way that they generate this anti-de Sitter throat region, much like an extremal black hole. And as it turns out, if you calculate the tension of these brains and the charge of these brains, it turns out that they are more charged than they are massive. So the electrostatic repulsion is stronger than the gravitational attraction. This is the so-called weak gravity conjecture at play, but the point is that we computed this. And so what happens is that these brains feel a potential, they feel a force from the other brains, and they are repelled. And from the effective field theory, this can be seen as a rate of nucleation that we also computed. So at the end of the day, we end up with the scenario that we wanted, right? I'm almost done. The scenario that we wanted is this anti-de Sitter parent universe. And this anti-de Sitter nucleates brains, and these brains expand. And if you're a little guy living on the brain, you see de Sitter universe, or at least a quasi-de Sitter universe, depends. And what are the advantages of this? The advantage, other than everything that I said at the beginning, is that because we have a microscopic theory giving us this scenario, we sort of have more control over what happens on the brain. So what are the degrees of freedom, right? What are the matter fields? What are the gauge loops? What are the couplings? So we know all of this. We can, in principle, compute stuff. Now, it turns out that with the simplest types of these vacua, the exactly anti-de Sitter vacua that we build out of the brains that are of dimension 1 and 5, these two, they give us anti-de Sitter. And as I said, this gives you a brain world cosmology, which is de Sitter. This is what I said before. Now, the problem with this is that this formula for the cosmological constant tells you that dark energy is positive. But it also tells us that it's of order 1 relative to the scale of the anti-de Sitter. And remember, the scale of the anti-de Sitter is the scale of the extra dimensions, which means that dark energy is positive, but it's not small. The extra dimensions are not hidden in this scenario. So for these two types of brains, the 1 and 5, the model doesn't fully work, right? So there is an extra, remember there was an exception. The exception is the unique exception actually in this class of models is these D3 brains in the model found by Sagnotti. And these D3 brains, they curve spacetime in such a way that they generate a quasi anti-de Sitter, so not quite anti-de Sitter, but almost. And you see the reason is that the curvature radii and also the string coupling are equal to constant values, which are actually the values of the supersymmetric anti-de Sitter 5 vacuum, the famous one. But then there's a correction due to the breaking of supersymmetry, right? And this correction is small if you put a bunch of brains, but it also runs with as you move. So it's not just the anti-de Sitter is actually deformed in shape, right? There's a slight running of the curvatures of the anti-de Sitter. And this implies that if, when these D3 brains start repelling, and they do, they will, a little guy living on the brain that expands away will see not quite de Sitter, but a quasi-de Sitter. And this is what you end up with. You end up with a dark energy of your quasi-de Sitter brain world, which is positive, once again, because the brain expands. But relative to the anti-de Sitter, it's now small, finally, because you can make this parameter small in this model, as opposed to the other two models.
Ivana, something happened with your sound. Sorry, we don't hear you.
But then, what's the price to pay? The price to pay is that it's not constant. It has to run the time. Okay. Hey. Yeah?
Yeah, the time almost gone also. So
Yeah, I know, but this is the last slide. But can you hear me now?
Yes.
Okay, very good. So as I was saying, so the price to pay for having a dark energy that is also small, it's that it's not constant, right? So in this model, it has to run with the scale factor in a way that's very weak, right? It's logarithmic, but it's nonetheless present. So if you will, the prediction of this model is that we have a 4-dimensional brain world supported on D3 brains, it expands because of breaking of supersymmetry. Dark energy is positive and small, but it changes with time in a way that is logarithmic in the scale factor. This is the Friedman equation of this model, okay? And we can also put bounds on the scales of the extra dimensions by requiring that this scenario makes sense for, for the whole expansion of the universe. And also the nice thing is that because we know the degrees of freedom of these brains, we know that they carry unitary gauge groups and chiral fermions. And we know what representations of these guys exist, and we can make the standard model gauge group by just putting one brain slightly separated with two brains, slightly separated with three stacked brains, which means that we can easily engineer U1 times U2 times U3, right? Of course, the SU part arises at low energies after decouplings of the U1 part. So this is what I wanted to say. We have a concrete string model where it looks like one can build this sort of brain cosmology with a positive small dark energy in 4 dimensions, which changes with time, right? This is the characteristic feature. And the broader punchline of the talk is that perhaps maybe this can be an alternative way of building realistic models from string theory, not by compactifying, but by making brains nucleate and expand, right? And at least the broad strokes are correct. The devil is in the details, as Roberto said in his talk too. The details are the couplings. So is the effective field theory minimally coupled in the way that we want it to be? Are there any spurious couplings that would be observable and so on? This we don't know, but it's a work in progress, as I said. So there you go. Thanks a lot for the very nice questions, and I'm happy to answer more.
Okay, thank you very much. Are there any quick questions? Maybe we can have one and then turn to the next speaker.
My question is not quick, so I'll leave it to the discussion at the end. Is that okay?
Yeah, I think it's better to leave the
Good.
discussion session.
Thanks, Philip.
Okay, if there are no questions for the moment, then let's turn now to the next speaker. And,
thank you.
Yeah, could you please stop sharing?
Yeah.
Hello, can you hear me?
Yes, we can hear you.
Okay. And do you see my screen?
No, yes, we can see.
Yeah, we can see Anish.
Nice. So the next speaker is Anish Ghoshal with a talk, Primordial Black Hole Archaeology with Gravitational Waves.
Okay, so
you have 40 plus 5 minutes. So please, you can start.
Okay, so thank you for the invitation to present this talk in the conference. So this talk is more on the cosmology and phenomenology side rather than on the theory sides. And I have a little bit of longer talk, so I will try to shorten a few things, and then during the discussion time we can go into the details. So the title of the talk is Primordial Black Hole Archaeology with Gravitational Waves. Particularly, I'm going to talk about 2 sources of gravitational waves. One is from cosmic strings, and another is from induced tensor perturbations. Induced I mean scalar perturbation inducing tensor perturbation, and mostly about detectable prospects from this kind of scenarios. Okay, so this is the outline of my talk. I will just briefly comment on few of the cosmic sources that are available for stochastic gravitational wave background that can be detected. Then I'm going to move to topological defects, how topological defects can form and lead to gravitational waves, and how this can act as a source to probe pre-Big Bang nucleosynthesis universe, the primordial universe, which we all like. And then particularly this pre-Big Bang nucleosynthesis universe involving very light primordial black holes, which can drive early matter domination era, how that can be probed using gravitational waves from cosmic strings. And then in the second part of the talk, the program is similar, but instead of cosmic strings, we have scalar perturbations at the first order, leading to inducing second order tensor perturbations, and particularly for primordial black hole, we will see very unique gravitation wave signals which can be probed and detected in the next generation gravitation wave. And then if I get time, I can also spend a little bit of how this can also probe or act as a probe for baryogenesis and leptogenesis and dark matter from primordial black hole decay, and maybe a little bit about the recent nanograph gravitation wave detection, which they have observed to see a signal, and then I will try to conclude. Okay, so this is a picture we all know. We all believe there was a hot Big Bang, and some point of time there was an inflation where the very, very small objects and perturbations became very, very large, which we called inflation. And then some point of time we have seen the Big Bang. We have observations for Big Bang nucleosynthesis, which is the radiation dominated era. And after that, there have been the photons, which have called decoupled from the primordial plasma, which we call it as cosmic microwave background, and we observe it. And after that, stars and galaxies and various complicated looking structures started to form. And here we are today at which we see the, here we see the universe today, which looks very, very complex. But the important point to appreciate here is that before this cosmic microwave background, we do not have any other way to probe this period, this period of primordial universe, which is, let's say, at the end of inflation, but the beginning of the radiation dominated universe. There is no other way to probe gravitation wave from such sources of inflation. There can be many sources here, of which I will list after this, can act as a probe from of any event or anything that is happening in between this period of end of inflation and beginning of radiation dominated universe. Okay, so this is just saying the same thing, and how to understand the pre-Big Bang nucleosynthesis universe, and gravitation wave can be one of the sources. And there are many theory motivations to probe this kind of scenario. There can be early matter domination in the form of moduli field, or can be some of other field. There can be cosmological phase transition, new degrees of freedom, multi-field inflation, and many reheating scenarios which can occur during this phase, end of inflation and beginning of radiation domination. But there is no other constraint, there is no other probe apart from this possible gravitation wave, which I'm going to show you here. So these are a few of the sources of gravitational wave which I've listed here. So gravitational wave from astrophysical sources, MARGERS was first detected in 2016. This gives us a new window into exploring the early universe, and there are many sources of cosmological origin from gravitation wave from inflation, from phase transitions, from reheating and preheating, from various graviton-Bremsstrahlung events, from topological defect like cosmic strings, monopoles, the domain walls. There can be non-topological solitons as well, and there are many other sources. Let's not go into details, but just to give you a soft introduction of how this gravitational wave work. It's very similar to the electromagnetic theory. In electromagnetic theory, you have a charge, and when the charge undergoes some acceleration, electromagnetic waves are radiated. These are electromagnetic waves oscillating up and down. And then in context to gravity, this charge, you can imagine the analogy being the mass, and when this mass undergoes acceleration, it emits gravitation waves, and this gravitation wave is nothing but a squeezing and stretching of space and time in various forms. And when you put a gravitational wave detector in space, and you can see this squeezing and stretching of space-time as we do it in our interferometer, and then you pick up and say that, look, there has been source of gravitation wave that pass through that. And regarding the algebra of cosmic gravitation wave, how do we do it? Usually we take a FRW like kind of a metric with a conformal scale factor with conformal time A, as you can see. Then you perturb around this background metric with tensorial degrees of freedom, h mu nu. Then you write down the Einstein equations of motion for this h mu nu. You solve them. So in Fourier space, they look like a plane wave solution, and that's why you conclude that these are gravitation waves propagating in space and time. And then what you do is after you find out the solution of this Hij, you take the first derivative Hij dot, take a special average of Hij dot, and then you say that this is the gravitational wave energy density with a particular spectral shape that can be measured in your next generation or current experiments. Just a point to note is that this Hij depends upon this conformal time tau, and when you inverse this is a function of then a frequency. So you can have gravitational wave energy density with frequency behaving as a function of time. An example I'm going to show you. So this is one typical example from gravitational wave from local cosmic strings. Remember that cosmic string is nothing but a classical solution, is a topological defect formed in early universe, particularly when you have some local gate symmetries being broken, it gives rise to this topological defect cosmic strings, and they can radiate gravitational waves in this form. So on the y-axis, I plot gravitational wave energy density, amplitude, and the x-axis is the frequency. These colored shaded regions are various gravitational wave detectors, current and future planned, which can pick up this corresponding amplitude and corresponding frequency if they lie within this region. Some of them are pulsar timing array-based detectors, some of them are interferometer detectors. Among the interferometer-based detectors, you have ground-based interferometer-based detectors like LIGO, which I show here, or you can have space-based interferometer detector, LISA, which is going to start in the next 10 years. But the most important thing is that various frequency ranges need various detection strategies, and you can cover a wide range of frequency, as you can see, with respect to gravitational wave amplitude. So for a typical cosmic string, the black line here represents the spectral shape as a function of frequency, as you can see. So this shape for higher and higher frequency, you can see it remains more or less flat. That means no matter how you change the frequency, this the amplitude of the gravitational wave remains flat. So therefore you call it the gravitational wave from local cosmic strings is scale invariant, because no matter how you change the frequency, it remains flat. And these numbers here, 10 to the power 15, 14, represents the scale of the symmetry breaking. So if you have a scale of, you want symmetry breaking of 10 to the power 15 GeV, 14 GeV, 12 GeV, this is the prediction of the gravitational wave. And you can see for some of these symmetry breaking scales, some of the detectors like LISA and BBO will be able to pick up the gravitational wave spectral shape and conclude there was an early universe symmetry breaking which led to gravitational wave. So this is just one example, but I also told you there are several sources of cosmological gravitational wave. For example, instead of imagining a local symmetry, you can also have a global symmetry, and the global symmetry will lead to a global cosmic string topological defect, and the gravitational wave spectrum is not the same as in the case of the local string. So you can see there is a dependence upon frequency here. The scale of symmetry breaking is 10 to the power 15 and 14, which will give us detectable gravitational wave in this next generation experiment. So the point to appreciate is that each gravitational wave source gives predictions for gravitational wave spectral shapes which are different from each other. So once we start to measure this from the gravitational wave spectral shapes, that is whether they're flat, whether they have a dependence of frequency, we will be able to distinguish whether there was a global cosmic string or a local cosmic string or inflation and a bunch of stuff like that. So I'll just skip the next few slides, but the main point to appreciate is that you can have other sources, like I told you, like you can have domain walls, the spectral shape of which will look like the spiky feature. Then you can have inflationary gravitational wave, first order tensor perturbations, second order tensor perturbations, and the shape here looks like in the yellow and the red line. These are also dependent upon your models of inflation. You can write down models of inflation where these shapes can be boosted and can be detected in next generation experiment as well. Similarly, you can have sources from reheating and preheating. This black line here represents the gravitational wave from preheating. Again, just a point to appreciate that each of these shape is different from each other. So once you measure this spectral shape in future, you will be able to know whether you had a cosmic string or a preheating or a reheating that you're observed. So let's just skip a few of these. So you can also have graviton-Bremsstrahlung, you can have cosmological phase transitions, and each of them will have its unique spectral shape which can be detected. Okay. So now coming back to this question of probing the pre-Big Bang nucleosynthesis universe. Suppose you are having a source of gravitational wave. In this particular example, we will focus on the gravitational wave from cosmic strings, which just to remind you how it looked like. So this black lines here represents the gravitational waves predictions from local cosmic strings, assuming radiation dominated universe, which means that there was a period of inflation. Inflation stopped. It gives rise to a radiation dominated universe. Then you go on and compute the gravitational wave predictions from local cosmic strings, and you will find this signals which looks completely flat. So now we want to ask this question: what if the inflation did not end up having a radiation domination? What if you had a brief intermediate period of matter domination, let's say, or some other non-trivial equation of state, which is not gives you the radiation combination index. So this is the question we want to ask. But before we answer this question, just a primer on what are basically cosmic strings, if some people are not familiar with this. So cosmic strings are stable one-dimensional topological objects. You can just think of like a classical normal string. It has its own string tension, which gives us basically the energy density stored in the cosmic strings. You can have many predictions from F strings, D strings, or you can have local U1 symmetries or global U1 symmetries, which gets broken and form these various interesting solutions of cosmic strings. As you can see, I've rewritten the Lagrangian here. So once this phi gets a wave, it breaks a U1 symmetry, and therefore it gives rise to the flux of cosmic strings. So now how to write this cosmic string? So once you write down the web, you can just have the web of the phi field and the phi web. So since this phi is a representation under this complex U1, so it's a complex field. So it has a phase, and this phase can take various values in various domains, and this gives rise to nucleation of cosmic strings, which I show here. So you can see on this figure, on this cartoon, you can see the various theta values at various places, and in between these boundaries of these various theta values, you are nucleating basically cosmic strings, and this mechanism of cosmic string formation is known as the Kibble formation. So only at a critical temperature, you can imagine having a symmetry getting restored or symmetry getting broken, and that typical cosmic and this typical temperature corresponds to this boundary via the Kibble mechanism, leading to the formation of non-trivial cosmic string like formation. So once this string starts to form, it will have its own dynamics. For example, it will oscillate, it will cut each other. So you're basically forming various shapes of cosmic string, as you can see. So once this cosmic string starts to have these dynamics, then depending upon the string tension, remember I told you that each cosmic string is characteristic by a cosmic string tension denoted by this parameter mu, and this G is nothing but the gravitational Newtonian constant that you can see. So if you have a larger cosmic string, then this dynamics will be larger. You will have more strings getting formed and more dynamic strings interlooping and cutting each other. And these cosmic strings with its own energy density will get transferred into the gravitational wave energy density. And that when we calculate the gravitational wave energy density coming from the cosmic string, assuming this cosmic string tension will give us the spectral shape of the gravitational wave. So these are very nonlinear effects. People do this kind of string loop dynamics on the lattice. This is how a typical how the string looks like on the lattice. These are various dense, you can understand these are various density regions due to formation of cosmic strings and its own dynamics getting cutting and intercommuting with each other. But what we require to, in order to calculate the gravitational wave or have a decent prediction of gravitational wave, is to understand how these nonlinearities take shape as a function of the cosmic string tension and of course of the background, which I'm going to show you here. So as I told you, gravitational wave will be emitted from these oscillating cosmic strings as in bursts, and this gravitational wave will form a stochastic background, which we can measure in our interferometer based or pulsar timing array based gravitational wave detectors. So the larger the string tension, the larger of the energy density of emission of gravitational wave, which I already told you. This L, capital L, represents the length, the coherent length scale between two strings. So you can see the larger the length scale, the less is the frequency. And these numbers, as you can see here, are completely, this dependency number are completely gotten from this lattice simulation which I showed. It is very difficult to understand otherwise. But once you get this number, it is very easy to compute the number of loops or the number of oscillations of loops that you form in the cosmic strings. It is usually represented by what is known as the Nambu-Goto action. And as I show you here, so as you increase the tension, so if you have a string with very large tension, as you can see, this will quickly deplete the energy from the cosmic string sector to the gravitational wave energy sector, and then you go and compute the gravitational wave from this. And then of course it has its own efficiency factor, how good or how quickly they will transfer the asymmetry, again coming from this simulation. But once you put some trustable numbers from various simulations that people have done, then the gravitational wave frequency, you can write it in terms of the number of strings or number of modes the cosmic strings have got, whether it's very large or very small. You can turn and write down as a function of the redshift factor times the length of the string or the size of the string. So this redshift factor comes because after the gravitational wave has been emitted from cosmic string from early universe, it needs to propagate from early universe to late universe, and we observe it today. So if you write down, put all story together, this is the energy density of the gravitational wave that you write down here with these various efficiency factors coming from lattice simulation. But the important point to note is that this redshift factor contains the pre-Big Bang nucleosynthesis information, which we were alluding to probe or to test. Because of its propagation of gravitational wave coming from cosmic strings which are formed during this era, which can be radiation dominated or matter dominated or some other non-trivial equation of state, these will carry the information, the spectral shape of the gravitational wave will carry the information of this redshift factor coming from such non-trivial pre-Big Bang nucleosynthesis era, which you have no other ways to probe. Okay, so that being said, let's look at how the cosmic string spectrum look like. I already showed you this black line represents the cosmic string spectrum if you had assumed the radiation dominated universe after inflation had ended. If you have a matter dominated universe, which is motivated from various moduli domination or string theory consideration, then you can see the blue line, which shows a dip in the spectrum of the cosmic string. So what is happening is that this matter dominated era has a non-trivial equation of state, which is different from radiation domination. So it is creating more and more Hubble friction. So when you are solving the equations of motion for cosmic strings, the Hubble not being that during radiation dominated universe, but that being due to matter domination is more and more stiff and more and more has a Hubble friction. Therefore, you have a suppression. You have a suppression of the dynamics of the movement oscillations of the strings, and therefore you have the spectral shape which goes down from here. And then once you know the shape which has gone down, from here you can conclude at what point of time, because this frequency here on the x-axis also represents the timing backward. So earlier and earlier time represents higher and higher frequency of the gravitational wave. So from the spectral...
Sorry for interrupting you, but you have a question.
Yes, please. Please.
Yes, a very quick question.
Yes.
When you studied the matter-dominated case, you were just working with omega m equals 1. Now, the question is that just from about redshift of 1 until we actually see the signal, omega lambda kicks in. Does that change things in any way?
Sorry, could you repeat your question again? So you're saying that...
I'm sorry. When you calculate the matter-dominated universe, you're working with omega matter equals 1.
Omega matter equals 1?
Omega m, yes, that it's 100% dark. It's just dark matter.
Okay, yeah.
And no dark energy.
Right, yes.
Except when the signal reaches us, it's traveled from redshift 1 onwards.
Yes.
In a cosmological constant dominated universe. So how does that actually affect what you've done? I mean, this equation you've got, h squared is 8 pi g over 3 times rho. You're taking rho just to be dark matter.
Right.
So I'm only asking, the signal that we see will be modified in some way by dark energy. And I was just wondering how it affects the curves that you showed.
Yeah, so just to remind you, so this frequency here also represents the time, right? So now we are only concentrating on before pre-Big Bang nucleosynthesis. That is before the time the radiation domination has begun. So we are talking about early matter domination and, if possible, early other state domination. So the dark energy domination and late time matter domination that you're considering is far on the left. So any modification you do here after the radiation domination has started, matter radiation equality, matter domination, late time matter domination, and late time dark energy domination are far here in these frequencies. However, in this context, the spectral spot I'm showing you is a matter domination before Big Bang nucleosynthesis or before the radiation, the early radiation domination has occurred. So any change here will not show up in the spectral shape that you had given here. But we have evolved the whole system through the radiation domination to matter domination to dark energy domination via these equations which I show you here, because these are the redshift coming from each of those errors and each of those shifting of time.
Oh, so you're using the real A of T?
Yes.
Ah, okay, thank you. That was all I wanted to know. Thank you.
Okay, so now with this, just to tell you, so from this spectral break, that is the time of the frequency at which this starts to go down, is a unique information giving us, once we measure it, suppose we measure and find it, will take us if and at what time there was a period of matter domination in early universe. And from that, you can conclude, okay, you had some string theory scenarios giving rise to moduli field, moduli gave rise to matter domination. At what point of time that matter domination was there, that matter domination went away and gave rise to the radiation domination. So this is one of the unique ways to catch the information before Big Bang nucleosynthesis, which otherwise you do not have any other handle to catch. Okay, now let's move on since my time is limited. So what more you can do, you can convert this gravitational wave did. So I just showed you the spectral shape, but you can calculate what is known as the signal to noise ratio for each of these gravitational detectors and turn this plot around for the detector versus this frequency space. So you can see for various frequencies and various temperature representing the change from matter domination to radiation domination with various string tension mu here within the color coding, which gravitational wave are probing which regions of the parameter space. So this is just an exercise that you can convert that simple gravitational wave spectral plot to individual detector, gravitational detector, LISA, Big Bang Observatory, or Einstein telescope, covering which region of the parameter space, assuming some string tension, of course. Okay, so now with that being said, the idea is that now we want to bring the story of the primordial black holes and what we can say regarding the primordial black holes. So now that being said, now we can imagine that instead of having a generic early matter domination like a scalar field or a moduli field, you can also imagine having primordial black holes getting formed in our early universe, and they come to dominate the universe at some point of time. And once you have primordial black holes dominating the energy budget of the universe, then it is as good as any matter domination. And then the primordial black hole will have its own Hawking evaporation. So it will very drastically go away after some point of time, depending upon its own properties like the mass of the black hole or the mass fraction of the black hole. Determined by its own property, you will create a matter dominated era driven by primordial black hole, and then it subsequent decay of the primordial black hole giving rise to the standard radiation dominated era. So now with this information at hand, we want to convert or understand constraints on this primordial black hole, mass fraction and the mass of the primordial black hole from this kind of scenarios. So just to show you how this can be done, I just like to skip some of this because I already told you these are some details, but let's quickly move towards, okay. So let's move towards this primordial black hole. So we know that the primordial black hole mass of certain number and the mass fraction of a certain number will give rise to early matter domination driven by primordial black hole. And these are usually given in terms of beta, which is the mass fraction on the y-axis, and the mass of the primordial black hole in grams or in solar unit. And these are some of the current constraints which are already there from micro lensing, gravitational lensing, electromagnetic era, and many other stuff. But in some regions, you can see, especially these light regions, 10⁴ and 5 gram and 1 gram, this light region, there is hardly any constraint because this is the region which can source this early matter domination by primordial black hole. And since this is pre-Big Bang nucleosynthesis era, there is no other way to constrain. There is no other handle to constrain this. So once you start having that primordial black hole region, so you can basically draw a line between these two independent parameters of primordial black hole, one being the mass of the primordial black hole on the x-axis and y-axis being the mass fraction. That is, if this number is 1, then you say that this constraint, this is the whole component of the energy density of the universe. And this is number is 10%. That means that only 10% of the energy density of the universe is sourced by the primordial black hole. So these two independent parameters, beta and m, is what you want to put your constraints coming from various scenarios, but very light primordial black holes has no constraints. So this red line basically discriminates the regions where the primordial black hole, above this red line is where the primordial black hole can drive an early matter domination of the universe, because you want to make this energy density dominate over the already present radiation dominated background in the universe. So this red line represents above the various parameters, the various values above this red line represents where the primordial black hole can drive an early matter domination era. Just before showing you the results, I want to show you the spectra of the gravitation wave coming from from cosmic strings, which I already showed you. So depending upon how long this duration of primordial black hole matter domination was, this gravitation wave from spectral shape will look like this. So this black dashed line I already showed you is standard gravitation wave from cosmic string in radiation dominated era. Suppose you have one e-fold of matter domination or one e-fold of primordial black hole domination. By e-fold, I just mean the ratio of the scale factors. So you can see how the spectral shape change. It gets this unique feature of this plateau feature, which can be detected in some of these gravitational wave experiments, as I show you here. But suppose you increase the duration of matter domination from 1 e-fold to 2 e-fold, 3 to 7, then you can see the spectral shape getting changed. So once you measure the spectral shape, once you see the spectral shapes, from here you can conclude how long the duration of matter domination was. And from here you can conclude what values of beta and what values of the mass of primordial black hole could have sourced such early matter domination. And you can put constraints, just like you can put constraints here. These are astrophysical black holes, but now you can put constraints on this pre-BBN black holes, which otherwise you have no other constraints. So this is the final results coming from the cosmic string. This is a plot of beta versus mass of primordial black hole, which I already showed here. And these are the detectors, LISA, BBO, Einstein telescope, which can probe these regions of the primordial black hole, acting as a complementary probe to other primordial black hole observations, which I already show you. The point to appreciate here is the fact that these are very light primordial black holes, 10 to the power 4 gram and 5 gram and 6 gram and 7 gram, which means that these primordial black holes have no other ways to test it. So if they existed in early universe, they would have gone away today because of its decay via Hawking radiation. And there is no other way to catch such signals except for this gravitational wave, which we showed today. So I come to the conclusion. Okay, so here is another plot which we included also the spin of the primordial black hole. So I have been assuming that the initial spin of the primordial black hole to be 0. But if you have a very large primordial black hole spin, the results slightly change, the spectral shape also slightly change, not a major difference, but you can in this principle probe such spins of such initial primordial black hole. For a maximally rotating spin, I show for 099 A star. For a K black hole, you can see that how the spectral shape looks like, and you can put bounds on the spin of primordial black hole from here. So this brings me to the conclusion of the first part of the talk. I'm running short of time, so let me just quickly summarize. Gravitational wave from cosmic string provides a very natural and solid candidate to test the history of the universe, particularly pre-Big Bang nucleosynthesis. And there is no other way to test other than gravitational wave, as we see here. Particularly for early matter domination, it gives a very unique gravitational wave spectral shape, which cannot be reached by any other means. This is some plateau feature which I showed you. Until now, there was only this idea that the temperature of early matter domination could be measured. But now with the spectral shapes information, we can also derive constraints on how long the matter domination was, when it started, when it stopped, because that is controlling, and that is being controlled by the mass fraction and the mass of the primordial black hole. I didn't go into details, but these are some of the details which help us make those conclusions. But to tell you, primordial black holes of mass 10 to the power 4 gram to 10⁹ gram can be looked or searched in LISA, and for 10 to the power 3 and 9 gram for local cosmic strings can be searched by Einstein telescope. I'll just pause for a few seconds to see if there are any questions, or else I would like to move to the second part of the talk.
Are there any questions for this part? Okay, but unfortunately, you have not so much time for this second part of your talk.
Yeah, so I still have 15 minutes, right?
You can do it in 5 minutes. It will be really good.
Okay. Okay, so the second part of the talk is basically a program that we started in the first part of the talk, but now the source of gravitational wave is different. Now it's scalar perturbations. Let's call it inflationary perturbations. So inflationary perturbations can also source gravitational wave. Scalar perturbations can induce tensor perturbation, which I show here. So this is just a metric involving scalar perturbations. And if you write down the equations of motion, you can see the scalar perturbations has a source which can induce tensor perturbations at the second order. So this is a second order equation of motion. Please remember, if you follow single field slow roll inflation, the first order tensor perturbation is already flat and not within the reach of the gravitational wave experiment. But however, if you have a source of scalar perturbations which is large, they can induce large second order tensor perturbation, which I show in this equations of motion here. So this is how the solutions of the second order tensor perturbations look like. If you solve it in a radiation domination era, the gravitational potential, the phi which I show here, it has this oscillating solution, and during the matter domination era, it has this constant solution. And this can be very easily understood in terms of the equations of motion. So you can see, you write down the equation of motion. If this guy remains constant during matter, like for example matter domination, then this basically has a decaying solution. And if this guy has this radiation domination solution, then it has a oscillating exponential solution. So what it means is that, again, we want to ask the same question. Suppose there was an early matter domination or early primordial black hole domination, then the second order tensor perturbations, which are sourced by these scalar perturbations, will have this significant change from its standard exponentially decaying solution to an oscillating solution. And this change in the solution of the gravitational wave can give us very interesting signals coming from early matter domination or primordial black hole domination universe. Since I don't have much time, I would just like to focus on the result. So this is how, for an example of how such primordial black hole density fluctuations can lead to such change in the solutions of the perturbations in the equations of motion show you. So on the right plot, you can see there is a big jump in the amplitude of the gravitational wave, and this jump is happening precisely because you are changing from this matter domination era, which has a constant solution, to a radiation domination era, which has an oscillating exponential solution, because of the change from matter domination era to the radiation domination era. To put it finally on the plot, if you have a primordial black hole, which I already told you and showed you that is for a primordial black hole of such as mass can give rise to this early matter dominated era. So after let's say that after inflation you have a radiation dominated universe. Then at some point of time the primordial black hole starts to dominate the universe. So first you have a change from radiation dominated universe to a matter dominated universe. Then due to Hawking evaporation, the primordial black hole decays and you get back radiation dominated era. So first you have early radiation domination, then you have primordial black hole domination, and then you back to standard radiation domination. So because of 2 times changing from radiation to matter domination and then to matter domination to radiation domination, you have see this unique 2-peaked signal, which I show you here. For a particular choice of mass, let's say 100 gram and the mass fraction of a primordial black hole, you have these 2 peaks, one here and one here, as you can see. These 2 peaks represents, first peak from the right represents when the radiation dominated universe gave rise to primordial black hole dominated universe after it starts to dominate the universe. Then the second peak on the left shows the time when the primordial black hole got evaporated by Hawking evaporation and gave rise to the late time radiation dominated universe. So from this unique 2-peak signal, one can able to constrain generic early matter domination as well as unique primordial black hole mass fractions and masses, which can catch this signal, some of which are detectable in the next generation gravitational wave in detectors, as I show here. And this is how the plot looks like. This is the plot I have basically derived these constraints from. So these are some benchmark points from primordial black hole mass fractions and masses. So I have reconsidered them in the generic plane of primordial black hole mass fraction and primordial black hole mass, and you can see these very light primordial black hole, 10⁻³ gram, 4 gram, 7 gram, 8 gram, are being probed by these gravitational wave detectors like LISA and Einstein telescope, and some of them will be constraining the parameter space. Again, the point to appreciate, there is no other probe in this mass range. There is no other way to probe because this is pre-Big Bang nucleosynthesis, this is early matter domination, and we have no other way to constrain or probe this kind of parameter space. So since I don't have much time, I'll just show you what happens if you include a spin. So if you include a spin, the plots I've been showing you for 0 spin, if you include the spin, you see the shift in the spectrum, gravitational spectrum. This is happening because once you include a spin, then it affects how long it takes for the primordial black hole to decay away or to evaporate away via Hawking evaporation. So for a larger spin, you need more time for the primordial black hole to decay away. So that is how you see the shape change in the spectral shape, because it takes more and more time for the Hawking evaporation to completely deplete the energy fraction primordial black hole. And from here, of course, you can put constraints on the spin of primordial black hole from various gravitational wave detectors, as I show here. Again, something that is otherwise not constrained. There is no other way to constrain the spin of such primordial black hole or distribution of spin of such primordial black hole or mass distribution of primordial black hole. There is no other way to constrain other than the gravitational wave, which I have been showing here. So now this brings me to the last part of the talk. I didn't get time to explore baryogenesis, but we can understand from a similar program, you can constrain baryogenesis mechanism, dark matter mechanism, dark radiation mechanisms, which is precisely given by Hawking evaporation of primordial black hole. You can constrain such scenarios. You can constrain dark matter scenarios, dark radiation scenarios, baryogenesis scenarios coming from such primordial black hole decay via the gravitational wave. So double peak shape of the gravitational wave spectrum proves that 2 times, one time of primordial black hole formation, which starts to, then after which starts to dominate the universe, and primordial black hole evaporation, that is the change from primordial black hole dominated universe to the radiation dominated universe. Since primordial black hole also can act as a source for baryogenesis, you are also probing baryogenesis in this manner. For that, you require some typical numbers, which I didn't get time to show you. Then that means that this gravitational wave put constraints on the primordial black hole mass of this range, very light. There is no other way to test this. Of course, there are questions related to what kind of perturbations are we sticking to linear perturbation theory, and these kind of questions and uncertainties are always there with such calculations. But with a grain of salt, if you believe that this is the mass range which we can constrain using gravitational waves. For particularly satisfying baryogenesis, the number of matter-antimatter asymmetry, then the gravitational wave will be able to constrain primordial black hole of mass ranges larger than 10⁻⁴ grams. Again, the spin of primordial black holes can also come in. It can play a non-trivial role in the lifetime of a primordial black hole, which dominates the universe and decay. And from spin of primordial black hole, you also saw the change in the spectral shape. So the spectral shape with the spinning primordial black hole and with non-spinning primordial black hole was completely different. So once you observe this spectral shape in next generation gravitational wave experiments, you will be able to infer or conclude something regarding what was the spin of the primordial black hole. In case of dark radiation coming from Hawking evaporation of primordial black hole, you can also imagine to have the effect of spin, and this dark radiation can be detected in next generation CMB experiments as well. So in that manner, it's a complementarity study between CMB experiments of dark radiation and the gravitational wave experiment, which I show you here. And also similarly, you can test dark matter production for primordial black hole. And again, just to make the point one last time, such primordial black holes of very light mass ranges, there is no other way to test them, because if they were present in early universe, they would have already gone away due to Hawking evaporation by this time. And we have no other signatures other than gravitational wave, which I showed you in these 2 cases. Thank you.
Okay, thank you very much for the talk. Are there any quick questions? Professor Mannheim, please go ahead.
Yes, thank you for the talk. You didn't have a time to tell us what nanograph has discovered. Perhaps you could do that now?
Yeah, sure. So let me see if I have this. Okay, so first of all, on this plot, just let me tell you this. Let me just quickly show you. Sorry, where is the plot for this? Yeah. So could you see this region written nanograph here?
Yes, yes.
Yeah. So this is the region where nanograph claims to have seen a signal of stochastic gravitational wave of background. So which means that if you have a source of gravitational wave, you could and you have a prediction here, then you can say that that source corresponds to what nanograph has seen, right? So for this second order tensor perturbation, I do not get any source which is coming in this region, because if you put this number less and less, you have other constraint. You can see this number is going high, and this number is already ruled out by some other experiment. But on the other hand, let me show you this spectral shape coming from cosmic strings. So you can see, for example, this plot which I showed you. Yeah, okay. So do you see this plot from cosmic strings, right? So this cosmic string plot, which a particular string tension 10 to the power minus 11 and the temperature at which primordial black hole starts to dominate the universe, you can see the prediction in this nanograph, right? So that means for a cosmic string spectrum, you can see the shape where nanograph has observed the signal 2 years ago, which means that imagine, and this plot has been particularly done, and I show you this here, imagining nanograph signal is correct. We put the string tension and the temperature at which the matter domination starts. In such a manner, you can see this spectral shape, this decreasing and the plateau-like shape in other detectors here. So if you fix the nanograph result, which will fix the initial properties of string and the primordial black hole, which can give rise to the nanograph signal seen by this experiment, then you can conclude what other things you can say in this kind of other experiment. Now to the nanograph signal exact, what do? They have observed certain number of events. So you can see this is a plot of what nanograph has actually observed 2 years ago, 2020 October. So you can see they have these events. They have these events in the plane of gravitational wave amplitude and frequency, and then just try to fit. So then they try to do this power law fitting of various amplitude versus frequency dependence of this gravitational wave signal. So there are very few events, as you can see. The bottom plot which you see is the plot of A, which is the amplitude of gravitational wave, and the spectral index gamma being the frequency dependent, whether it's going as k to the power 3 or k to the power 4 or k to the power 4.5, normalized with respect to some. And this is the fit coming from cosmic strings, which fits the best. So you can see.
I'm sorry, but I suggest to postpone it for discussion session because we have a tight schedule.
Okay, sure. So
So
the main message is that if you look at the signals observed by nanograph, you try to fit it to any source of gravitational wave. Cosmic strings fared the best. Cosmic string gives the best fit to the nanograph result. That's what I wanted to say.
Okay, nice. Thank you very much for the talk. And then let's postpone all the questions to discussion session and invite Brenno Ghiacini for his talk. Can you share the presentation?
Can you hear me?
Yes, we can. Okay, nice. We can see your presentation.
Do I need to put it in full screen mode, or is it good?
It would be nice if you can do full screen sharing, like yeah, Control L normally. Great. So you have 40 minutes for the talk and 5 for questions.
Well, first, I would like to thank the organizers for the invitation for me to present my work. And my talk is based mainly in 2 papers that are listed here. And it works in collaboration with Tiberio De Paula Neto, Leonardo Modesto, and Niccolò Burzilla. And also we have a book chapter that I wrote with Tiberio. That's going to be published probably this year in the book Regular Black Holes, organized by Cosimo Bambi. And some of the material of my talk are also explained in more details in this book chapter. It's not on archive yet, but very soon it's going to be. So my talk has two parts. The first part of the talk is focused on higher derivative gravity. So I'm going to talk about the Newtonian limit and the regularity of solutions in the Newtonian limit, especially the regularity of the curvature invariance and the regularity of the invariance containing covariance derivatives. Let's say the higher order regularity of the solutions. And in the second part of the talk, I'm going to apply some of these results to study the regularity of black hole metrics that are not necessarily obtained as solutions of equations of motion, but general metrics. So in the first part, we have a kind of model, then we obtain solutions or approximate solutions, and we study their regularity. In the second part, we get the metrics from elsewhere, and we study the regularity of the curvature invariance. And then using the finite action principle, we can use this maybe to constrain the model for quantum gravity. So the first part is based mainly on the perturbative approach to quantum gravity, while the second one is thinking on the Lorentzian path integral approach to quantum gravity. So when I say about higher derivative gravity, I have in mind this action here, where we have the Einstein-Hilbert term and the higher derivative operators here. So these are the Weyl tensor, these are the scalar curvature, and in between them we have form factors that are functions of the D'Alembert operator, and these terms contain higher derivatives. And there are many motivations for higher derivative terms. For instance, they appear already when you renormalize quantum field theory in curved spacetime. Then in the gravitational sector, you have counter terms with curvature squared that contains four derivatives. Also, because general relativity is not perturbatively renormalizable. However, the fourth derivative gravity is renormalizable. It's, for example, this action here, where we have these curvature squared terms, it is renormalizable, as it was proved by Stell in '77. And if you add 6 or even more derivatives to the action, you can make the theory super normalizable. Like in this action here, studied by Astorey, Lopez, and Shapiro in '97, where you have, besides the curvature squared terms, also terms containing powers of the D'Alembertian in between the curvatures. However, the higher derivative gravity has a problem that's very well known. That's the ghosts, because usually the higher derivative contains ghost-like modes in the spectrum. This can be seen from the propagator. This is the basic propagator structure of the model, where these functions here, f2 and f0, they depend on the form factors in the action. So the roots of these functions define the massive poles of the propagator. So in the case of the complete fourth derivative gravity, you have not only the massless graviton, but you also have a spin 0 particle, and that's a normal healthy particle, and a spin 2 particle that's a ghost. And if you have a higher order polynomial, you have more ghosts. Well, there are plenty of proposals of how to deal with the ghosts or to avoid them. For example, in the case of Levick gravity, the Faken's prescription, there's also the possibility of having the unstable ghosts. And today and in the next days, we're going to have more thoughts about these proposals. So I'm not going to talk about these in detail. And also there is the possibility of avoiding the ghosts by means of non-locality. In this case, the form factor entering the action is a non-polynomial function, usually with this form, where this hs is an entire function. In this case, the propagator only has the massless pole of the graviton. And the classical solutions of these models with 6 and more derivatives, they have good irregularity properties, as I'm going to show soon. So the basic thing that I'm going to use in my talk is this function here, this f, small fs, that it comes from the action. So it's very difficult to solve the complete equations of motion for models with more than 2 derivatives. Even in the case of steady gravity with 4 derivatives, it's already very complicated, but there are some important works. But with 6 and more derivatives, it's much more difficult. So normally the solutions are obtained in the linear approximation. So these are the linearized equations of motion. Here you see there is the f function that I mentioned before. And in the linear level, we can study the field generated by a point-like mass in rest. And in this case, the metric is static and spherically symmetric, so we can assume this basic form of the metric, where phi and psi are 2 potentials. And instead of working with phi and psi, I'm going to work with chi 0 and chi 2. These are auxiliary potentials, and they are useful because they only depend, each of them only depend in one of the spin components of the field. So the chi 2 only depends on the spin 2 part, and the chi 0 on the spin 0 part. And in terms of these auxiliary potentials, the field equations become this. So basically, we have one equation with labels here, different labels. And after you solve these equations for a chi, you can obtain the original potentials using this formula here. And there are many ways of solving this equation. For example, the Fourier transform method for the Laplace transform. Here we are going to use the Fourier transform, and the potential chi is given by this expression here. Again, we have the small f, that's the basic quantity, the basic function in this talk. So here we have some examples for the potentials. In the case of the 4th derivative gravity, that's also known as steady gravity, the potential has Yukawa-like correction, some coefficients. And for another example, in the case of the exponential non-local gravity, with this exponential form factor, we get this potential, that's the error function. And it's interesting to see that all these potentials are finite at r equals 0. And in general, it can be shown that if a model has higher derivatives both in the spin 0 and the spin 2 parts, then the Newtonian limit metric sourced by a point-like mass is finite. But it's very important for the model to have higher derivatives both in the spin 0 and in the spin 2 part. If it's only in one of these sectors, then the potential is not bounded. But this is not the true happiness, because the finiteness of the metric doesn't mean that you don't have curvature singularities. For example, if we expand, if you have regular potentials, phi and psi, and we expand them in Taylor series in a formula like this, we can calculate the Kretschmann scalar, for example, and we obtain this formula here, and we see that there are diverging terms that depend on the first order coefficients of the series expansions of the potentials. Here we have psi1 and phi 1, and also here. So then we have a regularity condition that in order for the Kretschmann scalar to be regular, this condition must be satisfied. This limit must exist. So in order to see if the metric is regular or not, in the point of view of curvature singularities, we needed to check the terms of order R in the series expansion of the potentials. So, for example, in the case of the general polynomial derivative gravity, the potential is given by this expression. And well, here these A are coefficients that are determined by the partial fraction decomposition of the function 1 over f. And so the dependence is only in this term here and on the Bessel function. And if you expand this in Taylor series, you get this expression. And you see that the divergent term on the potential, this 1 over r, is proportional to 1 minus the sum of all the A1. And the term linear on R is proportional to this quantity, S1 minus S2. Here is also some combinations of these coefficients. And it can be shown, as we showed as we did in this paper, that if the function f is of order at least 1, that means in fourth derivative gravity or higher, then there is this combination of the coefficients that cancel the 1 over r singularity of the potential. And if the f is of order even larger, at least 1, at least 2, then the S1 is equal to S2, and the term linear on R vanishes. So this means that if you have a model with at least 4 derivatives, you have finite Newtonian potentials. And if you have a model with at least 6 derivatives, you have a regular Newtonian limit that is without curvature singularities. So here I'm going to introduce a definition that if the metric doesn't have the divergent term, if the potential doesn't have the divergent term, I'm going to call it zero regular. That's regular in the normal sense. And if the potential doesn't have the term linear on R, I'm going to call it one regular. And in this case, this means that there's not curvature singularities. And we can extend this to 2 regular, 3 regular, and so on, to mean that the first odd power in the series expansion of the potential is higher. So this is, so far we see that the regularity of the curvature invariance, it's not a consequence of the non-locality or ghost-free condition, because the case I've just showed, it's a local theory that has regular curvature invariance, and it also has ghosts. But the regularity is consequence of the improved propagator in the UV. So it doesn't matter if the theory is local or non-local. Both types of theory can have regular curvature invariance. And this is the case of many non-local theories that were studied in the literature. So there are many works that studied particular models of non-local higher derivative gravity that have regular curvature invariance. But not all of them have regular curvature invariance. And to see this, how we can prove this in a more general sense, we can use the effective source formalism. That is, instead of working with that equation for the potential, that's a modified Poisson equation, we change the source, we invert the operator here, and we get a normal, traditional Poisson equation with a modified source. So we pass the effect of the higher derivatives to the source. So we get, instead of a delta source, we get an effective delta source that has this form here. And from this effective delta source, we can construct an effective mass function. That's the effective mass inside a sphere of radius r. And we have the potential that's then obtained from this formula here. And let me see, there is.
Sorry, may I interrupt with a second?
There is a question from Alexei Kush.
Oh.
It's a very silly question for 1 second. How do you know that your operator is invertible on the class of functions which you consider?
Oh, this, well, you shouldn't apply this to any theory. In the case of the polynomial theories, it is safe. And also in the non-local analytic case, because you can define them by series expansion. And since here we are considering the static limit, you also don't have the problems that appear by doing these theories in Minkowski, the dynamical theories. That this is a more complicated problem, but in the static limit, it is safe.
No, whatever your theory is, if it is exponent of the Lambertian and you invert it, you change the sign, and you will hardly find appropriate function. No, you will, but it's maybe not what you want from your rho.
Yeah, you can define it by series, and there are problems of convergence. Some problems of convergence, for example, if you have the squared, the box is squared, then it's better, like as it was shown in the paper by Zulimbach long ago. But this mainly, I think, on the dynamical case. But in the static case, you can do it by series. It's safe.
I think static or dynamic doesn't make any difference here. But okay, if you are sure that it's possible, okay, good.
Yes.
Thanks.
Yes. And okay. So we'll get the effective source. And then we can prove this theorem that relates the behavior of the function f to the behavior of the effective source, to the degree of regularity of the effective source. So if the function f grows at least as fast as k to the 4 plus 2n for a certain n in the sufficient large k, then the effective source is at least n regular. This means that the potential is at least n plus 1 regular. And as a corollary, if the function grows faster than any polynomial, like in some cases of non-local gravity, then the potential is an even analytic function, and it is infinite regular. That means that, well, it doesn't have any odd power in the series expansion. This is the case, for example, in the case of the exponential of box, of the exponential of box. So you have the effective source, that's the Gaussian, and you have the potential, that is the error function over R, which is even, and this is also even function. This increasing regularity of the source can be viewed in this graph. Here we show the behavior of the effective source for different models. So the blue line is the case of stellar gravity, that's like fourth derivative gravity. So you see that the source is still diverges, but the potential is regular, but the source still diverges. If you have 6 derivatives, then the source is finite, but its derivative is not 0 at the origin. So it is regular, but it's not 1 regular. In the case of 8 derivative gravity, however, then the derivative goes to 0, and you have it is 1 regular. And in the case of the exponential gravity, it's also infinite regular, so we have this behavior. And as a second example, now as a non-local model, which effective source is not infinitely regular, is the case of the Kuzmin form factor. Because the Kuzmin form factor is defined by this function here, And it has a polynomial behavior in the UV. So when k goes to infinity, you have this formula here. It tends to a polynomial, and depending on the value of lambda, the convergence is better or not. So in the case of lambda equal to 1, you have the theory that tends to stay in the UV. So then the potential is finite, but the derivative doesn't go to 0, as is shown in the second graph. And but for the others, for lambda equal 2, 3, 4, the derivatives go to 0. But if the lambda is 2, then the third derivative doesn't go to 0, and so on. So it's not that in all non-local models you have the infinite regularity. And well, there's also another example that we consider. That's the case of the fourth derivative gravity with logarithmic correction. That this logarithmic correction can come from quantum corrections, one-loop quantum corrections, for example. And in this case, it's more difficult to evaluate the potential because you cannot use partial fraction decompositions. And but you can obtain the behavior of the function near r equals 0 by means of some approximations. All the details are in this paper here. And in this case, the logarithmic correction improves a little the behavior of the form factor, but it's not enough to regularize the curvature of similarity. So the potential is finite. Its derivative goes to 0, so it's different than without the log. Without the log, the derivative goes to non-zero constant, but with the log, it goes to 0. But the curvature still diverges because the effective source diverges. So this can be seen in this graph. Here we compare the case of the Newton potential, the pure fourth derivative gravity, and the fourth derivative gravity with the log. So we see that the derivative goes to 0, but still very slow. And in the case of the sixth derivative gravity or higher plus the logarithmic correction, then it doesn't change too much because the log is subleading with respect to the polynomial terms. So here in the case of sixth derivative gravity, see that there is more shift, but it doesn't change the degree of regularity. But of course, there is a problem that's going to appear when higher derivatives are taken into account, because this log introduces a non-analytic behavior. So if higher derivatives are taken at the solution, then you're going to have a divergence coming from the fact that the log is non-analytic. So these ideas of the higher order regularity makes us question how we can apply these to curvature invariance, to higher order curvature invariance. Because we saw that the metrics that are one regular have finite curvature invariance without covariant derivatives. Then it would be interesting to have what's the relation between the order of regularity of a metric and the number of covariant derivatives that the curvature invariant can have, so that it's still bounded. And in fact, the absence of the term linear on R on the series of the metric is not enough to regularize these order scalars, for example. This is easily seen in the case of the box R, for example. That's you see that the box n to the box to the n R has a term here that diverges if the coefficient, if the derivative of order 2n plus 1 doesn't go to 0. So there is a general theorem on that that we showed in this paper here that says that if the potentials chi, they are n plus 1 regular, then all the curvature derivative invariants with at most 2n derivatives of the curvature tensors are bounded. This is a theorem that works in the linearized limit. In the case of, I'm going to talk a little bit later about non-linearized case, but it's still open. So for example, if the action contains 20 plus 6 derivatives of the metric, then all the curvature derivative invariants at the Newtonian limit have at most, with at most 2 n covariance derivatives are regular. So in the case of n equals 0, we have the 6th derivative gravity. That means that the first term, the first odd power in the Taylor series of the metric is r to the cube, and then the term box r diverges. If n equal 1, we have the 8th derivative gravity, then the first term in the series of the potentials is at order 5, then the r squared and the box r are finite, but box squared are diverged, and so on. So these are the conclusions of the first part of the talk, is that theories with more than 4 derivatives in both spin 2 and spin 0 have not only a finite Newtonian potential, but also a regular non-relativistic limit, that is without curvature singularities. In this sense, the divergences are softened when we go from 2 to 4, and then to 6 and more derivatives, both at quantum level and at the classical level, because at quantum level, we go from general relativity, that's non-renormalizable, to 4th derivative gravity, that's renormalizable, to 6 and more derivatives, that's super-normalizable. And from the classical side, we have, in the case of 2 derivatives, singular potential and singular curvature. In the case of 4 derivatives, finite potential, but still curvature singularities. In the 6 and more, we have finite potential and finite curvatures. And depending on the number of derivatives, even higher order regularity. And this higher order regularity can be achieved depending on the number of derivatives in the action. And it's possible to have the infinite regularity in some types of non-local theories, but not in all of them. And also the regularity of the curvature invariance is not a consequence of non-locality or the ghost-free condition, but of the improved behavior of the propagator in the UV. And this is a motivation for the investigation of the full theory in the nonlinear regime. So far, I know of only one work by Bob Holdom about static spherical symmetric solutions in theories with 6 and more derivatives. But still, there are more to be done.
Excuse me,
and
there is a
in the second part of my talk, I'm going to apply.
There was a question.
Yes.
For the part.
Question on the first half of your talk. Thank you for the presentation. The Schwarzschild solution has a Kretschmer curvature invariant, which goes like 1 over r to the 6. And we've never ever thought that that was a problem. So I have 2 questions for you. One is, why do you want to get rid of curvature singularities? Because the Schwarzschild solution only applies outside the source. It's an exterior solution. It doesn't hold at r equals 0. You have to put the source in and not just look at the free gravity. So there's no real 1 over r to the 6 singularity in the a Schwarzschild solution that's coupled to a normal source, like a perfect fluid. So I'm asking you, why would you be concerned about this? And I don't mean that critically. I mean it curious. I'm just curious.
Yeah, thanks for your question. Well, there are many things related to the singularities, because first, it means that it's a point where the theory loses its predictory value, and so it's even though it's a point, but it can be. It means that near this point, the things, the values, the quantities, they grow without any bound. So even this means that you're losing you're towards losing the predictability, and this is one reason. And the other reason is that this is a very interesting consequence of these models. For example, in the case of the 4th derivative gravity, you have a whole, not only the Schwarzschild solution as static spherically symmetric solution. You also have other families of solution. And then it's natural to ask what happens if you go to higher order theories. And in the case of for example, this paper of Bob Holdom, he reports that only found the regular solutions. So the result is towards a more, because there it was numerical work, here it's towards a more analytic work on this. But it would be very interesting to see what's the structure of this space of solutions in this more general case. Just some ideas.
Okay.
And
okay, we have 5 minutes left, unfortunately. So please.
Okay. Now, in the second part of the talk, I'm going to apply the results on the higher order regularity of the solutions to other metrics, not these metrics that are obtained as solutions of some equations of motion, but to general metrics that appear in the literature, because this is done in the framework of the finite action principle. And this was proposed by Baron Tipler in '88. And more recently, it was applied as a mean of selecting regular space-time configurations, because the claim is that metrics that make the action diverge produce a destructive interference in the quantum gravitational function integral when you integrate over all possible geometries. So this procedure selects with higher weight the space-time configurations for which the action is finite. And in this case, if the action contains higher derivative terms, more regular black holes metrics are going to be filtered out by this procedure, because even though they are regular, they might be not 1 or 2 or n regular. And in this work, we investigated this in the case of some of the solutions, some of the metrics available. Let me say that first, this idea was first put on by Lerner and Stelly, I think, on cosmology, and more recently by Borisov and Eichhofen for black holes. And so here are some examples. In the case of the high-order black hole, you have so here I'm going to consider a metric in this form. And in the case of the high-order black hole, the function A, it has this term r to the 5. That's the first odd order term in the expansion. So according to what we learned before, you might expect that the scalars with at least 4 covariant derivatives might diverge. And indeed it happens, like in the case of r box squared r, is diverged like 1 over r. And if you consider even more derivatives, you get even stronger singularities. Also in this case, in the case of the renormalization group improved black holes by Bonan and Reuter, you get also here a term of order 3 on r, and then scalars with 2 and more covariant derivatives can diverge. And indeed, it happens. There are the case of even analytic metrics. These are the ones that are infinitely regular. For example, the matrix in this table. And then in this case, all the curvature invariants are finite. Also in the case of non-analytic smooth metrics. Well, the details are in this paper, where we studied in detail the case of the invariance of the type box to the nr. And this is the simplest one to try to get a kind of non-linear version of the theorem I stated before. And the result is a little bit complicated, but I tried to put it here in a more simplified way. And it says that if A is equal to 1 over B, remember, these are the functions here on the metric. Then if A is n regular, the invariants of the type box to the nr diverge like 1 over r. But if A is different than 1 over B, and both functions are at least n irregular, then it's more tricky. And this box to the nr can either be regular or diverge. In the paper, there is all the conditions under which they can be regular. And well, one might say that in 4 dimensions, the divergences like 1 over r and 1 over r squared are not important, because when you put a curvature invariant in the action, this f is a generic curvature invariant, and when you integrate, because of the integration measure, you get r squared. So only the divergence of the type 1 over cube are important. But these terms occur in these curvature invariants like Riemann box to some power Riemann, or Ricci box to some power Ricci, and so on, like I showed before. So in this case, we couldn't find a theorem relating the highest power of the series expansion of the metric to the minimum structure that diverges, because in this case it's more complicated. So the conclusions here is that depending on the form of the gravitational action, some regular space-time configurations may not contribute to the path integral. And models with higher derivatives are more selective, because the space of regular metrics associated with a finite action is more constrained. So if you want to select a theory by the requirement that it selects only the regular spacetimes with any degree of regularity, then you need to put really non-local terms in the action. So all this shows that higher derivatives have many fruitful applications in different approaches to quantum gravity. And it's also a motivation for studying these models in the nonlinear regime. That's certainly the most interesting one. So thank you.
Okay, thank you very much for the talk. We have time for a really quick question. So please, Chair Yu Chen.
Yes, thank you very much for the talk. I have a question about what you mean by harmless in the curvature invariance. So you put a curvature and integrate over that. So what is the physical meaning of that integration, and in harmless in terms of what?
Okay, thank you. When I say harmless, because in the integration, there's also the integration measure. So you have the r squared in the integration measure, and then this r squared is going to cancel the 1 over r or 1 over the r squared, and then you're still going to get a finite result. So in this sense, it's harmless. But so in this sense, it's harmless. And in this procedure is on when you are integrating over all the possible geometries. And this framework is called the Lorentzian path integral approach. And in my opinion, these arguments are still a little bit a kind of estimates. And I think it's necessary more rigorous proof of how this interference occurs, and these singular metrics are filtered out. I think this is a very interesting idea, but I think it still needs more rigorous studies, and I think it's very interesting.
Okay, thank you.
Okay, I'm sorry, but it seems like that we don't have time for more questions. So I suggest to move them for discussion session. And now we have a talk by Professor Dvali. Could you please try sharing screen?
Hi, can you hear me actually?
Yes, we can hear. Hello.
Hi. So but by some reason I cannot raise the volume. It's the function is disabled.
No, but we hear you very well. No problem.
Oh, it's okay. All right. Okay. Just yeah, very good. So then I'll share the screen. Is that okay?
Yes,
From
yes.
my iPad.
From iPad. Wait a sec, maybe I have to then make you a co-host from iPad. Wait a sec.
No, I think it works.
It works? Ah, okay.
Yeah.
Good. Yeah, then you're good to go.
Okay. Perfect. Paste. And yeah, okay. Hi, and I would like to thank organizers for the invitation. And so I'm going to discuss some of the basics of black hole physics. So black holes are a phenomenon of nature. So, and then when we try to understand the phenomenon of nature, it's very important to differentiate and to distinguish between the domains of calculability, or, for example, lack of calculability or lack of knowledge, from the inconsistency. Because if you will make such mistakes, and we are making such mistakes, and in that case, basically we should not introduce paradoxes where they do not exist, okay? And so therefore, I'm going to focus on a very basic point, which by some mysterious reason is not really appreciated in our discussions about black holes. And for that, I will go to some basics of, some really basic points about quantum field theory. In particular, what is the connection between quantumness and classicality? Okay. So basically, my point. So one of my points that I will discuss, I will show, is that there is an absolute there's an absolute lower bound on thermality of a black hole that you can have black hole at temperature T. There is a fundamental uncertainty, an absolute lower bound on the uncertainty of defining the possibility to define the temperature. So, for example, this uncertainty, let's say per time of order inverse temperature. And this is given by one of the black hole entropy. So therefore, this uncertainty is a lower bound, which is also, and this is also not appreciated in general, that this is gravitational coupling of gravitational coupling, quantum coupling, evaluated at momentum transfer T. Okay. All right, and because of and this is, of course, this is extremely important, because this sheds a very different light on what we can say about black holes and etc. In particular, this tells you that within semi-classical theory, you cannot even, there is absolutely no point to say that there is any paradox or anything like that. So let me go to discussion of some couple of basic points. Was there any comment or a question? No.
No, it seems to be randomness.
Yeah, as I said, the volume is low and I cannot really hear you very well. Maybe I'll try with the. But you can hear me okay, right? That's the important thing.
Yes, we can hear you.
All right. So now, please stop me if you, in case I will not hear you. So in general, right? So first of all, I will use units. The speed of light equals 1, but I will keep Planck's constant explicit. Okay, this is explicit. for the time being. Then later I'll set it to equal to 1. Okay. So now, first important thing is about connection between quantum and classical, right? So in general, here's the schematic thing. I will put all the parameters equal to 1. I mean, 16 pi squared will be equal to 1, 2 pi will be equal to 1, except those that are important, okay? So numerical factors, I'll set to 1. So when you have a quantum field, right? So quantum field, the connection between quantum field and particles, because in most fundamental framework that we have is quantum field theory and particle physics. So therefore we should operate with this. I will operate with these notions. So so quantum field connection between quantum field and particles goes, of course, through creation and annihilation operators of particles, right? But here I want to make counting, H-bar counting, very explicit. So the way the coefficient goes is the volume, okay, you can set whatever volume, and then frequencies, right, as you know. And then this is a power of creation and annihilation operators, which are accompanied by mode functions, right? So we have creation, we have annihilation operator. Okay, if the field is Hermitian, for simplicity, it will be Hermitian conjugate. Okay, so the psi of K's are the mode functions that you can choose depending on which space-time you want to work. I will work on Minkowski. So they compose a complete set, and K is an identity of a mode. And the quantumness, of course, phi is an operator, and K's are operators. And quantumness, of course, in this algebra of creation and annihilation operators. So, for example, for bosonic case, it goes to commutators, as we know. So this is the bridge. This is the connection to quantumness. And when AK dagger acts on a vacuum, it creates a one-particle state of label K. So now, in general, if you have different other quantum numbers, you have to multiply the corresponding polarization operators, of course. Yeah. All right, and so the another important notion that we need for, so now another important concept is the connection with classicality. Now, what is the connection with classicality? Classical field, quite classic. This represents an expectation value of a quantum field. But not every expectation value, of course, behaves classically. The expectation values, there are certain states that are classical in good approximation. Those are states with high occupation numbers, okay? For example, coherent states with high occupation numbers or number states with high occupation numbers. Those behave approximately classically. So the dictionary between, so now on those states, so these are basically classical states are the states with high occupation numbers, okay? For example, in a given momentum mode, the occupation number is much larger than 1. So then the physics on such states can be treated approximately classically. I mean, there are other subtleties, but let me. And so therefore, the way, since the expectation value of the creation and annihilation operators of these A's on high occupation number, in particular, most classical states are coherent states. But for this discussion, it doesn't matter. They scale a square root from the occupation number. So now you can understand how the classical field, what is the point of classical field? The classical field essentially is a quantity like this. So schematically, of course, this is a sum over different modes, etc. But this is the factor which is important. V over omega, V times omega. So this is basically the connection between state and the classical field. So, and this is very important. So the classical field, the H bar and N scaling of the classical field is the most important thing. So in particular, for example, if you evaluate on the volume, so if you have a particle on Compton wavelength, okay, the frequency being H bar omega, H bar wavelength R, and you take volume over the R cube, okay, on the Compton wave of the, sorry, on the de Broglie wavelength. So the classical field scales as NH, square root from NH over R. So this tells you what does it mean to take classical limit in the theory, because when normally we say classical limit is limit H bar goes to 0, but I mean, of course, that limit, the whole point is that when you take H bar going to 0, theory doesn't become trivial because the quantum field is proportional to power of H bar from here. So now you could say, okay, if I take H bar to 0, quantum field goes to 0. No, because what happens is that the physics lands on states that are infinite occupation numbers. So those states are the ones that survive for which H times N is finite. Okay, and this is very important. So basically, deviations from classicality are encoded in 1 over N, okay? 1 over N is the measure of classicality. Okay? Now, unfortunately, in the standard QFT courses, these things are not paid much attention. Okay, in my courses, I try to pay attention, but anyway, so, and these are important things. Now, another concept, important QFT concept is the coupling, right? Is the quantum coupling of the field. Now, what is the quantum coupling of the field? The quantum coupling of the field, so, and what's the dictionary? We know what's the dictionary. For example, if you have a field phi, a classical field, you have Hamiltonian, and in Hamiltonian you have, some classical nonlinearity. In classical Hamiltonian, so I'm not putting any head. If you have classical nonlinearity, let's say phi to the fourth. So there is some coefficient of classical nonlinearity, phi to the fourth, okay? In quantum theory, there is a coupling between quantum particles. Okay, now if I promote this into a quantum field, when I promote this into a quantum field, the quantum coupling between particles will be given by alpha, and alpha is H bar times G. Okay, so what you need to do, you have to multiply classical nonlinearity with H bar. And of course, this quantity is quantum, obviously. Okay. All right, so very good. So now, the similar thing happens for gravity. For gravity, is exactly the same thing. For gravity, we have, let's say, graviton, which is, oh my God, this. Okay, we have graviton and classical. Classical graviton is fluctuation of a metric. So as I said, I'm considering Minkowski metric, and so there is a canonical normalized fluctuation which scales as, which we call linearized gravity, and that scales, that's accompanied with the square root from Newton's constant, okay? And now if you have classical nonlinearity of gravitational excitation, so if you have classical gravitational excitation, they interact nonlinear, let's say to the quartic order, right? So that's the expansion in G Newton and derivatives, right? And so this is accompanied by the G Newton times 2 derivatives, all right? Which, if I have characteristic wavelengths, let's say gravitational waves of certain wavelength R, this translates as G Newton over R squared, okay? All right, so now you use the same dictionary that you have for any classical to quantum dictionary, okay? And so the alpha gravity, the quantum coupling of gravitons, this is H bar times G Newton divided by the wavelength square. Now, of course, this tells you that in the process with the momentum transfer, so this R corresponds to the de Broglie wavelength of the corresponding momentum transfer between gravitons, okay? Now, what is this? This is actually nothing but the Planck scale square over R square, okay? So this is Planck scale square over R square, where Planck scale, as you know, this is square root from H bar times G Newton. This is quantum scale of gravity, okay? And also, this immediately tells you that the Planck scale gravity becomes strongly interactive. And so we can also define Planck mass, which is h bar divided by L Planck. Sorry, not L Planck. G Newton. All right, so we have this thing. So correspondingly, the quantum coupling of gravity you can also write as the Broglie wavelength of momentum transfer or in Planck units. Okay, that's what also you can do. Okay, so this is quantum coupling of gravity. Okay. Let me see how I'm doing in time. Okay, so very good. So now, next concept I want to introduce is about thermality. When we go to thermal states in quantum field theory. Now, in quantum field theory can be in the states that are approximately thermal. Okay, as we know. So, for example, you can have gas or particles in thermal equilibrium, etc., etc. Now, most interesting story that I want to focus on is when the system is out of equilibrium, slightly out of equilibrium. This is what's happening all the time, okay? There are actually no systems in nature that have exact thermal equilibrium. And when the system is out of thermal equilibrium, there is the following point that, of course, the temperature becomes ill-defined to certain uncertainty, okay? And this is what we have to understand very well. There's always certain, so what is the thermal state, right? So in thermal state, for example, I can prepare some thermal distribution of particles. So this is a distribution which is set by a single, there is certain wavelength, for example, and that defines temperature. And so once you give me temperature, everything is defined, okay? So there's a distribution. For example, intensity of radiation or occupation number and so on, okay? Now, however, okay, this is very schematic. So the thermal distribution, we know, everybody knows what it is. Now, the thing is that thermal distribution has no features because it's set by the temperature, okay? But this is only true if the system is not interacting. If system is interacting and it is slightly out of thermal equilibrium, for example, it's exchanging something, let's say some energy or some momentum transfer, there is a fundamental uncertainty to which this thermal distribution you can apply, to the precision that you can apply thermal distribution. And that uncertainty is set by the coupling of corresponding theory, whatever quantum theory you have, evaluated at the momentum transfer given by the temperature. Okay, so this is the general things about quantum field theory. Now, how precisely it is defined, you know, this may depend on other things, other parameters, but it's always set by this coupling. Okay. All right, so now let's move to black holes. I think I'm doing good in time. So now let's move to black holes. What this will tell us about black holes? As I said, this is absolute basis of quantum field theory. I'm not inventing anything new. I'm just paying an attention to the points that are important, okay? And that is what's very important. Now, what do we know about black holes, right? Black holes. So first of all, for black holes, again, I will use only absolute basic facts about black holes. Well, we know the black holes, they have certain radius, obviously, which is related to their mass. Okay, so if they have mass, they have radius. Again, as I said, I'm not putting here a factor of 2 because I'm setting 2 equals to 1. It's not important. Okay, so what else? So they have reduced, so black hole, which is, now this is very important because this has no powers of h bar. This relation has h bar in power 0. So it's a purely classical relation. And so in classical physics, you can define geometry, and that's given by the left-hand side of this equation. And the right-hand side of the equation is the mass. Okay, now, of course, nature is one. And now, if you treat black holes semi-classically, all right, which we come back what it means, all right, in that treatment, we know the black holes radiate, and so that's Hawking temperature. So they have temperature. Well, approximately. This is extremely important. This is what I want to make it very clear in this talk, and which is given by h bar divided by the size of a black hole. Okay. So if semi-classical approximation is good, this is the relation between temperature and the size of the black hole. And black holes, they also have entropy. And the entropy of a black hole, Bekenstein-Hawking entropy, entropy of a black hole, as we know, is given by, again, let me not worry about coefficients, although you can restore coefficients absolutely, perfectly precisely, no problem. So it's an area in Planck units. Very good. You can also translate this as a temperature. So it's temperature in Planck units. But then there is yet another observation which I want to stress, which is not paid attention normally, and I'm trying for I don't know how many years to say that this is what is happening here. This is very important. That this is 1 divided by the gravitational coupling evaluated at momentum transfer t. That's a fact, okay? So that's fine. You can write in several different ways this entropy. All right. Okay, so we have temperature and entropy. Now the question is, black holes evaporate. So let's say I start with a black hole with certain mass m, temperature radius r, and temperature t. And I declare at the beginning that semi-classical approximation for this black hole is good. All right, whatever it means. Okay, and then I say that okay, now this black hole is losing it, is radiating, so it's losing energy, and it evolves. Now, to what it evolves? That's the question, right? And usually the assumption is very tempting, and usually this is what is made as an assumption, because now we know that black holes exist for arbitrary masses. So for arbitrary mass, m prime less than m, you can have a black hole with radius r prime and with temperature t larger than t prime larger than t. Okay, and correspondingly, it's really tempting to assume that when black hole emits radiation, it evolves into black hole prime. In other words, it evolves into a black hole prime. What does it mean, black hole prime? This line means that assumption is that the semi-classicality holds. So when you emit the quantum, becomes a carbon copy of a smaller black hole. And the smaller black hole doesn't have any memory that it came from a bigger black hole. Okay, so this is the standard assumption. In other words, this is the assumption of self-similarity. Now, this is just an assumption. This is extremely important to stress, and I'm going to show that this cannot be a correct assumption. This assumption cannot work if all the basics of quantum field theory are correct. So now there is an option number 2. Option number 2 is the black hole emits quantum and evolves into something that you should not call into an object that is less semi-classical. Okay, so let me call this still a black hole, but with a question mark. Okay, so therefore the road here is that you are taking the road towards the breakdown of the semi-classical approximation, or you keep semi-classical approximation very accurately. Now, again, this requires some specification, but okay, let's assume some exponential accuracy. Okay, and you are going in this direction. So the point is that most basic points of quantum field theory tell us that this is the road. That the standard assumption that black hole evaporation is self-similar as black hole shrinks and becomes, it's not justified. I'm not, of course, I mean, this is extremely important to understand, to separate domains of calculability from the domains of the lack of knowledge and false assumptions. Okay, so how do I know that this is the case? Because I just told you a minute ago that if you have a quantum field theoretic system, interacting quantum field theoretic system, there is an uncertainty in defining a temperature. So if black hole evaporates and temperature changes, okay, for example, if I go from here to here, right, in this road, temperature will change, and therefore this change of temperature will impose an absolute uncertainty on how precisely you can define temperature in that process. And so that is controlled by alpha gravity at temperature T, which is T square over m Planck square. And now we can see explicitly this at work. So now you don't, so what is really interesting is that you don't need to have a microscopic theory of a black hole. If you have a microscopic theory, there you can confirm these results. But for the bound, you don't need a microscopic theory of a black hole. Just follows from the assumption itself. Indeed, let's assume that this is correct. The standard assumption is correct. This means that there is a mass changes of a black hole. There's a Stefan-Boltzmann law, right? Of the change of mass of a black hole. At this point, I can even set h bar equals to 1. Okay. So there's a Stefan-Boltzmann law of black hole change. This is fine, certainly. At the beginning, this is true because we are emitting, so the mass changes. And what is crucial for self-similarity is that temperature keeps to be well-defined all the time. Okay, so temperature always goes as 1 over mg Newton. Okay, all right. This is the thing. This is the thing. Okay. So if temperature, in other words, temperature tracks the mass, and this is assumption. And actually, I'm going to show that this assumption cannot be correct. This is a wrong assumption. There is a certain accuracy by which it is correct, and the magnitude of deviation is astonishing. It's really huge. Okay, it's not exponentially small, in other words. And now let me prove that this. So let me now immediately show that this must be the case. Now, for this, what you need to do is just take and differentiate the second equation. You differentiate T dot. Okay, this will give you 1 over mg Newton m square m dot. And then I use this fact that m dot is minus t square. I plug it here, and I get the following structure, right? So I get this object, then I get t square, so plus, and now I form the following equation, and this is the equation: t dot over t square. This is an extremely important parameter. Okay, this is equal to t square over m Planck square. Or, in other words, this is equal to alpha gravity evaluated at temperature T. Or, which is the same thing, 1 over the entropy of a black hole. Now, why is this? This is the most important expression in my talk, okay? Now, why? Because this is a parameter of thermality. Now, T dot over T square is a parameter of thermality. For this, you don't even need to know quantum field theory. If you know statistical physics, that's the way it works, okay? So in other words, if I have a system in which is slightly out of equilibrium, meaning that temperature changes, there is an intrinsic uncertainty in how to define, to which you can define temperature. And this uncertainty is given by this thermality parameter. This is also a semi-classicality parameter. And now what are we learning? We are learning the following thing, that when black hole emits a radiation, of course, the mass is decreasing. But what happens is that it becomes less semi-classical. In other words, the corrections during this emission, corrections to thermality or semi-classicality, these are 1 over S corrections. This is extremely important. Now notice the following thing, that why is this important? Because notice the following thing. This is a correction per 1 emission, okay? So 1 emission goes during the time of 1 emission time scale is approximately the black hole radius or inverse temperature. Now, by the time that black hole loses approximately half of its mass, if this approximation continues to be correct, the Hawking approximation, approximately correct, the time scale for that of when black hole loses half of its mass, the time scale T, and let me call it TQ because this is time scale, a very important time scale. This goes as entropy times R. So in other words, this tells you that if correction if correction to thermality is 1 over R per each emission, by the time black hole loses approximately half of its mass, the correction is 1, order 1. There is no way you can treat black hole beyond that point semi-classically. Hawking approximation is completely breaks down by 100%, okay? And then you have to go and study separate story. But of course, I mean, this means that there is an intrinsic uncertainty in features of the spectrum, which are assumption independent. And this intrinsic uncertainty in the features of the spectrum, they are 1 over S, okay? And of course, given this, okay, so now let's try to summarize this point. So given this, can you even talk about information paradox? Of course not, because I mean, how can paradox be there when there is an uncertainty, fundamental uncertainty in the features? So which means that it's just simply not there. Actually, it was never there. The so-called paradox is simply a consequence of the fact that we assumed self-similarity, but that assumption, I showed you, that assumption cannot stand. That's not possible. If we take into account absolute basic points of quantum physics, quantum field theory in this case. Okay, all right, so now, there is an uncertainty here, but it's always good to check now in a microscopic theory. So you see, this is what is very important to understand, that what semi-classical physics can tell you, there is an absolute uncertainty, okay, in the knowledge that you can extract from the semi-classical analysis, okay, period. Now, to go beyond that and to really extract the knowledge from the semi-classical knowledge about these corrections of 1 over S corrections, okay? Of course, you need a microscopic theory. Now, I mean, I have such a microscopic theory. Cesar Gomez, a collaborator of mine, and we were suggesting for a long time that black hole, once you treat black hole as a coherent state or a condensate of gravitons. So if you think of a black hole as a coherent state of gravitons, okay, and gravitons. Okay, this is Cesar and myself in 2011 or something. The way actually you can check, the rest follows basically. Once you make this assumption, the rest follows. So once you assume the black hole is a certain state of gravitons, in quantum gravity there is nothing else. I mean, for a macroscopic black hole cannot be anything else in pure gravity, for example, because they are only gravitons. There are no other building blocks. And if you assume that, the rest follows, and then you can compute these corrections. And indeed, you can see that in this theory, the corrections are explicit, because the Hawking evaporation in this theory is that you have state of n gravitons, and then what happens is that they rescatter and they deplete. The graviton condensate depletes roughly to n-1, and the emission rate. And then, of course, you can now, so the expansion now becomes 1 over n, and by the way, n is S, okay, which is also 1 over alpha in that theory. And then you can follow this. Okay, now, I will not enter too much into the details of microscopic theory. Of course, I would not be talking about this theory, but we're not sure that that's the correct theory. But what is important is at the conceptual level. This is what I'm trying to bring across, that already in semi-classical theory, without any knowledge of microscopic theory, already in semi-classical theory, you have an absolute lower bound on the thermality of the black hole radiation, which tells you that Hawking's computation always has 1 over S correction. Now, by the way, I want to make it clear that Hawking's computation, nevertheless, the original one that he did, is exact. Why? Because Hawking was computing in a special limit. Hawking's computation was done in a special limit in which you do the following thing. You take G Newton to 0, you take black hole mass to infinity. I mean, he did it to infinity. And of course, now you can see, and you keep, if you keep the radius finite, Gn times m finite. What happens in this limit? And you also keep h bar finite. So in this limit, black hole becomes infinitely heavy, okay? But geometry is fixed. So the temperature, h bar over r, is finite. Now in this limit, the corrections go to 0, but that's exactly also my point, that in this limit, the black hole entropy goes to 0, to infinity. And graviton coupling goes to 0. Correspondingly, black hole entropy, which is also 1 over graviton coupling, sorry, let me write it the other way around. Therefore, corrections, alpha, gravitational corrections at temperature T, which is 1 over the entropy, they go to 0. And of course, in that limit, obviously, there is everything is consistent. But also, black hole lives infinitely long. If black hole lives infinitely long, of course, it's just an eternal object. But for any finite mass of a black hole, as long as you keep gravitational interaction, black hole mass, and Planck's constant finite, there is no way out, because there is always a correction which is controlled by 1 over s. And this, again, is very important to understand. This is independent of the knowledge of microscopic theory. Okay. Now, the microscopic theory is the next level, because if you want to compute this what these corrections are, of course, for that you need microscopic theory. I'm not aware of any other one that allows these computations. I'm aware of this one, the one in which we call it M portrait, in which the black hole represents an coherent state of gravitons.
Excuse me,
So, you know, I mean,
question.
I know there's overwhelming evidence that this is the correct answer. For example, I don't know, there are different things. For instance, black hole formation in trans-Planckian graviton scattering, you can understand this as multi-graviton 2 to the n process. And we computed this process with Cesar, Dieter Lust, Stieberger, and others. And actually, we did this computation both in quantum field theory and in string theory. And
yeah, do you hear us? There
and,
is something on the way. Can you answer it, maybe?
Let me just, I'm almost two minutes from the end, and yeah, then I'll be more than happy to take your question. So here, actually, in this computation, you can see very precisely how that the production of each microstate, of n graviton microstate, precisely scales as black hole entropy when the momentum transfer, okay, which is given by the impact parameter. Impact parameter is given by the would-be temperature or inverse Schwarzschild radius of a black hole, and so on. I mean, there's a long list of consistency checks of this picture. I don't want to enter there. Okay, so therefore, again, to summarize, I think I still have some 5 minutes, but let me summarize here, because I don't want to dilute the point. I don't want to discuss many different things in one talk. I really want to focus on this. This is the most important message I wanted to bring across, okay, let me summarize here. That there is an intrinsic uncertainty of delta T per time of emission, which is set by 1 over the entropy, or which is the same as gravitational coupling as function of T. And therefore, this immediately tells you that after timescale TQ, which is of order of S times R, black hole goes out of semi-classical regime. And this means that we call it quantum breaking. This is a quantum break time. This is a quantum break time of a black hole. In other words, it's really amazing. You can have a solar mass black hole, which is a hugely macroscopic object. And now you would think that after half decay, when it loses half of its mass, it continues to be classical in a very good approximation. But it's not, because of this peculiarity of the black hole state, and because it's a saturated critical state, etc. But anyway, so this is the point. By the way, this time scale also agree. So this time scale is, as I said, this is half decay time, and also it agrees with the time scale of derived by Page with a completely different consideration. Page also suggested that something should happen around the time scale, but here I'm providing an explicit engine. What happens? Why that time scale is there? Because there are corrections 1/s throughout the black hole operation. Okay, I'll finish here and I'll take the questions. So please, you said there were questions.
Okay, thank you very much for the talk. And
by some reason,
Ravan,
I don't know. Maybe let me try to. Sorry.
Can you hear us?
Yeah, now.
Okay.
Okay, it's better. Can you hear me?
Yes, we can.
Okay, great. Okay.
So Ravan, go ahead with the question.
Hi, Gia.
Hi.
Thank you for the very nice talk. Nice to see you.
Same here.
I have a couple of questions.
Yes, please.
Question is, you mentioned quantum field theory. I'm a bit confused. Are you speaking about quantum field theory in Minkowski spacetime or curved spacetime? If it is curved spacetime, there are still a lot of questions, and this subject is still, I think, not finished yet. Do you agree?
Yeah, of course. And I think that it will never be finished, actually, because of the following reason. Because the reason why I chose, no, this is a very important question, actually. The reason why I chose Minkowski spacetime, because of course, first I can choose whatever spacetime I liked in order to study black holes. And so I chose Minkowski space, asymptotically Minkowski space. That's one thing. But there is another reason why I did that, because the only formulation of quantum gravity, the only closed formulation of quantum gravity that we have is the S matrix formulation. That's the state of our knowledge, okay? So, and the S matrix requires the unique vacuum, which is asymptotically flat, essentially Minkowski space. And so therefore, by the way, that's why string theory cannot be formulated in space-times which are not S-metric space-times. For example, the sitter. There is no formulation of string theory.
We only successfully formulated S-matrix notion in Minkowski spacetime. Curved spacetime, it may exist. I mean, it's not impossible, right? No one ruled out. Of course, claims about this rule.
So sure, but yeah. No. But there are several important things to hear since you are asking that question. Now, of course, these are irrelevant for my talk because black holes are perfectly well defined in Minkowski space, and okay, so this is perfectly fine. But the point is the following. So for the S matrix can only be formulated in space-times in which two conditions are satisfied. There is a rigid vacuum, asymptotically you can define an S matrix vacuum, which is rigid, okay? And there is a globally defined time. So therefore, if you have curved spacetimes which still allow that, then there's no problem. So then also my analysis holds because it's asymptotically the spacetime allows it to be flat and well-defined global time, then there's no problem for me. But if the spacetime doesn't allow that, there is no way to formulate the S matrix. Okay, so that's why I said, for example, in particular, I'm not hung up on string theory. I'm not saying that this it's also the same. For example, in my approach to quantum gravity, in which I think that quantum gravity is self-complete by black holes, because because of precisely this feature, in trans-Planckian collisions, what happens is that the theory gets unitarized by producing many soft gravitons. We have shown that explicitly actually in the computations. So I think that even in that case it's an S matrix formulation. So
yeah, so for me, the choice of asymptotically flat Minkowski space is doubly justified. I mean, first, because black holes are certainly S-matrix states. We know that we can form them in particle collisions, and secondly, the formulation of quantum gravity requires S-matrix. Yeah.
Yeah, but when you mention Hawking computation is precisely in curved spacetime, not in the Minkowski spacetime. So
no, because that's what. Yes,
yeah,
exactly.
Yeah.
No, because that's what I said. Because Hawking's computation is the limit. Hawking is doing computation in this limit. This is the limit in which you can think of a black hole as a vacuum. This is the only limit in which you can think of black hole as a vacuum. And in that case, you can do vacuum computation, and that will be the same as an S-matrix computation, okay? There is no problem. I mean, what Hawking is doing is perfectly fine, but that's only valid in that limit. In no other limit, you can treat black hole as a vacuum. It's always, so in any other limit, the treatment of a black hole as a vacuum is an approximate treatment. This is what I'm trying to say. Now, so again, I mean, my message, what I'm trying to bring a message which is extremely important and it's overlooked all the time, and people simply because when we are saying about, when you're talking about approximations, of course, the issue becomes quantitative. I mean, if approximation is doubly exponentially good, then of course you say, okay, after all, it's fine. I can treat black hole as a vacuum. But what I'm saying is that the approximation is incredibly fragile because 1/s corrections, they are extremely huge, large corrections because they are of the same order as the gravitational coupling, and correspondingly, the already by half decay black hole goes completely out of the semi-classical regime. So it's a quantitative thing, but it's so strong that it becomes qualitative because you see, it's like the corrections, if corrections would be exponent minus s, then of course they will be perfectly fine. But corrections are not exponent minus, they are 1/s, and they are hugely more important. So then, yeah.
Okay, I understand. Can I ask a second question, which is
sure.
Observational point of view? As you say, the quantum break time, which is basically coincides with the page time from a different point of view.
Right, that's right.
Let's say I mean, again, this question actually, it was asked by Slava Mukhanov, but the answer is not known. I'm curious if you can give some comment about it. So, well, if we observe black holes in the universe, how do we know whether they are at the quantum break time or at some other time? Just by observations, how do we make computations or observe something and correlate our computation with observations?
Yes, absolutely. Yeah. So that is an extremely important question, and the answer there could be so first order answer can come from semi-classical theory. Okay. Now, semi-classically, what we know is that black holes that lived for the time t, okay, which is less than their half decay time, the off classicality for them, this must be of order t divided by quantum break time. Okay, so t divided by tq. This is the measure of departure of those black holes from semi-classicality. Okay. Now, of course, if the t over tq is huge, is order 1, then of course the predictions are very clear. I mean, for example, there is absolutely no way to really see a thermal spectrum from such a black hole. Okay, and so on. There are other also things. So in other words, semi-classical theory can tell you what is the measure of departure from semi-classicality, and that's what we have to look for in this case. Now, to make precise predictions of what are the departures, of course, for that we need microscopic theory. And so that question I can answer within my microscopic theory. So in my theory, what happens is that there are n-graviton, black hole is an n-graviton state. And so black hole has modes that are responsible for the energy. So these are gravitons of wavelength approximately the size of a black hole. And there are modes which are responsible for the information storage, the entropy modes. So we call them memory modes and master modes. Master modes are the energy modes. Okay, so this is entropy and this is energy. And so what happens is that when the black hole evaporates, what we see is the following: that when black hole goes from a black hole, you go to a black hole prime, let's say plus a photon, right? Now, of course, already Page and others, they knew that there is an entanglement. There is an entanglement between outgoing radiation and the remaining state of a black hole. Now, however, what is new, that of course is there, but what we are pointing out, which was not known before because nobody had a microscopic theory, what we see is the following: that there are two other effects which are happening. First, this N graviton internally becomes entangled. So it's a self-entanglement or inner entanglement of this state. So in other words, this state itself, even without entangling with outgoing radiation, on its own becomes more and more entangled because it's a multi-particle state, and that's a property of multi-particle states to become entangled. So it becomes internally entangled, and there is another effect, I call it memory burden effect, that the memory modes, the information pattern stored by the memory modes, it back reacts on a black hole. Both are very clear physical effects. We have simulated them on prototype models, I mean, this kind of stuff. And so there you see very clearly why quantum breaking takes place by that time. And so then we know what to observe additionally. For example, there are indications that by the time the black hole loses half of its mass, it may slow down the quantum decay, but then it can disintegrate classically. So some Lyapunov exponents may appear. And so in other words, there is a list of signatures that we can look for those black holes in the universe, actually, yeah. And yeah.
This sounds very similar to the island approach, which became quite popular in this.
I don't know. I don't think so, because I mean, I can compare this to any approach that tells me that they have 1/n corrections. I mean, first of all, this is like 12 years old. This approach is, if there is some similarity between new approaches and this approach, maybe, but I mean, if you have 1/s corrections, that's the key. I mean, and you must have a microscopic theory. I mean, look, you can compute things in semi-classical physics, but then the corrections, I mean, obviously, this is very important thing to understand, that in order to pose certain questions, we need a microscopic framework. If we are in semi-classical framework, we cannot even pose certain set of questions. And so for that, you need a microscopic theory. And I can only tell you what I see in my microscopic theory.
In your theory, the observable is finding entanglement of outgoing radiation with something inside. Is it what you're saying?
No, there is an inner entanglement additionally, which has nothing to do with outgoing radiation.
Which we cannot measure anyway. We can only
you can measure. It translates into it translates into observable quantities. But it's very different to say that I have an object that is entangled with outgoing radiation, or I have object which is self-entangled. These are fundamentally two different mechanisms. Okay. But the self-entanglement you can only have if you have a microscopic theory. If you don't have microscopic theory, self-entanglement doesn't make any sense. You cannot self-entangle a semi-classical object. It doesn't make any sense. I mean, classical objects cannot be self-entangled. So you need a microscopic theory to see what this self-entanglement is about. Yeah.
So according to your microscopic picture, how information is carried precisely?
Shravan, sorry to interfere you, but maybe later you will give others to ask questions also.
Okay.
Yeah.
Okay. Yeah. I'm happy to go on with this.
Philip Mannheim, please.
Yes. Okay. Gia, hello again. Couple of comments. One is the large N limit as the classical limit is actually the original Bohr correspondence principle.
Well, that's obvious. Yeah, of course. I mean, the fact that large N limit is a classical limit is well known.
I'm surprised you're suggesting that people don't emphasize it. That was what you said. But that's
no,
fine.
but right, but I didn't say that. I said that these were absolute basics of quantum field theory.
Yes.
I just said that unfortunately in the textbooks they are not paid much attention. Precisely this transition from classicality and quantumness. For example, there is no discussion usually of quantum breaking or anything like that. So yes, of course. I mean that's the whole point of classicality. That it's the measure of classicality is 1 over n. That's not. I'm not claiming any credit for this. But I claim what I'm claiming credit for is applying this to black holes. That has never been done. And so that's, of course, is something absolutely, I mean, that's new.
Okay.
I mean, it was new 10 years ago, but so 10 years ago, we applied this to black holes. Yeah,
that was my minor comment. Now, my major comment is the question of what happens when a black hole emits Hawking radiation, where does it go? I don't think that's a legitimate question to ask, because it presupposes that the black hole forms independent of quantum mechanics. And really what has to happen is that the formation of the black hole will involve some effects of Hawking radiation as it goes. It's not that you switch it on afterwards.
But I mean, you are changing the subject. I don't want to enter because you see, we can discuss many different things. But I was discussing a very concrete story, and there is no ambiguity. I'm just saying, if we start at some t equals 0 with a black hole, which I let you prepare as you want. I don't care whether you prepared it classically, you prepared it quantum mechanically. It doesn't matter. So you prepare a black hole as you like, and you give me this black hole. And you tell me, okay, here is the most classical black hole I can prepare. But now, most classical means, why most classical? Because we don't live in classical universe. We live in quantum universe. H bar is non-zero, black hole mass is non-zero, G Newton is non-zero. So with those parameters, I let you prepare that black hole, and this is maximally classical. My logic applies after that. I'm saying, no matter what you do, you will not avoid this fundamental uncertainty in assigning a temperature to the black hole. That uncertainty is given by 1 over s. That's my most important message. And so that's an absolute bound. I'm not saying that you cannot have bigger corrections. Yeah, maybe you can have a bigger corrections in some other cases, but that's an absolute bound. It's a bound, okay? And so the power of that bound is that I'm not relying on any assumptions. I'm just using absolutely basics of quantum field theory. That's it. I mean, yeah.
Okay.
Okay.
Thank you.
Yeah. Alexander Wickman, please.
Yeah, great to see you.
Hi, Alex. Hi.
As usual. I just have a very maybe naive question. So what can one understand something what happens in the system like a black hole, which we put inside of a spherical mirror so that the mass would not change? Because it seems that at each process of basically emitting a quanta, there is some entanglement happening.
Yeah.
And, here, of course, it's a bit against your paradigm of Minkowski boundary conditions, but it would be nice to understand. So would this system, which looks like eternal, at some moment quantum mechanically break, nevertheless?
No, of course, yeah, it will. And it doesn't matter. I mean, the boundary conditions for me, Minkowski boundary conditions were convenient. Matter of convenience. So if black hole Schwarzschild radius, so you can equally apply my reasoning. So this goes back to this question. You can equally apply my reasoning to any space-time for which the curvature of the background space-time, curvature radius of the space-time, I don't know, whatever space-time, curvature radius is much larger than the Schwarzschild radius of a black hole. So if the radius is much larger than Schwarzschild radius of a black hole, you can apply ready-made what I'm saying. So now, yeah, let's take this type of situation. Let's say we put black hole in a thermal bath, okay? And then you have transfer of from here you have some thermal bath particles, and the black hole absorbs some radiation and emits some radiation. So perfectly fine. Now this creates again false impression that the system is because mass is not changing. It creates a false impression as if this black hole is eternal. Now, this is extremely important, and thanks for this question, actually. No, there is no way this black hole is eternal, because the process is still out of equilibrium. Because the way you can think about this like this: initial black hole is a coherent state, and this coherent state depletes. Okay, so it injects radiation into the surrounding medium. Okay, and then surrounding medium deposits some radiation back to but the deposited radiation, it cannot be coherent. That's not all of a sudden you cannot generate a coherent state by. There is always, therefore, there is this also in this system, there will be 1/s corrections to thermality. So in other words, these 1/s corrections are unavoidable, because when subsystem exchanges certain processes with the system is still out of equilibrium. Okay. So the only limit of a black hole for which presumably there is no quantum breaking is the exact extremal black hole. If you have an exact extremal black hole, with there essentially nothing happens. And so an exact extremal black hole in principle could be eternal. That's okay. Yeah, in that case it's okay.
But probably this breaking would happen just because the mirror absorbs too much entropy. There should be entropy growth in the mirror, or
no, it's again the same thing. Well, that also will be that process, but here is the Feynman diagram level to think about it. So you have n gravitons here, right? And then you have these additional quanta. I don't know, let's call them something. So this is the Feynman diagram. And then what happens is
the mirror. Right?
Yeah, mirror and radiation and everything. And so what happens is the black hole rescatters and emits, injects certain quanta into this story. But in turn, these quanta also rescatter, and that get deposited into a black hole. Okay. Okay, so what does it mean deposited? They bring energy, and then this energy gets redistributed among coherent state gravitons. But of course, this deposit is not coherent. Inevitably, it takes you out of coherence, because the initial state of a black hole was coherent, but then the coherence happens inevitably. And correspondingly, yeah, so correspondingly, that's the process inevitably results into the inner entanglement of these gravitons. So in other words, inner entanglement is unstoppable. Even if you keep throwing things into a black hole, that cannot stop inner entanglement, because inner entanglement is a quantum engine. It's a quantum process that you cannot stop it just simply dumping a lot of energy on a black hole. It just will continue to become entangled. And that's it, yeah, and then that's inevitable. So quantum breaking is inevitable in that case.
So in a sense, it relies to non-ideal nature of the mirror in some sense, because if there were no other radiation, just the same stuff constantly emitted by the black hole, and the mirror were ideal, then it
no. Even if mirror were ideal, what do you mean under ideal mirror? Ideal mirror would be the one that doesn't absorb any energy. That's what you mean, or you mean something else?
No, I mean like when people use lasers, right? They use also mirrors, and they send coherent laser pulses, and they get coherent laser pulses. They're still coherent.
Ah, you mean somehow this mirror, if the radiation emitted by a black hole would hit the mirror, come back undisturbed. That's what you mean. Yeah. The problem is that the entanglement is generated with irrespective of the outgoing product. That's the thing that no, it cannot stop it. No, even if mirror is absolutely ideal, let's say it doesn't even change the nature of a quantum. So a black hole emits a quantum, hits the mirror, goes back. Okay, doesn't matter, because already the emission process generated entanglement, and that doesn't matter. Now how this quantum goes back, it's irrelevant.
Okay. Thanks.
Sure.
Okay. Thank you very much for the question. Are there any other questions? If not, let me ask a question about whether the very definition of temperature is applicable in this case, because if the process at some point becomes non-equilibrium, maybe a different formalism is needed, which is sensitive to non-equilibrium quantum field theory.
Yes,
was it applied to this?
Yeah, that's precisely, yeah, indeed. I mean, when I was saying that there is an absolute bound on this, that this is a thermality parameter, I was using precisely non-equilibrium quantum field theory, obviously. So, I mean, we cannot use exact equilibrium quantum field theory. So, yes, indeed, this comes from non-equilibrium point. And so, you know, the way you can think about this is physically, it's very simple. I'm really surprised that this didn't take up some attention. I mean, I don't know, we're talking about black holes for 50 years, and I don't know why this was not paid attention. But in any case, I mean, the point is that whenever we have a system that is, let's take a very simple system. Let's say system in thermal equilibrium, right? Okay. And now, so let's say I have some quanta phi, certain phi species in thermal equilibrium. And then at some point, I start coupling these phi's to external species. Okay. So for instance, like, I don't know, there is a scattering between phi's and some external species chi. Okay. Now, and chi could be very, very weakly interacting. Okay. So for example, you can take this tank of phi's filled with radiation, and because of interaction with chi's, the system is coming out of thermal equilibrium. Now, why is coming out of thermal equilibrium? Because the phi that will decay into chi's here needs to redistribute its knowledge to the rest of the system. So in other words, the systems, they always have finite recoil time and finite back reaction time, okay? And correspondingly, and that's the key. It's very simple to understand, because you see, scattering in quantum field theory, scattering is associated with a time scale. So, and there is a time scale of scattering during which phi quanta somehow deposit some energy into different sector, okay, into chi, let's say chi sector. And then there is a time scale that system has to learn about it. And these time scales are always finite. And there is absolutely no way to treat system thermally on those time scales. And so then the whole question is, how adiabatic is the process? Okay. So yes, if you have a system which changes extremely slowly and adiabatically, yes, there will still be departures from thermality, but those departures can be smaller and smaller and smaller, because if you change parameters very slowly, the departure will be also weak, because system will try to thermalize. System can track the external parameters and thermalize all the time. Now that's a matter of now it's a concrete, it's a question, it's case by case basis. This you have to study on case by case basis. Now for black holes, we know what it is. We know what T dot over T square is, and correspondingly, that's the thing. In other words, what I'm saying is that everything, all knowledge about the internal structure of the system boils down to computation of this parameter, T dot over T square. Okay. And so for black holes, we know what T dot over T square is, because we just take assumption, we just take standard things and compute it. This is what I did. I just took derivative from this. I didn't put any extra assumptions. This is the amazing thing. This is the incredible thing, that already black hole itself tells you that it's not thermal because of this T dot over T square point. Okay. But yeah, I mean, of course, you are absolutely, I mean, yeah, for different systems, of course, we can have systems artificially prepared for which T dot over T square is very small, of course, arbitrarily small. You can make it arbitrarily small if you make system arbitrarily weakly coupled. So yeah, that's okay.
Is it important that besides gravitons, you have also normal matter particles?
No, it's absolutely unimportant, because black holes radiate even in pure gravity. I mean, gravity is self-sufficient.
There is just the result of impure gravity. Is it the same as in gravity with matter? With any
No,
matter?
actually, yeah, no, that's a good point. So in other words, the thing is, what I have shown a long time ago, sorry, this is, I don't know, yeah. So what happens is that if you have theory in which you have, instead of only pure gravity, let's say you have certain number of particle species, n particle species, okay? For example, in the standard model, there are 120 particle species, okay? So then these particle species, they multiply the correction, okay? So this parameter then goes as n species divided by the entropy, okay, of a black hole. And so you can see what happens is that the quantum break time shortens if you have many particle species. And that's very nice. So in other words, TQ, the quantum breaking time, goes as the number of species in the denominator. So it goes as entropy of a black hole times the radius divided by number of species. And so due to this, there is an absolute upper bound on the number of particle species that you can have in nature, because we know that the black hole quantum break time, because black holes, the shortest black hole quantum break time can be is the quantum gravity scale. I mean, the black hole that simply is not even classical. You form a black hole and just quantum breaks, that's a quantum black hole, okay? And that scale, we know that there is an absolute bound on that scale, which is around TeV energy, because we know from LHC physics, because we have not produced black holes at LHC corresponding, well, we don't know yet if we have produced one, but since we didn't observe any black holes at LHC, correspondingly, we know that this quantum break time for a smallest black hole should be larger than inverse TeV, and correspondingly, this puts bound on the number of particle species in nature in general. But okay, but yeah, but in general, it's very important. Yes, effect of particle species is very important because it increases the rate of Hawking radiation.
Thank you very much for the detailed answer. You have the other people who wants to ask questions. Philip Mannheim.
Okay. Gia, I want to come back to something we discussed a few moments ago. I agree with you. The first black hole you just take as a given, and then you've set some very nice bounds on what can happen afterwards. Right. But if people want to discuss the first black hole decays into the second black hole, they've got to discuss the formation of the second black hole. In other words, they've got to follow the new gravitational collapse, even if they didn't follow the gravitational collapse that got to the first black hole.
Yeah, absolutely, correct.
And I don't think they do that.
No, that's precisely what I'm trying to say. I'm saying, yes, of course, the whole point is when you, yes, absolutely, I fully agree. That's precisely the purpose of my talk. What I'm saying is that let's take a black hole which is maximally classical. Someone just gave me as a gift, okay, prepared this black hole, took infinite time, prepared this black hole, here's a black hole. It's maximally classical. And now what we know is the following, that when this black hole goes to, whatever it goes to, let's call it black hole prime, some state. This is some state now for me. So there is a state that is describing classical black hole or whatever, maximally classical black hole, the dream black hole, and then it emitted one Hawking quantum, evolved into something. My point is that this something, so if I am able to define temperature, notion of temperature for this one, T, for this one, T prime, there will be a fundamental uncertainty given by 1 over S, okay? So I'm very minimalistic in my, you see, I'm not, so your question, it goes beyond that. Of course, in the ideal world, then I need to evaluate and see what the state is and what you call a collapse and stuff like this. But what I'm trying to say, I'm not entering there. I'm just saying, I know that there is an absolute uncertainty, and correspondingly, that's my message. Now, of course, as I said, in order to understand what precisely this state is, for that you need a microscopic theory, and you need to study how you go from here to there, and so on. Obviously, yes, absolutely. And the only theory I know for that is this large N portrait that I have. I'm not aware of any other microscopic theory in which things are computable. Okay.
Yeah, very good.
Okay, thanks.
Okay, great. So there is a question from Sravan, and probably we can then turn to free discussion, including the other talks.
Yeah, just a very short question. We'll keep it very short. So, what is the quantum break time, if there is, in the context of inflation?
Yeah, very good. So, yeah, that's another thing, because I mean, our view of this de Sitter space and inflation is very similar because of this S matrix. What we suggested, Cesar and I, that also inflationary Hubble patch has to be viewed as a quantum state constructed on Minkowski, asymptotic Minkowski, and then it has a quantum break time. So here there are two things. what happens is that if you don't have an inflaton field, so in other words, if you don't introduce any other degree of freedom, somehow you start with pure de Sitter. I don't know whatever it means. At the end of the day, it's not consistent. But if you so imagine starting from pure de Sitter, just pure de Sitter with no other degrees of freedom. So in other words, here's an answer. So the answer is, if I have a coherent state with n constituents, okay? So suppose I have a coherent state with n constituents. Now the coherent states that describe black holes or de Sitter and stuff like that, they are special because they obey so-called saturation relation. So they have the occupation number is given by 1 over coupling and is given by the entropy. So this is a saturation relation. This is satisfied by black holes, by inflation, and so on. Now, there are two, it turns out that there are two regimes. So one is when system is classically stable or classically stationary. So if system is classically stable or classically stationary, meaning that it doesn't evolve in time classically, then the quantum break time scales as entropy. It scales as n times for example, for de Sitter, it would be Hubble horizon, which is the same thing as de Sitter entropy times Hubble horizon. So this is in the case if there is no classical evolution. However, if system evolves classically, the story changes dramatically. And if system has, for example, if system has classical Lyapunov exponent, okay, so then the quantum break time goes as 1 over Lyapunov exponent times log n. So it's dramatically shorter, okay? So therefore, and that's an extremely important question because this tells you that the moment you introduce inflationary type degrees of freedom, the quantum break time shortens dramatically. It shortens to logarithmic scale, so to the log of n. And absolutely. So this is extremely important to take into account in inflationary model building and stuff like that. Yeah.
Okay, thank you.
Okay, thank you very much.
Thank you.
Let me bring the attention to the question in chat. Can you see the question or shall I read it?
Yeah. This might be a question similar to Philip's. Gravitational collapse of a star. It generates a coherent entanglement. Is it assumed to be classical at t equals 0? Yeah, I don't know if I understood the question correctly. So presumably the question is, if I take initial matter and I collapse it into a black hole, okay? So how much entanglement does it generate during the collapse, okay? So yeah, I mean, that is certainly a very important question because of the reason precisely that I gave this expression here, because, and please correct if I misunderstood the question, because you see, if I view a collapse, again, this may depend on case-by-case basis, but for example, let's consider a collapse of a classical field, okay? So let's imagine there is some kind of instability in the classical field, and the classical field, some scalar field, and it collapses and produces a black hole, okay? Now, because in that case, there is a intrinsic classical instability to which I can assign Lyapunov exponent, okay? So it may then be that it already inherits quite a big fraction of an inner entanglement, okay? This probably also goes back to Philip's question. So yes, indeed, this absolutely can happen. So in other words, this would then mean that the black hole that I'm starting at t equals 0, a dream black hole, doesn't exist really, because you cannot really produce it out of a real collapse process, because collapse inevitably involves Lyapunov exponent, and therefore some portion of entanglement is already generated during the collapse. That may very well be, absolutely. I mean, that may happen. But again, that will not affect my argument, because my argument was based assuming the the dream situation, basically, assuming the most favorable situation, most favorable black hole, when I take it as being classical at t equals 0. But yeah, this is an absolutely valid point. Yeah, I fully share it. If I understood it.
Okay.
Okay, thank you very much.
Exactly. Yes. Yeah, that's right.
Yes, I'd like to switch to a question to Ivano. Is that possible?
Yes.
Yes. Yes, of course.
Hey.
Okay.
There you are. Good. Okay.
Okay, let me unshare the screen, right? Probably.
Yeah, probably.
Right. Let me do, what should I
I can share instead the talks which we had, just to have them.
Yeah, I can. I don't know what's happening. Stop sharing. Yes.
By the way, Guy, just short request to you. Can you save PDF of what you have written?
Sure. Yeah, and I'll send you by email.
You
Yes.
will upload like your slides. Okay,
Sure.
thanks.
Okay.
Yes. Gio, I wasn't trying to chase you away.
No. I like to be chased away, so it's okay.
No, I wanted to know this from Ivano. A couple of questions. You had said right at the beginning that you were doing ADS5 but not doing Randall syndrome. So I take that to mean that you have an ADS5 but you've not identified points at infinity.
Right.
So that means that the geometry falls off rapidly on one side of the brain but grows rapidly on the other. Now, what I don't understand is how do you compactify a geometry which is growing exponentially, which is what you were doing later on?
Well, no, wait, I did not compactify the anti-de Sitter. That's.
Oh, okay. Well, then we're living in a phi, or we're living in an unconstrained phi space.
We in this scenario are confined to the D3 brain, right? That expands inside of the anti-de Sitter or quasi anti-de Sitter.
No, so I'm saying we can send signals into the bulb.
Yes, we can. But the point of this model, in particular the last one that I showed, is that there is a suppression of all effects related to the fifth dimension, right? This suppression is weighed by this by the square root of the string coupling. So in the regime where the effective field theory description is under control, all the effects related to the extra dimensions are present, but they're suppressed, right? So they appear as higher derivative operators in the four-dimensional description, weighed by this small parameter.
Okay, I haven't seen those kind of calculations, but what you're basically saying is you don't need to compactify to localize gravity to the brain.
I don't need to compactify in order to have an effective description that looks like 4D gravity, right? But as I said in the beginning, this effective description does not arise because gravity is localized, but because the sources are delocalized. That's the catch, right? I think it's very well explained in one of the recent papers by these people from Uppsala. Okay. The catch is exactly this. So if you want to localize gravity, you have to compactify. But if you want to do something different, right? These models do something different. Instead of localizing gravity, they delocalize everything else in such a way that the effective Einstein equations on the brain still behave as if they were four-dimensional. That's the trick, sort of.
Okay, well, I find that surprising, but I'm not
right. No, but of course
they've done the calculation.
Right. Okay. No, but I mean, of course, at the classical level, so at the level of the field equations, this thing works. The question is this sensible quantum mechanically, and more importantly, non-perturbatively? This is a completely open problem, and so we're eventually, we would like to get a handle on that, so as to whether this scenario is consistent quantum mechanically and everything, or if, it's probably consistent, but perhaps gravity doesn't behave as we would like it to behave quantum mechanically. Classically it works, quantum mechanically we don't know. That's the catch.
All right, that was the first question. Second question is this. You've worked very hard to get rid of the 10 to the 120 in the cosmological constant. And that's a thing that has to be done if you have a regular string theory as a quantum gravity. But there's another source of the cosmological constant, which is that as the universe cools down, it goes through an electroweak phase transition. And that releases an omega lambda of about 10 to the 60, which we still have to live with. Even if we get rid of the 10 to the 120, we can't get rid of the 10 to the 60 because the free energy really is released. And to me, that's the real cosmological constant problem.
Well,
because we have very good evidence that there is an electroweak phase transition.
Right, and that's perfectly true. What I would say is that my model, this sort of model, only describes the very late time cosmology, right? This is a model of late time cosmology. So in this sense, the formula for dark energy that I gave at the end is the final one, the fully, IR one, when all the phase transitions have already occurred. So it's the final CC. It's not the bare CC, so to speak.
It's the late CC.
Yes. This is not a model of early cosmology.
Oh, okay. All right. So those models have a different problem, which I don't need to go into, and that is that the early universe will be very different from the way that we think about it. If the cosmological constant effect is big in the early universe and not in the late universe, then our whole description of the early universe has to change.
Yeah.
That would be rather consequential. Anyway, but I don't ask you to do anything about that at the moment.
It's just because the answer is that simply I have no idea.
Okay. Yeah.
This scenario was never born as a full, as encompassing the full history of the universe.
And the other thing I have to comment on is, while not having SUSY, in my opinion, is a good thing, because I don't see supersymmetry as a symmetry of the light cone, which is where I think symmetries begin. But nonetheless, if you don't have SUSY, you're giving up a lot. You're giving up a unification of the running coupling constants. You're giving up the existence of the SUSY as a candidate for dark matter. You're giving up a solution to the hierarchy problem, and you're giving up the Coleman-Mandula, the evasion of the Coleman-Mandula theorem. So not having supersymmetry comes as a high price, which I'm prepared to pay, but I'm curious to know whether you're prepared to pay.
I would say so. I understand your point. Certainly space-time supersymmetry is a likable property, right? It comes with lots of goodies.
Yes.
And this is why, indeed, probably the majority of people who do string pheno still sort of try to build models that have low energy supersymmetry breaking, rather than what I just what I did, which is high energy SUSY breaking. I'm not sure. Perhaps the deepest property that may be necessary for non-perturbative consistency of these models is that these vacua are unstable, right? So they have to decay somewhere. And in this talk, what I presented was sort of the in itinere of what happens. So it's still when the phase is sort of under control, but it's undergoing decay processes. Now, from the point of view of a little guy living on the brain, this can last ages because of warping. But so it may not be problematic for phenomenology, but from a formal theoretical point of view, eventually the vacuum will decay so much that it will enter the strong quantum gravitational regime, or at least a string regime. And it's important to ask what happens there. And it may be the case that only space-time SUSY can save the vacuum from infinite oblivion. So perhaps the deepest reason to want SUSY in this sort of formal theoretical sense is that it saves you from having no vacuum whatsoever, right? And that's totally fine, because once these models enter the strongly coupled regime, usually there are dualities that connect them to the supersymmetric one. So in the end, it may be the case that supersymmetry does play a role there.
Yeah, but then you're back to where you were on your first slide. Then it's just very hard to get down from 10 dimensions to 4 dimensions.
Yeah, no, but the trick is that I'm working in a duality frame where the perturbative regime has no supersymmetry, right? I start there, and then I start making these backgrounds decay slowly, and there's the phenomenology. Like in that setting, we build these cosmological models. Then you wait long enough, and then it decays to a strongly coupled regime, which is dual to a weakly coupled regime, which is supersymmetric in the final state. That's what I would speculate happens. But this does not help solve the electroweak hierarchy problem with supersymmetry, nothing like that. So what I'm saying is that supersymmetry may play a role in the final stability of this construction, but indeed it does not help with the stuff you said. So it does not help solve the electroweak hierarchy problem, or it doesn't sort of point toward particular ground unification theories, even though in this model ground unification can be attained because of because essentially it's achieved by the brains joining together. They're pulled together by the open strings, the stretching between them. That could be a mechanism that doesn't need the SUSY to achieve guts. But yeah, so the final answer is I am ready to pay for to pay the price of not having low energy unbroken SUSY. Because for me, the most important thing is to have a final state which is stable, but that final state, which may very well be supersymmetric, is far away from the regime in which I'm working here.
Okay.
So next question from Alberto Salvio.
So I have a comment actually on the talk by Breno Giacchini. So it's not clear to me that if you have some point-like source, like a delta function, then the field should be regular at the point of the delta function, at the center of the delta function. Because this delta function is an idealization, real sources have some extension. So I don't expect that the theory, even if it's UV complete, would react to this delta function source generating a field which is regular at the point of the source. For example, if you have some Yang-Mills theory, even some asymptotically free Yang-Mills theory, and you turn on a delta function source along some direction in the Lie algebra, there's always a solution which goes like 1 over R, where R equal to 0 is the position of delta function source. And so it is singular at R equal to 0. This is the classic Coulomb behavior of the field when you have a point like charge. And this, again, this is true even if you have an asymptotically free Yang-Mills theory, which is certainly UV complete. Nobody doubts that QCD is UV complete. So I'm not sure that a complete theory of gravity should eliminate this 1 over R behavior, because you're looking for a theory where even if you have point-like sources like a delta function, the Newtonian potential is regular at R equal to 0, where R equals to 0 is the position of the delta function. That's it. This is my comment.
That was also my comment. Thank you.
Yeah. Well, thank you very much, Alberto Salvi, for your comment. But in this regard, there was a discussion about the relation between the renormalizability of a gravitational theory and the finiteness of the modified Newtonian potential. Because, for example, the steady gravity has a finite potential, and it is renormalizable. And if you add more derivatives, you can have a super normalizable theory, still with a finite potential. But it's also possible to have a finite potential in a theory that's not renormalizable. If you have, for example, more derivatives in the spin 0 than in the spin 2, or vice versa sector, then the theory can be can have a finite potential, but it's not renormalizable. So I think when you talk about the theory being finite or normalizable from the quantum point of view, it doesn't necessarily imply, well, I think in this way it works. If the theory, in the case of gravity, as far as we know, if the theory is normalizable, then the potential is going to be finite. But the other way around, it doesn't work. And in the case of for example, the fourth derivative gravity, that is renormalizable. But think on the classical solutions, the families that were studied by Stan and collaborators, for example, the solution that couples to a delta source, it is regular. There are solutions that are singular, but these solutions doesn't couple to a positive definite source. So the Schwarzschild solution is a solution also in fourth derivative gravity, but the source is different. So I think that the effect of the higher derivatives can be viewed as a regularization of the source. Of course, you can also say that instead of if you have a non-local theory, you can ask whether the delta is a good source. Maybe you can have a kind of another source, a non-local source that's going to compensate the effects of the higher derivatives, and then you recover the solution. But then this needs a non-standard source, let's say. But in what concerns the higher derivative gravity and these non-local gravity theories, the potential gets regularized.
Yeah, but my comment was about really the fact that, in my opinion, when you have these idealized sources, the singularity of the field at the position of the source is more a fault in a sense of the source rather than the theory, because it occurs also in QCD, in some asymptotically free theory. So. Which is well defined. I mean, nobody doubts that QCD is well defined and it's a UV complete theory. So my interpretation of this singularity is that they are there because you're putting some idealized source. And so I don't think that you should remove them. You should exclude a theory just because if you put a delta function source, you get a singular potential. On the other hand, the question of the existence of black holes that are singular at the origin is another story. So I don't have a clear opinion about that. So it might be that maybe theories that have this kind of solutions should be excluded. Although if the theory is UV complete, in principle, even if they have singular solution of some position, they could be consistent. I mean, if you have Einstein gravity, which is not UV complete at the position of the center of the black hole, you should replace the theory with something else. But if you have a UV complete theory, it might be acceptable to have. I say might be acceptable to have a solution which is singular in a point. So this is another story. But regarding the fields generated by a delta function source, I don't think that one should exclude a theory just because the reaction of the theory to a delta function source is some field which is singular at the position of the source, because we have counterexamples to that. Okay.
Yes, yeah. Even for example, if you're going to
okay, so you agree with this?
I agree that maybe you shouldn't exclude the theory. I'm not excluding anything.
Okay. No. You didn't say that you wanted to exclude it, but just to clarify what you think.
It's important because even, well, if you consider the Newtonian limit, you can make any other source by superpositions of deltas. And the delta is the most simple, the Newtonian singularity associated with the delta is the most simple singularity that you have. So it's a good start if you want to see if the theory can regularize the singularities or not. And even the Schwarzschild solution, you can obtain it as with the delta. So it's a very important example, in my opinion.
Yeah, regarding the black hole, there is another comment I have that so in Einstein gravity, you have when you have the gravitational collapse, this never ends, and at the end everything gets compressed to a point. But if you have a theory where gravitational interactions are softened at some scale, you don't expect the collapse to occur all the way down to a point. And so even if the theory has solutions, black hole solutions, which are singular at the center, this might not be the real endpoint of the gravitational collapse in a given theory, which differs from Einstein gravity in the UV because of this softening mechanism. Okay, thank you.
Okay, thank you very much for the questions. There are other people who want to participate in the discussion. Huang Wu, please.
I have the question for Diwali. Why the entanglement entropy of Hawking radiation can't bigger than entropy of black hole? And when we say the entanglement entropy, this is entanglement of state A and state B. So in information paradox, where is A state and where is B state?
It's to me, right? The question.
Yeah.
Was it to me? Yeah. So can you hear me? Yeah.
Yeah.
So yeah, this is an important question. In other words, first of all, when just to clarify, right? When I say entanglement, inner entanglement, so I'm talking so when I'm talking about, of course, inner entanglement is a property of a microscopic theory. Okay.
Yeah.
So in that theory, I'm always talking about pure states. The states are pure. It's a coherent state of graviton. It's a pure state. Now, when I'm talking about entanglement, I'm talking about entanglement of pure state. So in other words, maybe I can share the screen just to make it simpler.
Yeah, let me stop sharing, please.
Yes. Okay. Yeah.
Yeah.
Okay. So. Yeah. So in other words, here's the way you can think about it. So imagine I have an n particle state. Okay, so this graviton state, n particle state, and so what happens is that in these states I have constituent gravitons. So there is a high occupation number of these constituent gravitons, n. Okay, and so this is a pure state. Okay, so this is a pure state. Now, right. And then the way you can think of it is like there is a there are these memory modes, and the initial state of a black hole is certain state of a memory modes. Okay, so it will be like, let's say one memory mode has occupation number n1, another has n2, and they are like of order n memory modes. Okay, so there is this state, and now what happens is that this state evolves into a superposition of all possible basic states like this. Okay, so there is some after, let's say after half decay, there is some n prime state number of n primes remaining in the, and then you have superposition of n1, n2, nn, but with certain coefficients, yeah, with some c, n1, n2, nn, where you are summing overall. Okay, so this is what I mean under entanglement, because this state now is maximally entangled. It's a superposition of exponentially large number of basic states. So basically, if you, for instance, if we restrict ourselves with zeros and ones, you would have the following structure. It would have 0, let's say 1, 1, 1, 0, 0. Then you will have with one coefficient alpha, then another coefficient beta, 1, 0, 0, 0, and so on. So exponentially large number of states entering in this pure state. So that's what I mean under inner entanglement. And so this inner entanglement as a phenomena itself is completely independent of radiation, of entanglement between black hole state and radiation. Because what happens is that in addition, this inner state, this black hole state, let's call it black hole, then of course this becomes also entangled with radiation, of course with radiating quanta like gamma 1, gamma 2, etc. That's a different phenomena. So here I'm only restricting myself by inner entanglement, internal entanglement of a black hole. And so, so this one, of course, can also be measured by growth of an entanglement entropy, absolutely, but it's not the same entanglement entropy as the Page's entanglement entropy between black hole and outgoing radiation. And so what we see is that both entropies increase, both entanglement entropies, of course, increase. Now, this one, and so what happens is that at the end of the day, because of this back reaction, what we see here is that it plateaus out, sort of, and then there's a big question mark. What is happening to black hole after that? Okay, this is an unexplored territory. Okay, but in other words, there are three effects that go hand in hand. There is internal entanglement, Page's entanglement, entanglement by Page, and then this memory burden effect, which is represented in the thing that these memory modes, initially their gaps are very small, energy gaps. They have energy gaps initially which go like 1 over n times 1 over r, where r is the black hole radius. And then after half-life time, this evolves into a huge gap, which is 1 over r. Now 1 over r is a very big gap because there are too many of those modes. And so so yeah, that's also part of the entanglement. So that's also part of the engine why this is generated. Yeah. Okay, so does this answer your question?
Okay.
Okay.
Okay. Yeah.
Okay, very good. Since I will use this opportunity and just comment on the other. I agree with Alberto fully that about the previous discussion about this singularity. I fully agree in general that I don't see why we should fight singularities, 1 over r singularity, because like from what 1 over r singularity is a signal that theory must change a regime. That's what it is, and so yeah, I don't see why one has to insist then in this singularity should be classically removable, because that never happens in this example of QCD, asymptotically free theory is a very good example. I mean, we know that the singularities, they are not resolved classically. Even in electrodynamics, singularity is not resolved classically. It's resolved by quantum effects. Therefore, I don't see why you should take this as a guideline that the black hole singularity must be necessarily resolved classically. I just don't see that. And I don't think that in fact, I don't think that is the case. Because usually the way consistent theories work, they resolve singularities by quantum effects. And so that's what we should expect also for gravity. I don't see why gravity should be any different.
Can I comment on what I think Brenner was trying to say? Because Alberto, Gia, and I are all in agreement that there's nothing wrong with getting a 1/r. However, I think Brenner is saying something else. To do renormalizability, you've got to look at short distances far off the mass shell. To study the 1/r potential, you've got to look at low energy on the mass shell. Now you solve the exterior Schwarzschild problem and you find a 1/r, but you don't need to know, is it going to be 1/r in the interior? And the answer is it shouldn't be. But I think what you're saying is that theories that will have good ultraviolet behavior will have as an exterior solution one in which the 1/r is softened by some factor like e to the minus mu r. I think that's what you're trying to say. You're not saying that that solution is therefore going to hold at r equals 0 as well. You're just saying that having solved the exterior problem in the Schwarzschild, in the analog Schwarzschild case, you can correlate that with the behavior of the theory far off the mass shell. Is that what you're trying to say?
My impression was different, but maybe my impression was that there are these attempts. Also, there are several attempts in the literature, which, frankly, yeah, I have a different opinion because, I mean, there are these attempts to sort of provide classically regular black hole solutions. I mean, that I don't see anything wrong with it. Of course, sure, if you have a fundamental theory that gives you classically regular black hole solutions, maybe it should be taken seriously. I don't know, but that absolutely never happened in consistent quantum field theories. In consistent quantum field theories, 1/r and other singularities, they're resolved by quantum effects, not by classical effects. So therefore, I mean, I don't see why this guideline should be a necessity. But yeah.
No, I'm only asking.
What is going to solve the singularity? This I don't know, and probably it's only quantum effects. I agree, but also there might be theories that solve the singularity already from the classical point of view. That's also an option, and these theories, they are the theories, the models that I consider, they are very much studied in the framework of perturbative quantum gravity, and already at the classical level, they seem to improve the behavior of the potential, the regularity of the solutions. So
no,
I
sure.
This is interesting.
No,
but,
sure. I mean, I'm not saying, I don't have a theorem which says that every time you resolve singularity, you manage to resolve singularity within a classical theory, there is something wrong with the theory. I don't have such a theorem. But usually from those theories that we know for sure are consistent, this never happens. Usually 1/r classical singularity, in fact 1/r or whatever classical singularities, when they are real singularities, they tell you that there is some new quantum physics happening around that point, and it is the quantum physics that usually resolves those singularities. But of course, I don't have a theorem which says that necessarily this should be the case. No, yeah, I mean, yeah, I would just say that, I mean, we don't have to insist on that. So even if theory doesn't resolve singularity classically, this is still okay, like Einstein theory. Now, in Einstein theory, we know why singularity is fictitious, because once you go to a distance of order L Planck length, you start producing micro black holes. You cannot localize anything in Einstein theory at distances shorter than the Planck length, because it would require energy, and that energy will produce a bigger black hole. So in Einstein gravity, actually, this is automatic somehow, that the theory prevents you from probing singularity in a sense, real physical singularity, and that's great. Yeah, but that's all. That's all I was commenting on. I'm not, yeah. Also, if you take, for example, gauge theory, right? In gauge theory, what do we have? We have singularities, two types of singularities. We have singularities that are magnetic, for example, Dirac monopole, and we have singularities that are electric, a charge, right? Now, the magnetic singularities can be resolved in a classical theory. For example, Dirac magnetic monopole, you can resolve it as a Toft-Polyakov monopole. That's perfectly fine. But the electric singularities are always resolved by quantum effects. They are never resolved like by, there is no classical solution in electrodynamics or in QCD for the like smooth classical solution for the charge. Yeah, sorry, this is just a side by, but I think this is important to keep in mind. So.
Anyway, but I still, Gia, I agree with you, but my question was slightly earlier. Was Breno saying that if he could take the pure exterior solution to a gravity theory and find that it had no singularity at 1 over r, even though we know that you shouldn't be using it at 1 over r as is, but he's saying that if that's the case, then at the same time, those theories in the short distance behavior far off the mass shell will prove to be renormalizable or even super renormalizable.
No, that may be, yes, but of course,
was that Breno? Was that your point?
Right? No, sure. No, that may be, but I mean, in general, of course, that has to be shown that the theory is consistent. I mean, the fact that theory is renormalizable doesn't make it consistent, of course, as we know. Because
there's more. I'm just trying to, I'd like Breno to tell me, was that what you were trying to say?
Yeah, I think this is one point, but the other is the simply study of the structures of the solutions of the model, because these models are very much studied nowadays. And in the case of fourth derivative gravity, you can study the space of solutions, and there are many works on this. But with more derivatives, and especially in the case of non-local theories, this is still an open question. And then the beginning is the starting point is to consider this kind of solutions, the linearized solutions, and the effective sources associated with. So I think when I started studying these solutions, 5-6 years ago, the goal was to have this relation between the renormalizability of the theory and this, the regularity of the potential. And I think they are related in one way, like you said.
Okay, that's what I thought I was trying to do. Now I want to make a comment. I have a counter example to what you've discussed. It turns out that if you take second plus fourth, just r plus r squared, it's renormalizable in the ultraviolet, and it has a 1 over r potential in the infrared. So I don't think you have to correlate renormalizability with good behavior at r equals 0. I mean, that's a simple counter example. I'll talk about it a little bit tomorrow, but basically, I don't think that you need to correlate renormalizability with, let's say, good behavior of the curvature invariants. And I mean, Gia and I and Alberto were saying you don't even need to do it in the real world anyway, but it's still an interesting physical phenomenon to ask whether there is a correlation between the ultraviolet and the infrared.
And let me just return to something that I said replying to Alberto Salvio, because I don't know if I was clear. I said that in the case of fourth derivative gravity, the solution that couples to the delta in the linearized theory is has a finite potential, but it has non-regular curvature invariants. And even in the nonlinear regime, it's also like this. There are regular solutions, but they don't couple to the delta. And in the case of 6 and more derivatives, it's still open. Okay.
Okay.
Well, let me also briefly comment that in principle, even in renormalizable gravity, it's possible to have black hole solutions with normal singularity. So I mean, in the stellar gravity, there is a class of solutions which is still singular in the center. So it doesn't seem to be related to the renormalizability issue. And another comment is that all the theories which contain finite higher order derivatives are all non-unitary. They contain ghosts, except maybe the case of infinite number of derivatives where it's less clear what's happening, but still, I mean, probably from the picture which Gia was thinking about, probably it's not the same. I mean, there is an assumption of unitarity.
Yeah, I agree, fully agree. Yeah, exactly.
Kind of not clear whether it can be implemented.
Yes,
so
absolutely.
I mean, from what Gia you are calling a good theory, a good UV theory, probably you assume that it's unitary at least.
Absolutely, absolutely. No, thanks very
All
much.
higher
Yes,
derivative
yes.
attempts are a little bit,
Yes.
well, it has to be proven what's happening.
Yes, thank you very much. Yeah, this was exactly my point. So I meant like usually these theories with good classical behavior, as you said, they are high derivative, therefore they contain ghosts, and thereby as quantum field theories they are not really consistent, strictly speaking. And yes, indeed, yeah, that was the point too. Therefore, yeah. So this may be another sign of sort of. So, but okay, that's a general question. Yes, thanks very much for
Okay.
clarifying
So
it, yeah.
we probably we had one more question from Marco Piva. So please go ahead.
I also have a question for Breno. I had more than one, but I forgot most of them because I had them during his talk. But well, one thing that I remember that I wanted to ask, it's very maybe naive. I don't remember exactly all the slides, but at some point you said that there is that the potential in the case of even 6 or more derivatives has some kind of Yukawa-like term, right?
Yes.
And was it with the whole mass or just the real part of the mass in the exponential? Because, you know, in the 6th derivative case, for example, if you adjust the coefficient, you can have complex conjugated ghosts, like the one that Leonardo was mentioning today.
Well, in the case of, yes, with 6 derivatives, you can have real or complex or a pair of complex conjugate poles in the propagator. If you have the real poles, then it's the exponential, it's the Yukawa-like with the mass.
Yeah, so the question is, how is it in the case of complex? I mean,
in the case of complex poles, since they are complex conjugate, then the potential is still real. And then what enters the exponential is the real part of the pole. And then you have the complex, the imaginary part that contributes oscillatory function.
Yeah.
So you have a cosine. And because since the 2 poles, they are complex conjugate, then you have these.
Yeah. So if they're complex, they are complex conjugated. And I guess that they appear with the same, the exponential in the Yukawa term has the same coefficient, right? For both the mass and the complex conjugated mass.
Yes, you have well, in that case, it's not, if you can get the formula and just substitute the mass in the Yukawa to the complex mass, and then you expand everything, and then you get something that's not Yukawa anymore. There is the exponential, there is 1 over r, and there is the cosine.
Yeah, so but so if you go to large distance, at some point you should see something that is not Coulomb, Newton.
Yes, and there is also this oscillations in the case of complex poles.
Yeah, but isn't it in contradiction with, I don't know, some macroscopic observation or not?
Well, then it depends on the scale of the theory. It depends on the values of the mass. If the masses are very huge, very big, then they have a very short range, and then you can like choose a value that doesn't affect the physics that we see nowadays. And but also you can, in this case of these oscillations, for example, there are some works studying oscillations in the gravitational force using torsion balance experiments and these things. And so there are people investigating whether we can, from the experimental point of view in the lab, see oscillations. And then in some cases they use these models that predict this to make some bounds on the parameters. But and also in the case of non-local gravity, if you have, instead of like exponential of box, if you have higher powers of box, you also have oscillations in the potential. And but then it all depends, if you can actually measure this, it depends on the range of these modes. But if it's very short.
So you're saying you can make it large enough so a cosine looks like I don't know 1 over r in some part or something like this?
Yes, yes. At far away, it recovers 1 over r.
But there should be a limit, to this mass to have this.
Yes, yes, yes. But if this mass is very small, or if you go enough far, then the potential tends to 1 over r. So you recover the GR limit, the Newtonian potential.
Okay. Can I also ask to Philip what was his counterexample, because I didn't understand?
Oh yeah, I'm sorry. It's second plus r squared.
So Starobinsky theory, you mean?
Ricci scalar plus Ricci scalar squared is a renormalizable field theory that was proven by Stella, and it has a 1 over r potential.
That is not renormalizable.
Yeah, it is. That was Stella's result.
No,
it's got a 1 over
Ricci squared.
Ricci squared. Yes, it's got a 1 over k to the 4 propagator.
Yeah, yeah. So all of them, but you need all of the quadratic invariant.
No, just r plus r squared.
That's
just
not
on its own. Anyway, that was my point. But my point is that it has a 1 over k to the 4 behavior at large k, and it has a 1 over r behavior at small r. Sorry, large r. That was all I was trying to say. And
but it's not renormalizable. So
why is that? Well, what did Stella get wrong? What did Stella get?
Stella is renormalizable. Stella is not r plus r squared. It's r plus r squared plus Ricci squared.
Ricci r squared is Ricci squared. Yes.
Yeah, you need to put all of them.
Oh, you mean r mu nu squared?
Yeah,
Riemann square. Yeah, Riemann.
Sorry, when I say Ricci, I mean Ricci tensor.
Y tensor square.
You mean r? Okay.
Okay, so
you could mean c squared. You could mean r mu nu squared. You could mean r squared.
Yeah, sure.
Okay, all right.
So you were saying that in stellar theory, there is 1 over r, small r.
Yeah, 1 over r occurs in all of them.
Okay.
That was what I was saying. But I have to go. But let me just say this: the statement that high derivative theories are not unitary because they have negative norm states is not correct. Carl Bender and I have discussed that, and I'll go over it again tomorrow in my talk. But the point is that in that Hilbert space, the Hamiltonian turns out to be not self-adjoint. And therefore, you have to go to a different Hilbert space where it is self-adjoint. And in that one, the inner product is positive definite. And I'll discuss that tomorrow. But the hidden thing that people ignore.
I cannot resist not to. I know it's late, but I know it's late, but I still would like to separate the issues. I mean, if you have a program that somehow attacks this very fundamental question whether we can work with high derivative theories properly and somehow, that's a whole different program. But that, and I admire if you are working, if you are doing that, that's fine. But I would not, until that program is finished and we know that everything is okay, I would not bring these theories with ghosts at the same level as other observational things, because I mean, in this theory, with high derivative theory, yes, it's renormalizable. We know that we have a ghost, and it's a textbook knowledge that ghosts are problems.
It's not correct, because look, you presuppose that you were working in a Hilbert space where the Hamiltonian was self-adjoint.
No, that's what I mean.
And it isn't.
Yeah, but these are revolutionary program that it's fine. I'm happy to discuss that and go along with you. But you see, we cannot. What I mean, we should not mix up the issues. Up until you come up with that program that will prove that we can work with ghosts. Right, but still. Up until that we really understand what's going. To just declare that, okay, theory has a ghost, but then, so what's the problem? Let me go out and measure Newtonian potential and cosine oscillations.
No, it was.
I mean No, I'm not talking about you. I'm saying about this program that, you know.
Thank you, Gia. I would never have even have entered this discussion.
No, of course. I'm not talking about you.
If I hadn't already addressed the ghost question.
No, I understand.
I think without addressing the ghost question, the whole discussion of high derivatives is hypothetical.
Absolutely, that's precisely my point. Now, regarding your thing, we can discuss it separately. That's a separate story. But I'm saying that if we, for a moment, if we just simply stick to what we know from textbooks, and then we cannot just simply say, "Oh, this theory has high derivatives; it has a ghost, but it's okay. Let's go and measure some oscillatory potentials and these kind of things," because that sort of, that sort of makes it very.
Okay. In fact, Gia, I'll
undermines the whole thing about quantum field theory.
I'll make life even easier for you. What I'll discuss tomorrow is not merely that the ghost argument is wrong, but also that the vacuum in which you think there's a ghost is not normalizable, and therefore that means the Hamiltonian being self-adjoint will tell you that. The fact that the vacuum's not normalizable means that even at small r, where you think you can do Newton, it's not correct, because you're working. There's no Hilbert space which has a finite 1/r potential as its output in a high derivative.
That's all very interesting. But as I said, but that's precisely the point. One needs to enter in those type of discussions. And then after a lot of fight and a lot of discussion and argument, perhaps we will come up to some common denominator in that case. But what I was trying to say is that, without addressing the issue of ghosts, just simply to say that high derivative theories are okay and we can just do observation.
Not only do I agree with you, and which is what has triggered the research that I've done with Carl Bender, but it also responds to another point that Brenner raised, and that was that you generate higher derivative theories regardless of whether you started with r squared or r mu nu squared in the initial Lagrangian. You just do a fermion loop in a background gravitational field, you get high derivative terms. Now,
but there's infinite.
They are not unitary. They're not unitary. Then SU3 cross SU2 cross U1 is destabilized when you couple it to gravity.
No, but there you have infinite series, and then one has to. So that's different, because that's okay, because you see that simply tells you that a cutoff sensitivity introduces new physics, and you have to address that new physics. That's okay, but what I'm trying to say is that we cannot cherry pick. We cannot say, "Oh, look, I have that just fourth order derivative. Let me now, without addressing the fundamental consistency of the theory, only pick up the pole, a complex pole, and say that this gives some observations." And that's what I'm saying. I'm saying that
I'm in complete agreement with you.
Okay, very good. Yeah,
I'm going more. I'm saying is
sorry for interruption.
If you don't want to do high derivative gravity, Brenner was pointing out that radiative matter loops will force you into high derivative gravity.
Sure.
So you always, in the end, you have to deal with the problem.
No, that's absolutely correct.
And it's not even the problem of renormalizability of gravity. It's the problem of unitarity of gravity.
No, absolutely, yes, absolutely, yes. Yeah.
And that means that 3 × 2 × 1 stops being unitary if you couple it to gravity. So something radical has to be done, and that's what Carl and I are claiming we've done. I mean, we're fully aware of that issue.
Well, okay, I mean, yeah, we agree on the fact that gravity requires UV completion, meaning that we have to understand cutoff sensitive part, and that I fully agree. Yeah, that's yeah, of course, yeah. We agree.
Well, integrating out Fermion loops can just bring you to some effective field theory formulation, which of course will contain higher derivatives, but this is not something that should be treated like this theory contains ghosts. Okay, formally it will contain ghosts, but the mass of the ghost will have the size, will have the quantity which is at the place where precisely the theory breaks down.
Yes, Anna, that used to be the argument, but I've brought a new argument, and I'll talk about it tomorrow.
Yeah, that's
it turns out that the vacuum is not even normalizable, even in the effective theory, or what you think is the effective theory, namely you're way below the mass of the would-be ghost. You still don't have a normalizable vacuum. And that's something that I only found out recently, and that's why I'm now broadcasting it. But nonetheless, that's an actually more severe problem, because you can't even get away with an effective theory anymore.
Well, this is very strong thing, which is actually breaks down all EFT approaches, which are common.
Absolutely. I think it breaks down everything, but I'll show you, if I get a chance tomorrow, I can save everything. All you have to do is find a Hilbert space in which the Hamiltonian is self-adjoint. And then everything that you've been doing actually works. And then there's no ghost problem to begin with. So you'll see.
So sorry to interrupt. So you mean kind of you want to find a new way to normalize vacuum? That's what you say.
Not to get rid of a Dirac norm which is infinite. You see, a Hilbert space has all the wave functions in a Hilbert space have to be square integrable. Yes. Now we've always assumed that when we see a ghost, we haven't asked, well, in that Hilbert space, are the wave functions square integrable? And the answer turns out to be no. And that was the thing that Carl Bender and I showed. And therefore, if they're not square integrable, you're not in a Hilbert space. So you've got to find another Hilbert space where they are square integrable. And then you look to see whether that one has a positive norm. And the answer is it does. And then, of course, if the wave functions are square integrable, the vacuum's normalizable. That's the issue. That's the issue.
Okay, I think it will be nice to discuss tomorrow.
Yeah.
Yeah, so tomorrow it looks like we'll have another.
Yes, I can't make the first session. I'll join you for the second session, but I won't be able to make the first session. I think starts at 1 o'clock in the morning where I am. Let me see.
Yeah, indeed.
Yes, so you're at session 1, 8:15 Central. Oh, so that's 2:15 in the morning. Oh, that's still hopeless.
It's a little bit early indeed. So are there any other questions?
Wednesday we will start early. We will start late, so maybe
that's fine. That's fine. Yeah. Can I tell you before we go? Can I tell you Sidney Coleman once made the following joke? He was asked to teach an 8 o'clock in the morning class, and he said, "I can't stay up that late."
Yeah. Okay. Good. Yeah, indeed. So other questions, more questions?
No, anyway.
To discuss right now, some urgent questions.
I think you can stop recording.
Okay, see everyone tomorrow. Bye-bye.
Yeah. Bye-bye. So just to remind that tomorrow we start roughly the same time. So roughly tomorrow's schedule is the same. I mean, timetable. Yeah. Yes. And everything is on the website.
Bye. Okay, bye-bye, everyone.
Hi, Richard.
Bye.
Is that Richard?
Yeah.
Yes, it is me.
Richard, hello.
Hello, Richard.
Howdy.
Hello and
Hello,
goodbye.
American.
I'm afraid and goodbye.
Okay, I'll be there tomorrow.
Oh, very good. We'll meet up during the week. Bye-bye.
Okay. Thank you. See you tomorrow. Bye.
See you. Okay, Alexei. Good night.